Welcome to everybody. This is Gaetano Guerra, the President of Italian Chemical Society, which is the institution which organizes the Avogadro Colloquia. This edition of the Avogadro Colloquia is co-organized between Italian Chemical Society and National Research Council of Italy. This is the 5th edition. Also the 4th edition was co-organized between these two institutions, thanks to Maurizio Peruzzini, which is in some place there, and Angela Agostiano. And also in this occasion, Angela Agostiano, which we speak in few minutes, and we have maintained this organization between the two entities. This edition, you know, is relative to, as this title, From Water to Chemical, Vision and Opportunities of Sustainable Hydrogen Society, a very important topic, very relevant in these years. We have outstanding speakers which will tell whatever is relevant in this field. The meeting is organized in 4 sessions. The session 1 on hydrogen production, the second one on hydrogen storage and transport, the third one on chemicals from hydrogen. The fourth one, that one of tomorrow morning, will be in Italian because it's devoted to the politics of decarbonization and Italian politics of organization. So for this reason, will be in Italian, the session of tomorrow morning. Let me conclude my short welcome address, starting with some acknowledgements for people which has contributed to the scientific organization. Then Lydia will make also acknowledgements about organization, administration, and different kind. This is the list of people which has worked on the scientific organization, the executive committee of SCI, of Italian Chemical Society, and the scientific committee, which include many people, many of them are in this room. Let me specifically acknowledge 2 people, those which are indicated with bold letters in my slide, which did most of the work for the scientific organization. Elio Giamello, which is somewhere, is there, and Lydia, which will speak in few minutes. Thank you very much to everybody to be here, and good work. Now I will introduce Xavier Garcia, which is president of IUPAC. IUPAC is, everybody knows which is IUPAC, so I will give the word to him immediately. Sorry, I have to remove this. I don't know if you can. We cannot hear you.
Are you sure you cannot hear me? My microphone is on.
Now we are, please, Xavier.
Microphone is on. Can you hear me now? Hello?
Please.
Hello, can you hear me?
You can go.
Can you hear me now?
Yeah, we can hear you.
Okay. So, buongiorno once again. Thank you for the opportunity. I wish I could be in the beautiful city of Rome, but I'm currently in DSCTM. It's a major conference where societies from Europe, Africa, and America are meeting. But anyway, thank you very much. I really am delighted to be part of this Avogadro Colloquia. Congratulations to the CNR for its 100th anniversary. I think it's wonderful that society, like the Italian Chemical Society and the CNR are putting together this wonderful colloquia on a very topical issue, which is the hydrogen economy. With the war in Ukraine, we are seeing a shortage of natural gas, and when people don't create problems, chemistry provides solutions. And the kind of talks that I saw in the program are going to be about production of hydrogen, the storage, and then the transformation of water to chemicals. And I think they are not only very relevant, but also highly inspiring. At IGPAC, we have launched a series of initiatives on sustainability. Start with, we are now in the International Year of Basic Sciences for Sustainable Development. This is a wonderful opportunity not only foster basic research, but also science-based solutions to tackle our biggest problem. Also, through the Interdivisional Committee on IGPAC for Green Chemistry for Sustainable Development, we are launching many programs, and I just want to mention one of them has been a great success. That's a workshop and some pedagogical materials deal with events. I don't know if you're aware of these major issues, but we are constantly using a lot of electronic waste. Some of our most care elements are in the electronic devices we use every day. We dispose them mainly in Africa, and we are not able to recycle all the electronic waste we are producing. That's again a challenge. Very recently, the IGPAC Green Chemistry Conference in Athens gathered hundreds of researchers talking about sustainability. And because of all of that, I'm delighted that the CNR and the Italian Chemical Society decided to put this Avogadro Colloquia not only hydrogen, but also sustainability in general. I want to say a few words also about what we are doing in our global conversation sustainability. And again, another initiative launched through this year with the International Chemistry Net, and that's an opportunity for everybody to engage in a local conversation about how our cities, our nations can be more sustainable. Finally, I will mention an initiative that again has been very successful. I hope all of you are already aware. IGPAC top-training emerging technologies in chemistry. Every single year, we get nominations on technologies that scientists from all around the world think they are going to transform the chemical industry. And our experts select 10 technologies that we want to highlight because they provide hope for a more sustainable future, to increase our productivity, to make our industry more sustainable, and also to well-being. We launched the 2022 Top 10 Emerging Technology Chemistry very recently, and now they are going to appear in underadvanced chemistry. Some of these technologies involve not only green hydrogen, but also green ammonia, which is, again, a great opportunity for the transition from natural gas to water-based solutions that don't involve emissions of CO2. Last week I was in Cairo attending the African Chemistry Education Conference, and as you know, just before that conference, Cairo was hosting the 2027. And once again, our leaders have failed to agree on the kind of agreement that society is demanding. Climate change is a real threat. Our leaders are not responding to the demands of society to really fight climate change in an effective and urgent manner. It is also up to the chemistry community to provide those solutions. And I'm convinced that this Avogadro Colloquia is not only to provide the solutions we need, but also new avenues for it. With that, congratulations again on the 100th anniversary to the CNR. To wish you on behalf of IGPAC wonderful and very successful colloquia. Greetings to Lydia, the president of our division on organic chemistry. Have a wonderful day.
Okay, thank you. Thank you very much, Xavier. Thank you for your contribution. Let us thank you and IUPAC to be present here in our meeting. Thank you very much. Thank you. Let's go now to the next welcoming address from Angela Agostiano, which is past president of Italian Chemical Society, and let me say more relevantly is the president-elect of EUCHEMS, European Chemical Society. she always say from January. Yeah, from January, but you are already the president-elect of European Chemical Society. Please, Angela.
Thank you very much. I will give a warm welcome to all of you. I'm very happy to be in this room because this room is such a symbol for the collaboration between the Italian Society of Chemistry and CNR, because over here the Avogadro Colloquia have always have a house, and my research has been for most half of the total has been possible thanks to the CNR. Now I'm happy to be here as president of UCAM, and let me say first of all that I really congratulate with the organizer of this Congress, because they choose a team that is related to the chemistry way to try to solve the problem connected with hydrogen. And from hydrogen we know that all of us, and also the society, is asking for answer, because we repose a lot of hope in the answer that can give this field of research. We live now, I believe, in really strange times in which the geopolitical asset of the world is completely changed, and also all the ghosts that we relegate to the past, like war, like pandemic, like all the problems related with the change of climate, are again back. And we have to find solution to fight this problem. And it's sure to all of us that this problem, this huge problem, cannot be solved by a single person, neither by a single nation. The collaboration between researchers from different disciplines is relevant for researchers from all the world to try to face this problem and to find problems that have to be equal, should have equity inside, should be inclusive. And so I think that we have to really talk about interdisciplinary, but between the other disciplines, chemistry has a huge role. And I think that the goal, the target of this Congress is to show how chemistry can solve several problems, from the production to the utilization of hydrogen, and try to help a lot of problems that the civil society is waiting to be solved. From the other side, I will be the president of UCAMS, and UCAMS is an umbrella society, and so talks for 51 other society and more for more than 1,500 people. And as umbrella society talks in the behalf of all the chemists in the world. And this is important because it's important to help create a network, because only by the network we can find solution, but also to ensure that the solution that we find are ethical, are sustainable, are inclusive, and so without having always a focus on the freedom of science. Then what UCAMS and the other organization also as UPAC wants to do, it talks on not only with scientists trying to put together their effort, but also to the social society to try to let people, scientists, understandable by the society, to avoid that in the future we can find the problem that found now with the war and with the pandemic, and to be prepared for the old and new emergency that we will find. And we really hope, I hope, and I think that it is the hope of all of you, that this workshop, this initiative can give some of this answer, can show how chemistry is a powerful science to solve this problem, and we should be honored to be chemistry and to have the power to deal with this problem and to offer to all outside the results of what we do and the fact that we do this ethically and also democratically. That I think that is one of the best things that we have to ensure from the inside, from this place in which scientists talk and outside that listen to what we do. Then good luck. I hope that we will talk freely and openly, and so the solution that will come out from this meeting will be really solution that can help to deal with the problem of energy. We do have a nice time, and I will stay here and listen to you. Bye.
Now we have the welcome address from Lidia Armelao, which is Director of the Department of Chemical Sciences and Material Technology of CNR. As you know, this is an umbrella organization with all the institutes of CNR which works in chemistry and in materials. Please, Lidia.
Thank you. So, dear guests, it's my great honor and pleasure to welcome you in this very representative and extraordinary Aula Marconi of the National Research Council. I'm delighted to open this edition of Avogadro Colloquia together with the President of the Italian Chemical Society, the President-elect of the European Chemical Society, the President of the International Union for Pure and Applied Chemistry. So the President of CNR, Maria Chiara Carrozza, cannot be present today due to urgent institutional duties, but she will hopefully attend the symposium tomorrow. So, as already mentioned, Avogadro Colloquia is a triennial symposium jointly organized by the Italian Chemical Society and the Department of Chemical Sciences and Materials Technology of the CNR. And it is usually focused on frontier issues where, as mentioned by Angela, chemical sciences, innovative materials and new technologies play an enabling and central role for the development of a sustainable future. Avogadro Colloquia in 2022 is even more special for the scientific community and for the CNR in particular, since it represents the first of a long series of events for the celebration of the centenary of the CNR Foundation. Indeed, CNR was founded on November 18, 1923 by the prominent physicist and mathematician Vito Volterra, and it was funded as a moral institution with the role of representing the Italian scientific community at the International Research Council, and with the aim to coordinate and to encourage the national activities in different areas of scientific research and its application. So this year, as already mentioned, Avogadro Colloquia is dedicated to hydrogen and to the fundamental role played by this energy vector to create a sustainable energy future. So I wish you all an interesting and fruitful meeting, fruitful debate and discussion. I thank you again for your kind participation, and I leave with pleasure the floor to Lucia Curri for the first scientific session that will be focused on hydrogen production. Thank you very much.
Good morning. It's a pleasure for me to open this first session of the 5th edition of Avogadro Colloquia. As we heard, this session is on hydrogen production, and the session will be opened by the plenary lecture delivered by Professor Strasser. Professor Peter Strasser is the chaired professor of electrochemistry for energy conversion and storage at Chemical Engineering Division of Department of Chemistry at the Technical University of Berlin. Previously, Professor Strasser was a professor at the Department of Chemical and Biomolecular Engineering at University of Houston, and before that, he was senior member of CIMIC's Technology at Santa Clara, USA. Professor Strasser got his doctoral degree in physical chemistry and electrochemistry from Fritz Haber Institute of the Max Planck Society in Berlin, under the direction of the chemistry Nobel laureate Professor Gerhard Hertl. In the same year, 2000, he was also awarded the Otto Hahn Research Medal by the Max Planck Society. Professor Strasser has been also visiting scientist in Sony Central Research in Japan, and studied chemistry in Stanford, in Tübingen, and also here in Italy at the University of Pisa. Professor Strasser is a renowned eminent scientist in fundamental material science and catalysis for electrified liquid-solid interfaces, and in particular for renewable energy conversion, energy storage, production of fuels and chemicals. And today, Professor Strasser will talk on electrocatalytic materials and interfaces for the production of solar fuels and chemicals. Please.
Not 100% sure. I think it's this one, isn't it? No. I don't know where he put it. No. Oh, yeah, this one. Okay, let's see. Sec. Okay. Thank you so much. You need to?
To share with for the streaming. Okay.
All right. Yeah, thank you very much for this wonderful introduction. Good morning, everyone. It's my pleasure and privilege to be here with you in Rome and share some of our recent work in the area of green chemicals and green hydrogen. In particular, I would like to thank Professor Giamello for the personal invitation to this event. So let me see. Okay, so I will start my journey this morning with these two gentlemen. You may probably recognize them. Do we have a pointer here by any chance? But maybe I'll do it with my mouse. Let's see. Yeah, you can see them. So on the left, you see Fritz Haber, and on the right, you see Franz Fischer. So, and I picked these two gentlemen not only because they were students and professors at the Technical University in Berlin, where I'm from, but also because they're so well known for their processes which turned gray hydrogen into ammonia and gray hydrogen and CO into hydrocarbons. And these two processes, among others, became actually the basis of the chemical industry of the fossil 20th century, which followed essentially this paradigm. The molecules that we needed came from fossil sources, and so-called fossil refineries basically provided the molecules for our everyday life. However, what's not so well known is that the green hydrogen and the green chemicals revolution started right around the same time when these two people were developing their gray hydrogen processes. And who would know that better than the Italian Chemical Society? Because in Umbria, Luigi Casale started in 1921 his green hydrogen and green ammonia company, Ammonia Casale. So we're celebrating about the 100 years of green chemicals already. And what I brought you here on the right is actually his patent of a alkaline water electrolyzer, which was filed in 1922 and then later awarded in 1925. So this is really the start, I would say, of the green chemistry and green chemical revolution. And what Luigi Casale really did is that he was scaling up water electrolysis already then to the several hundreds megawatt scale. So you see here plants of water electrolysis driven by hydropower. Yeah, this was the kind of renewable energy available at the time. And this was an enormous feat, yeah, that most people have forgotten about. Eventually, Luigi Casale's technology ran into the same problems like the electric cars, which were also very abundant at the beginning of the 20th century. They ran into big oil and they ran into scale-up problems. And this is why today all of this work sort of often becomes forgotten. However, the inspiration from Luigi Casale is really that we replace our fossil refineries through so-called e-refineries. These are devices that turn free electrons into molecular bonds. And today we coined a new term for this, and we in Germany work a lot on this. This is called power to X, which is basically a connection between electricity and the world of molecules, which is the world of chemists. And I personally divide power to X in two worlds. There is a bright side to power to X, where the free electrons are being generated today, not only with hydropower, but with solar and wind. And then these free electrons are basically helping to convert molecules, valorize molecules, into fuels, into chemicals, into building blocks, chemical building blocks, that may one day also provide the same kind of chemicals as we receive them today from fossil refineries. We have lots of choices. We have gaseous fuels like hydrogen that we want to talk about, but we can also make, via these electrochemical devices, directly hydrocarbon molecules, oxygenates, and commodity chemicals like ammonia or hydrogen peroxide, for example. At the heart of these devices, of these electrolyzers, are electrified solid-liquid interfaces, at least when they operate at room temperature. And this is why it is so important to study these interfaces and to engineer the interfaces to understand the catalytics and the reactivity at these electrified interfaces. And this is what my group does. So today I brought two topics for you. I would like to talk a little bit about the generation of green hydrogen from water electrolysis, followed by a few words about the electrocatalytic CO2 valorization to e-fuels and e-chemicals. We have more electrolyzers at our disposal today than Luigi Casale had 100 years ago. We still have the liquid alkaline electrolysis technology, the most established and validated one. We have the polymer electrolyte or proton exchange membrane water electrolysis, already commercialized, for example, by Siemens Energy in Germany through their Silyzers 300 that you can purchase in a 17 megawatt version. And we have more emergent types of water electrolysis technologies. That is the alkaline membrane electrolysis and the high temperature electrolysis. And behind each of these technologies, there are real companies now which are trying to scale up and to ramp up a market to make green hydrogen. So ThyssenKrupp, for example, stands for liquid alkaline technology. Siemens Energy stands for PEM. And NAPTA, which is originally an Italian company from Livorno, actually stands behind AEM water electrolysis. And Sunfire and other people sort of also try to establish and commercialize high temperature technologies. So we're working on the PEM a little bit to lower the iridium content on the anode. But today I'd like to talk a little bit about this emerging alkaline exchange membrane water electrolysis, where we work on both sides to actually make the anode catalyst that releases oxygen more efficient, and also on the cathode side where you release hydrogen. And you would like to replace this last bit amount of platinum, which is still used today in this technology. So electrolyzers and fuel cells suffer from so-called overpotentials. These are power losses, which basically results in inefficiencies. We have the letter eta in order to denote overpotentials. And a large portion of these overpotentials come from the oxygen evolution reactions in all of these electrolysis processes. And that's why we need to improve the catalysis on those catalysts. The same is true for fuel cells, just the other way. That you're actually seeing less voltage than you should because of these overvoltages. And the reason are the activation barriers of the individual elementary reactions. For example, here the 4-step 4-electron reduction of oxygen, which happens at the cathode of a fuel cell. So in order to address oxygen evolution in alkaline environments, we've been working on a class of inorganic materials that come from the great family of hydrotalcides. These are layered materials, as you can see, where you have edge-connected octahedra inside the layer, which are, the archetypical one would be pure nickel, which is then also doped, however, with a 3-valent metal, like iron, for example. And because of these ions, which are 3+, you have a positively charged brucide layer, which requires a kind of a counterbalance of negative anions in between the layers. So in between the layers, you have water and carbonate, for example, and in the layers, you have just nickel and iron and oxygens. And when you look on the right, you can see there are different hydrogen-oxygen ligands, the red balls. And of particular interest for oxygen evolution are the so-called mu2 hydroxyl bridges. This is the OH, which are bridging 2 metal atoms here, the 2 green balls, for example. In particular, also the oxygen bridges, which is bridging a green and a red ball, which would be an iron and a nickel atom, as we see shortly. So we can synthesize this in a silver thermal process. And we have synthesized a large variety of combinations. Hydrotalcides are so versatile materials. And as you can see on the left, they have their very characteristic patterns where you can actually read off their structural characteristics. You can actually see that these are sort of anisotropic platelet type materials where you can actually see the rhombohedral symmetry that you can recast in a hexagonal lattice. And when you actually then test the electrochemical ability, performance, activity, if you like, for the evolution of oxygen from water, this is shown on the left, where we plot the current density, which is a measure for the oxygen evolution as a function of the applied potential. You can see that these materials vary in their catalytic reactivity, and that basically a lot of the cobalt ones behave fairly good. You can see this in the red bars, better than the nickel-containing ones. But there's one combination which really stands out with a particularly high oxygen evolution reactivity, and that is the nickel-iron combination. And we wanted to find out what's so special about this nickel-iron layer double hydroxide. You also see that it performs much better than iridium oxide in an alkaline environment. This is not surprising. Iridium is really only the best catalyst in an acidic environment. And in particular, of course, we want to know what is the catalyst's structure under operating conditions. So what is this really active phase of the catalyst? And to understand that, you have to keep in mind that as we increase the potential, the first thing that we do is that we change the catalyst, because we inject positive charge holes into the lattice. And you can see it here when you compare the charge that we inject versus the catalytic oxygen molecules released. The blue line in both plots here denote the actual oxygen signal detected from a mass spectrometer, versus the red line is the actual voltammetry that shows you how much charge you have injected into the material. And for the nickel-iron LDH, you can see that you first start injecting a little charge, and the oxygen signal actually follows quite soon afterwards. So immediately, or as soon as you have injected charge, meaning redox charge, some metals change the redox state, you also see the evolution of oxygen. But for example, for cobalt iron, you have a very broad window where you first have to inject charge into the catalyst, you change the oxidation state of the cobalt, but you do not see any catalytic reaction yet. That only comes then later when you basically push cobalt from 3 into oxidation state 4. And the left side, this is basically where you have a resting phase. We call it the alpha phase. This is catalytically inactive. But then under OAR conditions on the right side, we say there is a gamma phase, or we call it the gamma phase, which is the catalytically active phase. And we would like to be able to know more about the structural characteristics of that phase. To study such a thing is basically you have an inactive phase, you have an active phase, and we're only interested here in the brown phase and not in the yellow phase. Yellow phase is well characterized. This is the hydrotoluene in its original state. In order to learn more about this, we need to apply so-called operanto techniques. And to illustrate what that is basically all the catalytic investigations of a catalyst before the catalysis and after the catalysis is like shadow. It's like a shadow from an object that we do not know. And shadows can be quite misleading, as you can see here, from this shadow artist. Obviously, the shadow is very obvious, but if you look at the real object, this is actually a piece of trash. This is a Japanese shadow artist that sort of, misguides your mind and your eye. But this is exactly what operando is about and why operando techniques are so useful. So the operando technique that I would like to use here is wide-angle X-ray scattering that provides us with structural characteristics of the active phase. And what we do is we follow the 003 reflection, the Bragg reflection, that is basically the distance between two layers. And we're following the 110, which is actually related to the distance of the metals in the layer. And we do this at the synchrotron. We have here an in situ cell where we put our catalyst. X-ray comes from the left and the detector is on the right. And when you do this, when you follow, for example, the 003 peak, and you apply positive potentials, you can see that you see at some point a shift of the Bragg reflection. It broadens also, and then when you lower the potential again, it sort of goes back. It's sort of reversible, so between alpha and gamma phase. You can now investigate, analyze with Rietveld, so full pattern analyses, and then you actually can extract lattice parameters, and you can see that the material starting at 1.5 volts is actually contracting from around 23.4 angstrom to 21.6 angstrom, which is corresponding, you can see the interlayer distance contraction in the catalytic active phase. We can do the same thing also for the intra-atomic distance between two metal layers, and we go from 3.11 to 2.83 angstroms. And we can even do more. We can also say what is the fraction of the catalyst of the alpha phase which is transforming into the gamma phase. This is basically going from the blue bar down to the gamma bar, so to the 1.6 volts bar. So you see that we're not able to actually transform everything of that phase into the gamma phase. And with this experimental data, once we had sort of gathered that, we went to our theoretical collaborators at Purdue University, and I would like to acknowledge Professor Jeff Greeley and Sen-Hua Tseng that we're closely collaborating over the past years on this topic. And what they did is basically they started with the alpha phase. This is the hydrotoluene phase that we all know. And they started with a reasonable sort of guess for the gamma phase. Usually people start with the gamma nickel oxyhydroxide phase. However, that phase is not really exactly what the actual phase here is. And what you can see here, this is a kind of a sum formula of the gamma phase. You have removed all the protons, complete deprotonation of the hydroxyls. And the metals should, in theory, go all to the oxidation state +4. However, nickel doesn't do that. There are 2 nickels that stay in +3, and that actually turns the layers from a positive into a negative charge. And that means that you need positive charges in between the layers to compensate. So what we concluded is that actually the anions in the transformation from alpha to gamma, the anions leave the interspace and cations are actually intercalated. In this case, sodium because we work in sodium, potassium because we work in potassium hydroxide. And then the model actually provides you with structural predictions, and when you look at the numbers are very close to what we measured. So that gives us additional confidence that these calculations sort of represent reality. You also see from the free energy diagram that at 1.5 volts, the gamma phase is more stable, so you expect the transformation from alpha to gamma. But the model can actually do more. The model now can also do and look at things that we cannot really look in experiment. They can actually look at the edge faces of the crystal and actually identify the active site, or potentially identify an active site. And this calculation, what they concluded is, when you go through the catalytic cycle from an hydroxyl, then you oxidize it to an oxo ligand, you stabilize the oxygen atom, so to speak, then you have the nucleophilic attack of an OH minus to form a peroxide, and then you go and release the oxygen molecule. In this cycle, you can see that a hybrid site, a kind of a bridged site between a nickel and an iron, is the energetically preferred active site. So nickel and iron basically share this hydroxyl active site where the OER process happens. And another observation was that when you have the stabilization of oxygen, when you go from OH to O, then iron is actually changing its redox state. And when you release oxygen from OOH to O2, then it's the nickel atom which is changing its redox state. So it looks as if iron is responsible for stabilizing the oxygen, the oxyl ligand, versus nickel is responsible for destabilizing the peroxide and releasing oxygen. So this hypothesis and this energy can also be plotted in a free energy staircase that you see on the left. You start from OH and you go up these 4 electron reactions all the way to released oxygen on the top. And the step that is energetically largest is the one that is sort of potential limiting. We call this the potential limiting step. And from this you can predict a theoretical overpotential for this material. And then that overpotential we can compare to the trends in the experimental overpotentials. And what you see here, the calculated trends correspond excellently with the experimental trends that we obtained from our experiment. So another sort of confirmation, or let's just say a piece of evidence that we may be on the right track with the gamma phase that we have identified. So, but there's something curious and something very interesting about these materials. When you now look at these various gamma phases that we have studied, and you look at the models, you see that there is always one metal that takes care of the oxygen stabilization, and the other metal which takes care of the release of oxygen, in a way a destabilization of the peroxide. And when you look which metal takes on which role, you find that whenever there's nickel involved, it's always the nickel which is releasing the peroxide into molecular oxygen. And if there's nothing else but nickel, nickel has to do both jobs, right? Like in the nickel oxyhydroxide. If you have a nickel iron, then iron is rather stabilizing the oxygen and lets nickel destabilize the peroxide. If you have cobalt iron, then iron is stabilizing the oxygen and cobalt is releasing the oxygen. And we believe that there is a kind of that this has some meaning, some bigger meaning. And you can basically illustrate the energetics of stabilizing oxygen, which is the upper bar, and releasing oxygen, which is the lower bar, also in terms of how close is a metal to the ideal case, to the ideal catalyst. The ideal catalyst is the dashed line, and as you can see on the very left, the purple bars, this is the pure nickel oxyhydroxide case. You can see that this material is very good at destabilizing peroxide, releasing oxygen, but it's very far from actually ideally stabilizing oxygen ligands. Yeah? But now, if you dope this purple with iron, you jump to the black lines, and on the black lines you can see that this material, or this combination of active sites, are a little less able to release oxygen, but it's much better in stabilizing oxygen ligands. And everything becomes more symmetric, and that in combination is actually better for the overall catalytic process. And this is why nickel iron is really a a much better catalyst than a pure nickel oxyhydroxide. And we even can draw, this is now a hypothesis, we can even draw to a concept from inorganic chemistry that some of you may be familiar with, which is called the so-called oxo wall. The oxo wall is a concept that there are the transition metals to the left of the oxo wall are able to stabilize high-valent oxygen ligands, in particular terminal oxygen ligands. But the metals, or the transition metal elements to the right of the oxo wall, they are not able to form stable oxo compounds, right? So this oxo wall comes from molecular chemistry, but I believe that there is a conceptual link to what we observe also here on the solids. And when you look, a good oxygen evolution catalyst typically contains one metal from the red block, from the destabilizing block, and one metal from the stabilizing block. The best combination seems to be nickel-iron. Cobalt-iron can do it also. But if you leave out an element from the left side, if you only work with pure nickel or with pure iron, you have terrible catalysts because you either cannot stabilize or you cannot destabilize the intermediates in the catalytic cycle. So to prove to you that this is not just all theory, we put our catalysts in a real alkaline exchange membrane electrolyzer. This is a funded project by the Federal Ministry for Science and Technology in collaboration with Siemens Energy. And what I showed you here are IR-corrected curves. I note this is IR-corrected because we only want to look at the catalysis. And what you see here is an alkaline exchange membrane electrolyzer that works with iridium and platinum from the literature, from Stephen Holdcroft at 50 and 60 degrees C. And you see a typical PEM, state-of-art PEM acid water electrolysis with 1.6 milligram iridium and a small amount of platinum on the cathode. And what you see is that our catalysts, completely iridium-free, nickel-iron LDH on one side, platinum on the cathode, I agree, is very competitive actually to the PEM water electrolysis. And we can go easily to 5 amps per square centimeter in these alkaline exchange membrane cells. And you can see that this additional overpotential now is maybe only 150 millivolts between acid and between alkaline. So this is a huge step forward actually to a completely iridium-free, high power and high efficiency water electrolysis technology. And finally, I'd like to close with a few comments on CO2 valorization. The CO2 reduction is a very interesting process. The CO2 molecules needs to be removed, right? And it can be chemically converted, electrochemically, to a number of interesting intermediates. The problem is that a large number of electrons are needed in order to generate things like ethanol, acetaldehyde, or propanol, or ethylene, 12 electrons. Yeah? This is a lot, and there's certainly then somewhere a step which has an unfavorable kinetics, and that makes the entire process very slow, and you see an enormous overpotential. So catalytic researchers everywhere in the world are now trying to identify better catalysts in order to convert the CO2 molecule electrochemically in any of these compounds. Our ambition is clear. We would like to provide a room temperature ambient pressure process which can compete with the respective fossil process. So the first one would be a kind of electrochemical reverse water gas shift, if you like, replacing steam reforming and basically removing hydrogen. Or in the case of ethylene, we would like to replace electrochemical ethylene production from catalytic cracking of naphtha into ethylene. And how do we do hydrocarbons in our sort of green hydrogen environment? You are probably familiar with the two most popular routes, where you start from power, water, you get hydrogen, green hydrogen, you mix it with CO2, and then you can make methanol as sort of a platform chemical, well-known process on copper-zinc formulations. It's a thermal process. And then there's a process called methanol to liquids, where you can make hydrocarbons, jet fuels, and everything for applications where neither hydrogen nor electricity can really power or provide the power which is needed. So this is currently a very popular route. Of course, that competes with a very classical route by Fischer and Tropsch, right? The person we talked about at the beginning. So you can use also your green hydrogen, mix it with CO2, put it in a reverse water gift reactor, then run it through a Fischer-Tropsch, and you also come to hydrocarbons. The problem with these process chains is that you are generating a large amount of water molecules in the thermocatalytic steps in the end. These are the two boxes called water. And this water is generated at high temperatures, and you have to heat up these water molecules to those operating temperatures, and it costs a lot of energy. So the question is, can we not find a more efficient alternative route towards electrochemical jet fuels, electrochemical diesel, or e-gasoline? And we're currently working on a process that we call EcoFuel, together with Siemens Energy, where we basically take power, water, but we also feed CO2 directly into the electrolyzer. And basically, out of this electrolyzer comes pure ethylene. Basically, we're skipping the C1 step, if you like, and we go directly to a C2 molecule. And importantly is that in the electrochemistry, we are separating off the oxygen atoms from the carbon atoms. So we generate water, but we generate the water at room temperature and ambient pressure. And then we come out of this electrolyzer with pure ethylene, and then we're applying a process, ethylene to liquids, which is just an oligomerization of ethylene into the hydrocarbons. This process is very old. There are patents out there from the 1970s and 1980s, but it has never been commercialized because we had no access to ethylene from something else than naphtha. So obviously, when you start from hydrocarbons to make ethylene, you don't need that process. But now we have new ways to form ethylene, electrochemical ways to form ethylene. And now this process may become actually quite interesting to have a very efficient route to e-jet fuels, to e-diesel, or to e-gasoline. Now, in order to show you progress, this is the process scheme in particular. We will capture CO2 from the air. We are responsible for turning this electrochemically into ethylene and propylene. Then we have to separate out hydrogen and CO. These are the two poisons in that process. Then we go into the thermal catalytic reactor, and out comes jet fuels and long-chain hydrocarbons. Now, our job is to make very efficiently ethylene from CO2 and water. And we do this in two separate cells that we sort of put in series. The first cell is only doing CO2 to carbon monoxide, a 2-electron reaction, very efficient. And the second cell then turns CO into ethylene. The advantage of this tandem cell is that you can choose individual operating conditions and individual pHs and individual catalysts. So in the first cell, we look for a very selective CO2 to CO catalyst, and in the second cell, then we turn CO into hydrocarbons. In the first cell, we do CO2 to CO on so-called single atom catalysts. These are metals which are coordinated by nitrogen atoms and embedded into graphene. So the advantage here is that we force the reactant onto this single site, and since hydrogen evolution is our competition, we don't want hydrogen evolution here, we also force the hydrogen atom on top of this single site atom, and that is less favorable than like hydrogen being in a 3-fold hollow metal site. And that is why we can achieve very high selectivities for CO on these catalysts. So we discovered this, or we described this for the first time in 2015, that active sites like this are very good for CO2 reduction, and that iron is very efficient early, and then later on makes actually hydrocarbons even, methane. But nickel actually turned out to be a very selective catalyst for CO alone. It doesn't make any hydrocarbons. And so we synthesize these single metal atoms from precursors. These can be MOFs, COFs, other polymers that we need to pyrolyze. And our reference catalysts are the porphyrins and the phthalocyanines. And you can see here some electron microscopy of these single nickel sites. You see them here in the dark field. And here in the eels, you can actually see that the close proximity of nitrogen atoms and the nickel atom in this material. And when we now test them in a real electrolyzer, this is our electrolyzer cell. we feed in humid CO2, and out comes a mixture, or out comes CO, actually also a little bit of CO2. And we plot the Faraday efficiency as a function of applied current density, and we compare this to a state-of-the-art silver denora electrode, which is sort of the state-of-the-art for CO2 reduction, also for oxygen reduction in the chloralkaline technology. You can see that our sort of single atom nickel catalysts that only contain about 1 weight% nickel in carbon are very competitive in terms of Faraday efficiency and Faraday and partial current density. And that is actually a nice result, and that gives us confidence that these single site catalysts may be a way to sort of circumvent all this very silver-rich electrodes. Now, since we never have a 100% conversion of the CO2 into CO, at 100% selectivity, we still have a mixture of CO and CO2 out of the first electrolyzer. So in reality, in the second electrolyzer, we're looking at a co-reduction of CO and CO2 to ethylene. And this is a very interesting topic in itself, because when we played around with the reduction of mixed feeds of CO and CO2, you can see that pure CO makes ethylene, pure CO makes ethylene, a little bit less because the solubility of CO in water is much less. But if you have mixtures of CO and CO2, you actually see an enhanced ethylene production. And we didn't quite understand that at first. But we then hypothesized that there should be 2 active sites on copper surfaces. We don't know what sites they are, but there should be, or we believe there's one side that has a higher affinity for CO and one side which has a higher affinity for CO2. And if these sites are in molecular proximity, then the CO, which forms from CO2, and the CO, which forms by just direct adsorption, is actually, or can form carbon-carbon bonds like ethylene. So you actually have 3 ways of forming ethylene. You can make ethylene from 2 A sites. That would be then 2 carbons coming from CO2. You could make ethylene from 2 carbons from CO. And you can make ethylene from a carbon coming from CO and 1 carbon coming from CO2. And in order to follow that process, we used isotope-labeled mixed feeds and a mass spectrometer. So we fed in 12 CO with 13 CO, 12 CO2 with 13 CO, and we detected the 3 types of ethylenes that are formed because of the 3 different masses. We have ethylene with a 13-13 mass, ethylene with a 12-12, and ethylene for a 13-12. And the 3 colors show you, as we change the potential and go back up, how the ethylene production changes of this respective ethylene. And the blue one is the one that you have the cross-coupling path, where you have 1 carbon from the CO and 1 carbon from CO2. And this cross-coupling path in our mind is actually what makes this process so extra ethylene efficient. So this extra ethylene comes from this cross-coupling of these 2 different sites. And calculations also, these are simple reaction diffusion. This is no DFT or so. Just reaction diffusion on the surface actually provides further support that we can reproduce. The CO, the red curve actually comes first because the kinetics from CO is quicker than from CO2. But the blue one, which is the cross-coupling path, is dominating and is providing this extra ethylene. So the rest is basically now we actually did it. We tried to couple 2 cells. Cell 1 is making CO, cell 2 is making ethylene, and these are 2 real electrolyzers just coupled together in the laboratory. And when you look at the Faraday efficiencies, left is the reference case when you feed CO2 directly in cell 2, so single cell. Right is the tandem case where you have a cell where you make CO2 into CO and then CO into ethylene. Note also that in the Faraday efficiency values on the right, the charge that you inject in cell 1 is already considered. It's already corrected for. And what you can see is then when you compare at equal current densities, let's say minus 700 milliamps, we have an advantage in terms of ethylene and other CO2 fuels. I selected now the 500, which is comparable to the 700 on the reference case. So in other words, we're more efficient, we're making more useful C2 plus products like ethylene, propanol, and ethanol in this tandem sort of device. And to show you again that we're going towards scaling up, this is the setup at Siemens Energy right now. They have now a scale up to 3,000 square centimeter CO electrolyzer cells. This is an intermediate sort of step with 100 square centimeter direct CO2 electrolyzers going to ethylene. And with this, I'm skipping a summary in the interest of time. I'd just like to acknowledge my collaborators, Brian Seeger, people from Denmark, Professor Jan Rossmeisel, with whom we do a lot of theory, Dr. Max Fleischer from Siemens, that we work on in the ecofuel process, Beatrice Roldan from the Fritz Haber Institute, people from the Microscopy Center, Ernst Ruska, and of course our theoreticians at Purdue University. And the funding comes from EU, the German Ministry, and the German Science Foundation. And last but not least, I'm very grateful to my team. I'm blessed to work with really gifted young scientists, in particular an Italian scientist, Fabio Dionigi, who did all this work on nickel iron LDH, and the people in red working on the CO2 reduction. With this, thank you very much for your attention.
Thank you very much, Professor Strasser. As you have seen from the program, there is no question just after the talk, or will be time at the end of the session to discuss. So now let's move to the second talk of this morning that will be delivered by Dr. Antonino Aricò. Dr. Aricò is the Research Director of Italian National Research Council, and he's based in Messina at CNR Institute of Advanced Energy Technologies. Dr. Aricò has received several appointments by Italian governments as well as by European Commission, and he's a representative, CNR representative in Challenge 8 of Mission Innovation, Renewable and Clean Hydrogen, and ERA Fuel Cell and Hydrogen. Dr. Aricò has been a coordinator and responsible of several projects, including European, national, bilateral, and project with the industry and co-funded contracts. And his interest is on renewable and clean hydrogen, and today he will talk on green hydrogen production and advanced membrane electrolysis technologies.
Good morning, everybody. I would like to thank the organizers for their kind invitation. It is really a pleasure for me to be here today to discuss our recent activities on green hydrogen production by advanced membrane electrolysis. My name is Antonino Aricò. I work at the Italian National Council of Research, and in particular I'm director of the Institute of Advanced Energy Technologies that is mainly located in Messina. So regarding electrolysis, as you know very well, this technology plays a central role for production of green hydrogen from renewable power sources. And this was well recognized by the European Commission in their hydrogen strategy. The hydrogen strategy was communicated in July 2020, and the main goal is the installation in Europe by 2030 of 40 gigawatt of electrolysis plant to produce green hydrogen inside Europe, inside the European Union, and another 40 gigawatt outside Europe using European technology. If you consider that at the moment the production is around 2 gigawatt per year, you may understand that there is a long way to go in order to reach such targets. This means that we need to develop advanced electrolysis technologies. Of course, there are several strategies, hydrogen strategies in the member states of the European Union and outside the European Union. And also the Italian Recovery Fund, that is the PNRR, has individuated electrolysis as one of the main technology to produce green hydrogen. As was already discussed by Professor Strasser, there are several electrolysis technologies, 4 main electrolysis technologies. Today I will essentially discuss about PEM electrolysis and AM electrolysis. However, at the moment, the 2 consolidated electrolysis technologies are liquid alkaline and PEM electrolysis. And there are advantages and disadvantages of each of these technologies. As an example, for the liquid alkaline, these are based on a zircon, a thick zircon separator. And of course, these technology cannot reach high operating current densities. Moreover, there are issues regarding hydrogen purity, and we need some purification efforts in order to get pure hydrogen. And also, these systems are limited in terms of operating at high pressure. On the contrary, PEM electrolysis technology can achieve extremely high current densities, high energy efficiency, and high hydrogen purity, and also can operate at high differential pressure. However, the main difference between PEM and alkaline is that in alkaline environment we can get rid of precious metals, and we can use steel instead of titanium bipolar plates. So you may understand there are advantages and disadvantages. So at the moment both technologies are developed and can contribute to reach the challenging goals of the European Commission. Regarding PEM electrolysis, we generally identify this technology as a zero gap cell, and as you can see at the SEM microscopy of an MEA, a membrane electrode assembly, this is after several thousand hours of operation, you can see the catalyst sticking the membrane. This is the concept of zero gap cell. And of course the dense membrane can reduce the hydrogen crossover. That is a relevant aspect I will discuss more in detail in the next slides. As also shown by Professor Strasser, polarization curves are essentially used to determine the performance of the PEM electrolysis cell, and according to the operating voltage we can understand the voltage efficiency and the operating current density. It is extremely important to operate at high current density because of course we increase the hydrogen production rate and we decrease linearly according to the Faraday law the capital costs. So it is important operating at very high current densities in order to decrease capital costs, especially in PEM electrolysis where we use precious metals. But this is not sufficient. We need to determine Faradaic efficiency because it is really necessary to understand how much is the produced hydrogen, how much is the hydrogen lost in the crossover mechanism, and also the purity of hydrogen is also a relevant aspect. So the product of Faradaic efficiency and voltage efficiency provide the overall energy efficiency. Of course, the performance and efficiency of these systems are essentially related to different characteristics. As an example, the catalyst loading. that is an indication of the number of active sites, and also the operating temperature. If you increase the operating temperature, of course, you decrease the activation energy. And essentially, we use AC impedance spectroscopy as an in situ diagnostic in order to understand rate determining steps. In particular, using AC impedance spectroscopy, we can distinguish between the contribution from the membrane, from the ionic conductivity of the membrane, and the contribution from the electrodes, series resistance and polarization resistance. And if you operate such PEM electrolysis systems at high current density or at high voltage, 1.8 volts, corresponding to about 80% efficiency versus the high heating value of hydrogen, you can see that at high temperatures, but also at low temperatures, provided that you operate at high current densities, the membrane is dominating the polarization behavior. So it is really important to develop advanced membranes in order to reach high performance, high efficiency under practical operating conditions. We have started working on electrolysis, let's say, some decades ago, and one of the first approach was related to replacing conventional Nephio membranes with new advanced short side chain Aquivium membranes developed by Solvay Specialty Polymers in Italy, in Bollate. And you can see that the main differences are regarding the equivalent weight. That means lower equivalent weight, higher conductivity, higher ion conductivity for Solvay membranes, but also better crystalline properties. That means lower crossover. And it is also in the higher glass transition temperature. That means operating at higher temperatures. Moreover, another important aspect that we have addressed was replacing amorphous nanosized iridium oxide catalysts with crystalline iridium ruthenium oxide electrocatalysts with larger crystallized size but much better stability and intrinsic activity. And if you have a look to this EDX profile of these iridium ruthenium oxide particles, you can see that iridium is mainly located on the surface of the particle, and ruthenium is in the bulk of the particle. And this provides stability to these electrocatalysts, but also it is important the crystallized sites, because this is related to the number of active sites. And this is for the anode. Iridium ruthenium oxide is used for the anode, for the oxygen evolution. For the hydrogen evolution in this field, we use a conventional platinum on carbon catalyst. Regarding the comparison between Aquivium and Nephio, you can clearly see from the impedance spectroscopy that in the case of Aquivium there is a lower series resistance associated to the higher conductivity, but also better interface with the electrodes, with the catalysts, and this is related to a smaller polarization resistance. And these advanced materials have been demonstrated in FP7 EU project ElectroIPEM that I had the honor to coordinate, where we have validated, assessed such materials in practical operating under real life operating conditions in a practical stack fed by the power profile from a micro wind turbine, and also demonstrated the stability over time. In a subsequent project that also I had the honor to coordinate, HPAM to gas, dealing with power to gas, European project, we have addressed the more challenging goals like operating at high current density, high energy efficiency, and also good durability. By starting from these functional materials that were advanced electrocatalysts and membranes and short side chain membranes combined into an MEA that is assembling between catalyst and membrane and installed into stacks and tested in a system. And in this project, we have learned that the degradation rate is essentially related to the turnover frequency. That means it's related to the operating current density and inversely related to the catalyst loading. That means if we use a low catalyst loading, of course there is an increase of degradation rate because the catalyst is more stressed to operate at high current density for the oxygen evolution reaction. And this was demonstrated by carrying out durability tests of 1,000 hours at different current density, different catalyst loadings. And it seems that this is not related to a change in morphology of the anode or the cathode catalyst or a change in surface area, in electrochemical active surface area. It is more related to the modification of the electronic properties as essentially determined by XPS analysis. There is a curious, let's say unusual, shift to lower binding energies for the iridium and ruthenium peaks, photoelectron lines, that is associated to some extraction of oxygen at high operating current densities. And of course it is unusual because the catalyst operates in an oxidizing environment, but can be also common in other chemical processes regarding these electrocatalysts. Regarding the membranes, of course, the first approach was with extruded membranes, but also recast membranes show interesting performances. It is important using thin membranes because we can achieve a lower ohmic drop and thus operate at high efficiency at high current density. However, if you can see from this plot, at low operating current densities, you have a significant concentration of hydrogen in the oxygen stream at the anode, and we can reach the flammability limit, that is 4% hydrogen in oxygen. And this means that, of course, we are limited in terms of partial load operation. And since we need to address flexibility and dynamic operation, of course, this is an issue. We have tried to address this issue by developing a recombination catalyst. But before discussing this, I would like also to mention the comparison between reinforced membrane and extruded membranes. Reinforced membranes is a new approach that is carried out in the field of electrolysis, where you have in this case a PTFE reinforcement in between two dense aqueous layers that are essential to avoid hydrogen crossover and to increase performance. And using these membranes, we have low gas crossover, and at the same time we can reach extremely high current densities, something like 10 ampere square centimeter at practical cell voltages. Of course, durability is an important aspect because performance without durability is not much relevant for practical applications. And we have assessed these membranes in durability test of 3,000 hours, 4,000 hours, that are essentially something like 6 months operation in the laboratory. Of course, there are some startup shutdown cycles in between that can be recognized here in these plots. What is really interesting, there is a very good stability with time, and after operation, by doing some in situ diagnostic, essentially cyclic voltammetry, there is a minimal change in electrochemical active surface area for both anode and cathode. Now, regarding the hydrogen crossover issue, of course, it is necessary to manage this hydrogen crossover by using a recombination catalyst at the anode. We have used essentially platinum cobalt, a dual layer, platinum cobalt and iridium ruthenium oxide, or a mixed catalyst. And by using this let's say, a recombination catalyst, we have been able to reduce the hydrogen content in the oxygen stream. And this is essential to avoid safety issues at low operating current densities. Also, the durability of the recombination catalyst based on MEA is quite good. Of course, there are some reversible losses that are typical of the system, but still performance is even better than a bare MEA. All these developments have been validated in practical devices. This is the 200 kilowatt stack that was developed by our colleagues at ITM Power in the framework of the HPEM2Gas project. You can see this is an innovative stack concept without tie rods. It is based on a hydraulic compression, providing homogeneous compression. And this 200 kilowatt stack was demonstrated in Emden in northwest Germany, where there is a surplus of renewable energy, especially from wind power. And this is some pictures from the inauguration of the electrolysis plant, where you can see the container. The container includes the 200 kilowatt stack. Of course, you need a balance of plant around the stack, and they produced the hydrogen. The container, the electrolysis container was fed by wind power, and the produced hydrogen was injected into the gas grid. This is, of course, one of the main applications of electrolysis. Now, just a few words about anion exchange membrane electrolysis. As already discussed by Professor Strasser, the main advantage of this technology is that it is a zero-gap cell, so membrane electrodes sticking to the membrane, but this is an alkaline environment, so we don't need precious metal electrocatalysts. Also, we don't need titanium bipolar plates. So the technology is extremely cheap, and also we can overcome the issues of the alkaline electrolysis. However, there are several phenomena to take into account. Different ion conductivity. Of course, hydroxide mobility is not the same, is not as much as proton mobility. And of course, there are aspects related to diffusion layers, stability of the membrane, operating temperature, and so on. And these aspects are addressed because it is currently running the Anione project. This is Horizon 2020 project that is still running. We have 1 year until the end. And especially in this technology, we have replaced all precious metals with non-critical raw materials. Not only non-precious metals, but we have also avoided the cobalt. The anion catalyst is very similar to what was already presented by Professor Strasser, is nickel iron oxide. Indeed, it is a layered double hydroxide. Regarding the cathode catalyst, at the moment our best performance is with the nickel molybdenum alloy on carbon, and also this system has shown good durability in a practical device. And this is a comparison very similar to what was already presented by Professor Strasser. Is a comparison between AM and PEM, but in this case, this is including ohmic drop. This is the original performance without, let's say, IR correction. So we have the contribution of the electrodes and membrane, and at 2 ampere square centimeter, at the moment we have something like 300 millivolts gap between performance under AM electrolysis and performance under PEM electrolysis. And if you look to the in situ AC impedance spectroscopy, indeed this gap is essentially due to the electrodes, to the electrocatalysts. So there is really a long way to go in order to achieve the similar performance of PEM electrolysis. But we have a real advantage. No non-precious metals, no critical raw materials. We have essentially nickel-based, nickel iron, nickel molybdenum electrocatalyst, hydrocarbon membranes, no fluorine chemistry, no titanium bipolar plates, only steel. So this is really the future. And this is the new challenge, is the new project that was recently approved by the European Commission in the Clean Hydrogen Partnership, by the Clean Hydrogen Partnership. This is the call 2022, and the new project is called Advanced PEM, is still dealing with PEM, but addressing the challenge of operation at extremely high pressure, 200 bar. So we lose a lot of energy in downstream hydrogen compression after the electrolysis system. So this is the new frontier of PEM electrolysis. With this, I have concluded. I would like to acknowledge all funding from the European Commission in several projects, from FP7 to H2020 and now to Horizon Europe, and all of you for your kind attention. Thank you.
Thank you, Dr. Arico. Let's now move to the third lecture of this morning, of this session, that will be given by Dr. Perego. Dr. Perego has got his degree at Politecnico of Milan, and he's at De Nora company since over 18 years. Until 2022, Dr. Perego has been manager in the research and development sector for developing electrolyzer or component of electrolyzer, which is the main business of De Nora company. Since last year, he is a technology manager for energy transition technology, a sector that has been created for better addressing the effort of the company in really bringing hydrogen technologies for serving societal needs. So now I give the floor to Dr. Perego, that will talk of role of water electrolysis in energy transition.
Thank you very much. So, already said, my name is Michele Perego, and I'm here representing the company I work for. It is Industrie De Nora. And I don't know if everybody of you knows Industrie De Nora. De Nora is let's say, worldwide leader in supplying electrodes for many electrochemical industrial processes. We have been defined as a kind of pocket-sized multinational, in the sense that we are not as big as a corporation. We are 1,700 people worldwide, but we are worldwide present. So we have production facilities in US, in South America, in Germany, in India, in China, in Japan. And we are present in all those places as a consequence of our of our history. And it's a bit it's a consequence of our history and how we grow along the year. And most important, it's a consequence of a strategic decision to be present and close to our strategic markets and customers. The history of De Nora has been, I would say, a rich of events in the sense of merging, acquisition, partnership, joint ventures. And you can see here with this timeline First of all, we were funded, De Nora was funded in 1923, and next year we will turn 100. So let me say, Professor Strasser mentioned before Casale, and the good thing is that Casale was not alone back in time let's say, in playing the electrochemistry or industrial electrochemistry. So the company was founded in 1923 by Oronzi De Nora, an Italian engineer. And still nowadays, the company is first of all Italian, so the headquarters is in Milano, and the president is the nephew of the founder, Mr. Federico. No, okay, I can also keep. Okay, thank you. Yeah, but it works. Okay. Thank you. So the president is now Federico De Nora, the nephew of the founder. Okay, it's difficult. Recently, we accepted some minority investment from the outside, from Blackstone. But what is important is that from 2021, these minority investment are coming from a solid industrial Italian partner that is NAM. As you can see here. First of all, we grew a lot in what for us was our core business, is chlor-alkali. Then we decided to expand our activities into water treatment arena. And more recently, we are really focusing on energy transition application. Okay, one moment. Okay. Let's say that talking about our mission, you see, green technologies for value creation. Now everybody is talking about being green. What I can say is that De Nora has been always green by definition, because all our efforts in developing better products for electrochemical application means providing products giving lower power consumptions, and that is green by definition. So, as a company, we serve different markets, and we are structured with different business divisions. The first one is called Electro Technologies, and includes what for us is our core business. It's chlor-alkali. Not only chlor-alkali, we have also customer in the electronics segments, in the mining sector. We have a second business division, the one that I mentioned before, is the Water Technologies division, providing solution for water and wastewater treatment, being it municipal, industrial, power, and marine. And now, let's say we are building a third leg in the energy transition with a special. Does it work? Yep. Okay. With a special focus on hydrogen production, but I can say without completely neglecting other sector in the hydrogen value chain, like hydrogen storage and transportation or fuel cells. We will see later more details about the technologies we can provide in this segment. So, as I was saying before, De Nora is known mainly as a coating company, so a company providing coatings and electrodes for various electrochemical applications. It is true, we develop and provide anodes and cathodes for instance, chlor-alkali, other electrochemical processes like the electrolysis of hydrochloric acid. We provide anodes for electrowinning of non-ferrous metal like copper, nickel, or cobalt. We provide anodes for the electroplating of printed circuit boards. But it's important to say that we do not only produce electrodes, but we also manufacture cells in our production facilities. So the cells composing electrolyzer. And when we move to water technologies, our approach to the market is a bit different in the sense that we provide not only electrodes but really plug-and-play solutions, skid-mounted for water treatment. Not only electrochemical solution like electrochlorination, but besides this we added other technologies like disinfection, filtration to be able to give to our customer more comprehensive solution. And lastly, as I was saying before, we are building our product portfolio in the energy transition, and we will see more details later on. Okay, why energy transition for us, and why green hydrogen production? Obviously, we can see in both sides, like a top-down or bottom-up. What I mean is that for us, the green hydrogen production technologies is the natural evolution of our traditional electrode technology business. We could see and identify a lot of similarities between chloralkali, for instance, and alkaline water electrolysis, and we could see a good overlapping on competencies, of existing competencies, both in catalyst and electrode development, but also in the electrolyzer development. And so for us was a natural way to enter this new arena. On the other side, it's clear the decarbonization is required, and the transition is something that is happening, and you can see that the global hydrogen demand is really impressive, and we know that we agree that this hydrogen needs to be green. Okay, we now even especially after the presentation given before, we everybody knows what is green hydrogen, what is electrolysis, how is powered by a renewable source of energy. We are traveling, let's say, or traveling this journey into energy transition not alone, but with partners. And the partnership that we like to highlight here is the joint venture that we have with the ThyssenKrupp. It is called Nucera. So it is a joint venture that is 1/3 De Nora, and the balance is ThyssenKrupp. This joint venture recently changed its name, is Nucera, but is older than the name, because it started in the late 90s as Udenora, a joint venture between De Nora and the engineering company or division of ThyssenKrupp that was called Ude, and the focus at the time was only chloralkali. This joint venture grew in the years and changed its name in ThyssenKrupp Ude Chlorine Engineer, and more recently become Nucera. I can say that De Nora and ThyssenKrupp can complement each other very well. ThyssenKrupp brings into the joint venture its engineering expertise, its ability to provide and sell plants on EPC basis, so engineering, procurement and constructions. On top of it, ThyssenKrupp can ensure a smooth integration with downstream processes, because ThyssenKrupp has also the possibility to supply on EPC base other technologies, other plants like green ammonia or other green chemicals plant. On the other side, we as De Nora, we provide our technology expertise in the joint venture. So we provided to the joint venture our electrodes. We share with ThyssenKrupp R&D programs, and we are also the manufacturing hub of their electrochemical cells. And this is true for the core business application chloralkali, but it is also true for the alkali water electrolysis plants. let's say that as De Nora, we are really convinced that we can support the energy transition towards a larger use of green hydrogen thanks to our expertise in electrochemistry, just to quote the words from our CEO, Paolo Della. And the moment for this transition is now. You can see in this graph the announced green hydrogen project. This graph is not, this map is not even updated. Now the number of projects, okay, you cannot see the number here, but believe me, it's more than 600. And what is good is that the number of projects is increasing, but also the size of the announced project is increasing. Is particularly interesting the number of projects here already at gigawatt scale. One comment is that those are announced projects, and the percentage of projects that are in their execution phase is much smaller than this, but we are proud to say that we are already engaged in some of those projects being executed. So, going back to what De Nora does for those kind of application. So we provide electrodes for alkaline water electrolysis, anodes, cathodes, but on top of it, I would say that we can provide components to ensure the better integration of our electrodes into existing stack technology. Professor Aricò mentioned before the zero gap concept, and also in alkaline water electrolysis, the zero gap concept is something that is practiced, and obviously electrodes needs to be properly installed into existing stack technology in order to work, to exploit, let's say, the most out of the zero gap concept. And that's what we do and what we can do on our customer, let's say, stack technology. We produce cells for alkaline water electrolysis. We have in our portfolio electrodes for fuel cell, so gas diffusion electrodes. We have a lot of R&D projects ongoing. We are developing electrolyzer system, small capacity, containerized, kind of plug-and-play solution, so not overlapping with the mission of the joint venture I mentioned before, Nucera, that is targeting large-scale installation plants. We are, you are aware, we are concentrating a lot on alkaline water electrolysis, but we are not neglecting the other technologies. We have ongoing projects on AEM, on PEM, on liquid organic hydrogen carrier, direct CO2 reduction, so all topics that have been mentioned before. Now let's spend a few words why we think that De Nora can play a role here. In this graph, you can see the dark blue lines, let's say anode over potential and cathode over potential. We learned from the presentation before the difference, the distance between these two lines is basically cell voltage, and cell voltage can be directly translated into specific energy consumption, so the kilowatt hours per kilograms of hydrogen produced. Thanks to the use of activated electrodes, the potential for oxygen evolution and for hydrogen evolution can be greatly reduced, thus lowering the cell voltage and the energy consumption. And this has an effect, I would say, on not only on power consumption, but also on the capex. That is other important component of the total cost of ownership of the produced hydrogen. That's because by bringing down the cell voltage, we can unlock the operation at high current density. And operating at higher current density means obviously more compact installation, more compact electrolyzer, so higher specific hydrogen production. And so decrease in the capex portion of the total cost of ownership. On top of it, we are aware that also lifetime stability is important because it will affect the third component of the total cost of ownership, that is the OPEX, so the maintenance cost, and so those performance must be kept stable as much as possible along the operational lifetime of the electrolyzer. The same concept better translated into this graph where we can show the difference between the traditional old-style alkaline water electrolysis, the blue lines and the blue area, the blue region of the graph, compared to the enhanced alkaline water electrolysis. As I was saying before, thanks to the introduction of advanced components like electrodes, but not only electrodes, also diaphragm can play a role, we can shift to lower power consumption, higher hydrogen production, specific hydrogen production, does as an overall effect to lower total cost of ownership of hydrogen. As a result, we have already projects in execution phase. So, as a result of what I'm saying, of the ability that we had to enhance the technology, we had a project in their execution phase. Some of these are in Europe, some are in US, some in South America. Obviously, the most important project that I will mention here is a NEOM project in Saudi Arabia, where the overall capacity is already at a gigawatt scale, so 2 gigawatt of hydrogen production. And this slide for us is particularly important, not only because of the project itself, but because we can say that obviously production capacity is required to follow this kind of project. And De Nora already has, with all its production facility, the production capacity to produce electrode and cell for those kind of projects already at gigawatt scale. Obviously, the demand will increase over the years, and that's why we are also increasing, or we have, let's say, plans to increase the capacity of our existing production sites. On top of it, we are going to build an Italian gigafactory, so roughly 2 gigawatt capacity, manufacturing stacks, system and components for water electrolysis and fuel cell. This will be done in cooperation with SNAM, and it will be funded by the European Union because our project was selected in the frame of the important project of common European interest. That's all for me. Thank you very much.
Let's thank Dr. Perego as well as all the speakers of this first part of first session. And now we have a coffee break. We'll meet back here in 20 minutes. The coffee break is available at -1 floor, so 2 floors down, in the Laguna room. So thank you. Thanks a lot. Welcome back. Welcome back to the session. I think it's time to start. I think it's working. Okay. Okay, let's wait that the attendees take seat, and then move to the second part of the hydrogen production session, the first session of this fifth Avogadro Colloquia. And I would like to remind before starting that a discussion session is expected to take place at the end of this morning session. So keep your questions and the comments for this later session. Now I will start with the second part with introducing Professor Stefano Agnoli. Professor Stefano Agnoli is Associate Professor of Chemical Science Department at University of Padova, here in Italy. He got his degree in Material Science in 2002 at University of Padova, and later in 2006 his European PhD. He was working as a postdoc at Brookhaven National Lab, where he joined the catalysis group of Dr. Rodriguez and studied the real and model system based on Syria and their application in catalytic production of hydrogen. His activities involves study of model and real system for catalytic application, and his research interests expand towards complex mixed oxide systems, new two-dimensional materials, including graphene-based material and transition metal dechalcogenides, and electrocatalytic process. I will now give the floor to Professor Agnoli that will talk on what we can learn from watching atoms during the hydrogen evolution reaction. Please.
Okay, thank you very much. Okay, so thank you very much for the kind introduction, and I would like also to thank Lydia and Elio for the invitation to speak at this very nice conference that gives me the opportunity to present some of the results that we obtained in our group about a new technique based on electrochemical STM that can be used to look at electrochemical reactions in operando condition. So a lot of speakers have already stressed the importance of the hydrogen economy, so I will be very brief. Essentially, the hydrogen economy wants to use renewable energy sources in order to give electricity and also store energy in the chemical bonds of a suitable energy vector, and the best one seems to be hydrogen. And then the idea is also to use this hydrogen for energy purposes, for example, to use it as a fuel, but also to convert it back to electricity. So in order to establish this virtuous cycle between chemistry and energy, we need very, very efficient devices like electrolyzers for the production of hydrogen and fuel cells to convert back hydrogen into electricity. And so this means that we really need to develop very efficient materials and materials that are sustainable, cheap, and very abundant, so we can really make real this ecological transition, and we made it affordable for everybody. So in this talk, I will give you a short survey about a new technique that we developed at the University of Padua that can be really a game changer in this context, because it's a technique that can accelerate the discovery of new materials, of new electrocatalysts, and can also unravel a lot of fundamental processes during electrocatalysis. So in order to demonstrate that, I will present you two case studies, and in particular the study of the hydrogen evolution reaction on two quite interesting catalytic systems, like thin films of molybdenum disulfide and single atom catalyst of iron supported on graphene. Both these catalytic systems are quite interesting because they have the potential to go beyond platinum, and all these elements are available in large quantity in nature and are also very cheap. So this study really can provide new practical materials for electrolyzer. So you look here, the main instrument of my talk that looks really not that nice, look a bit old, is not as shiny and showy like could be transmission electron microscopy, which is the competitor in the field of microscopy. TEM is the only one technique that can give you the same atomic resolution, but I want to convince you at the end of this talk that this kind of ugly duckling is actually much better than TEM, because this instrument can be used in operando condition. Just before, Professor Strasser just showed you that you can be mistaken by a shadow, and this instrument can allow you to look at the real thing in operando condition. Actually, the electrochemical STM can be used to look at what's happening on a 3-electrode cell on the surface of the working electrode. So in this case, we really have the real deal, something that is totally not affordable by TM, but in this case, we can still have the exceptional atomic resolution of advanced microscopy. So to build a bit of suspense, I want to go back at the beginning of STM and to one of the first work by the Nobel laureate Gerd Binnig, who already in '86, he spotted some noise in his STM images. But he recognized that this noise was not just an artifact or a random event, but was actually the signature of a dynamical process. So actually in this paper, he demonstrated that the spikes that he was observing on the surface of nickel were due to the movement of oxygen atoms on the surface. So we later on, after 30 years, the same concept was also taken back by Professor Bondarenka at the TU Munich, who actually applied the same concept to electrochemistry and recognized that the noise that you can sometimes observe also during electrochemical STM in the tunneling current could be due to the fact that in between the tip of the STM and the surface, it could happen electrochemical reaction. So you have protons that became hydrogen, and so you have oscillation of the electrostatic potential. And this creates some perturbation on the electron that tunnel from the surface to the tip. So the idea was that the noise can be associated to a catalytic current. So there is a direct correlation between noise in the tunneling current as a production of a catalytic current. So right now, through the tunneling current, we can look at the catalytic current. And this is really very interesting because it demonstrated that on analyzing the platinum-11 surface. So platinum is a very good catalyst for the HER, and he demonstrated that when he was applying a negative bias to the platinum surface in a potential window where the HER could take place, he was observing on the step edges that are the active sites for this reaction a lot of spikes because a reaction was happening there. And when it was switching back the potential into the AA region at much positive potential, where the HER doesn't happen, the surface was becoming again flat. So this was a good demonstration that the noise can be associated to an electrochemical reaction. I want just to show you that he was able just to have a limited resolution. You see, just in the order of 1-2 nanometer. And so we took the cue from here. Actually, at the beginning, we were a bit skeptical about that. When you deal with noise, you never know when the noise is coming from. So we decided to test it on a different system that we studied in the past, together with Matthias Batzil from the University of South Florida. So Matthias produced these thin layers of molybdenum diselenide supported on graphene that has some special features that are these line defects that are called metallic twin boundaries. Metallic because differently from standard molybdenum disulfide on the, that can be grown on graphene, these line defects are metallic. This is quite obvious from STM images, and you can see here these very intense lines that are these domain boundaries and are very corrugated because they have a special electronic structure. So we investigated this material as a catalyst for the HER, and we obtained very nice results. And essentially studying different materials, different prepared, we observed that there was a direct correlation between the number of these defects and the catalytic activity. So our idea was that, okay, these line defects must be very, very active. However, we decided to go a bit deeper into this topic, and we used electrochemical STM. So here is what we saw. So this is the CV of the system. You can see a decent HER activity. And this one is the image of the catalyst in the AA region at this electrochemical potential. And you can see that we could observe very nicely, even if we are in the presence of the electrolyte, atomic resolution both on the basal plane. We could even recognize the single selenium atoms and even point effect like selenium vacancies. And of course, we could observe these very straight lines that are the metallic twin boundaries. Then we said, can we do a Bandarenka experiment like changing the potential and see what happens? That is what we did, and in this image you can see the previous image rendered as a 3D plot. In this inset you can see the value of the electrochemical potential during our experiment, and you can see what happens. So when we move from the double layer to catalytic condition, you see the surface gets very noisy and becomes flat again when we go back to the double layer, and then we go back to catalytic condition. You can see, for example, here it's like it's bubbling. It's really like we are observing a lot of noise. The surface becomes totally fuzzy. So actually, Bandarenka was totally right, but how can we make this quantitative? Our idea was we work a bit on how to make quantitative the noise, because I mean you cannot say that the surface gets just noisy. You have to provide numbers. So we used a concept that is tracing back to surface metrology, that is surface roughness, and we applied to our tunneling current. And we defined this new quantity that we called current roughness, that is essentially a standard deviation of the instantaneous values of the current, where we take as a reference value the value of the tunneling current in the feedback loop of STM. We are using STM at constant current, in constant current mode. So I don't go through the math of all these. It took us a while to find the correct normalization to be independent on the experimental condition, but eventually we were able to obtain some analytical description of the noise, which allow us to be quantitative, to analyze quantitatively the noise and relate the noise to the catalytic current. And you can see that when we plot this quantity as a function of the electrochemical potential, we have a curve that is very similar to a linear sweep voltammetry. The idea at the very base of this method is that the catalytic current is a first-order perturbation of the tunneling current. So if you look at the tunneling current, you're actually measuring the catalytic current. And you measure the tunneling current with subatomic precision. So now we can do electrochemistry at atomic scale precision. And these are the results. You can see here when we plot the current roughness as a function of the electrochemical potential, you can see that we are able to identify some hot spots. So in these hot spots, these allow us to see where are the sites of enhanced chemical activity. And so we were able to refine our first idea that the metallic twin boundaries were very active. You can see here a couple of images, and here the full potentiodynamic scan, and the different curves relate to different places on the surface. And you can see that already at almost zero over potential, we see that the vertex one, that is these sites are formed by the intersection of two metallic twin boundaries, starts to have some noise, and then we have the vertex 2, that is the crossing of 3, and also the selenium vacancy. At higher of a potential, we can see the metallic twin boundary. So our first idea was kind of correct, but not correct at the nano level. It's not per se the metallic twin boundaries that is active. It's active, its combination, its intersection with other MTB. And here you can see, on the other hand, the scarce activity of the basal plane. So this was what we deduced experimentally, and we called on theory in order to have a confirmation of that. So we asked Arkady Krashenikov from Aalto University to calculate for us the hydrogen absorption energy on all these different sites. And these are the results. And then we plot the results of the hydrogen absorption energy, that is the best descriptor for the hydrogen evolution reaction, compared to the onset potential that we determined by our noise analysis. And you can see that the data are in a straight line. So there is a perfect agreement between theory and our experimental method. And incidentally, I want to show you that these sites that we found are indeed very active. So you can see that they compare very nicely with the best catalyst based on TMDC that we could find in the literature. Okay, we were very happy, but this was just the first example, so it could have been a coincidence. So we decided to investigate a different system that is graphene layer supported on different metal interfaces. Actually, in the literature, you can find a lot of paper that claims that graphene, which is totally not active for the hydrogen evolution reaction, can indeed induce a high activity when it's supported on a metal. The metal graphene interface seems to be very active. So we tried that with platinum, which is the best catalyst for the HER, and the results were bad. You see the red curve. We increased the overpotential. However, if we use iron and we create an interface, a direct interface between graphene and iron, we obtain the same activity as platinum. So, and this is a very notable results because iron is much cheaper than platinum, so you really gain a lot. So we try to investigate also this system, so a layer of graphene that is covering an iron surface with electrochemical STM. Also, these one are all measured in operando condition. So we were able to identify a lot of single atom defects. So you can see here the pattern, hexagonal pattern of graphene, and on this zoom in, you can see that some defects are formed. Essentially in graphene, there are vacancies, double vacancies, 3 vacancy or cluster of 6 vacancies, and in these vacancy pockets, single atom of iron can be immobilized. So you can see, for example, 1 atom of iron immobilized in a double vacancy, and here you can see 3 atoms of iron aligned within a 6 vacancy pocket. The identification of these defects was performed by DFT calculations of the STM images. So we look at these very interesting surface where we can find a lot of point defects. We can see also a step edge and the platinum interface, graphene interface, and the iron graphene interface. And again, we measured STM in operando condition, and also in this case you can see here the value of the electrochemical potential, and here what happens on the surface. So here you can see a zoom in on this defect that is made up by 1 atom of iron trapped into a 4 vacancy of carbon. You can see that when the potential decreases, when we reach to catalytic condition, you will see that here we will observe a lot of spikes, a lot of noise, you see, meaning that this is a center for the electrochemical activity. The same happens also on all the other single atom catalysts and also on the step edge. So we were able to obtain once again this current roughness plot as a function of the electrochemical potential. Again, we asked to some theoretician, to Cristina Di Valentin from the University of Milano Bicocca, to calculate for us the hydrogen absorption energy on all these defects. And these are the results. I just want to stress how good is the hydrogen absorption energy on the single atom catalyst. So if, according to the Sabatier principle, the best electrocatalyst should have a 0 absorption energy, and here we are very, very, very close. Once again, we plot the theoretical results, so the value of the Gibbs free energy absorption of hydrogen versus the electrochemical potential, and once again we obtain a perfect correlation with our experimental data. So I hope that I convinced you that we have a very nice technique based on electrochemical STM that can help you to really look at electrochemical reaction even on a single atom. This is something that is not available by any other technique. If you have, in general, if you have a microscopy, you need to use, for example, like TM, electrons, and you cannot use it in electrochemical condition. On the other hand, if you want to understand the structure by other spectroscopic means, in that case, we don't have atomic resolution. You have technique very nice like X-ray absorption spectroscopy. You can look at atoms, but you don't have atomic resolution. So this is the perfect technique because you have evaluation of the catalytic activity, atomic resolution, and possibility to perform your study with a real deal, with real operando condition. So I want to thank my group that made possible these studies, and in particular Marco Lunardun, our PhD, and our postdoc Tomasz Kosmala, and all the other people from University of Milano Bicocca, Aalto University, and South Florida who helped us in this project. And also the funding source from the University of Padua, and the EU, and also the Italian Ministry of Education. And I want to thank you for your attention.
I want to thank Professor Agnoli for the talk, and now it's a pleasure for me to introduce Professor Pacchioni. Professor Pacchioni is Professor of Solid State Chemistry at University of Milano Bicocca, and he studied in University of Milano, and he received his PhD in physical chemistry at the Free University of Berlin. The main interests of Professor Pacchioni are in theory and electronic structure of oxides, bulk, surface, thin film nanostructures, supported metal clusters, materials for catalysis, photocatalysis, and energy production. Professor Pacchioni received various awards, including Italian Nasini Medal and Pisani Medal from Italian Chemical Society, the Alexander von Humboldt Award, Blaise Pascal Medal from European Academy of Science, and he is fellow of Accademia Nazionale dei Lincei, Accademia Europea, and European Academy of Science. Today, Professor Pacchioni will talk of DFT modeling of water splitting by single atom catalyst. Handle with care. Thank you.
Thank you. Thank you very much for the introduction. Thank you for the invitation, and I'm really pleased to be here. Thanks to Lydia and Elio and the other organizers. And as you see from the title, and I will be a little bit critical about some aspects of how DFT is used, specifically in respect to what we are discussing today. So water splitting and in general catalytic reactions. Well, we all are familiar with the reaction, and we all know that basically there are two semi-reactions, the oxygen evolution reaction and the hydrogen evolution reaction. I will only talk of the hydrogen evolution reaction, but I could give exactly the same talk on the oxygen evolution reaction. Well, what is the role of modeling? Well, according to at least my general view, theory should be used to interpret experiments, to better understand experiments, to provide insight, which I think is very important, and of course also stimulate the preparation of new materials and new catalysts, which however is an extremely challenging target. So the question is, can we really safely go to the literature and take results from DFT calculations that predict the catalytic activity of a given compound and go on to the lab and try to reproduce and maybe to verify these results? Is really this something that we should follow? Well, I will also talk about single atom catalyst, although in my career I'm coming more from the, let's say, from the field of nanoparticles supported on oxides. Well, it is a great achievement now that we are able to control these metal systems down to the dimension of a single atom, which is also very good for theory because you are reducing enormously the complexity. So indeed, I spent most of my career dealing with problems like the particle size, the particle shape, the way this interacts, the interface between the metal particle and the support, the defects at the oxide surface, and so on and so forth. A huge complexity when you want to model this. But when you go to single atom catalyst, and we have seen examples in the previous talks, you have just one layer of graphene, for instance, and you have one atom which is basically incorporated into this single layer. And for a theoretician, this is a paradise. You have just a smallest unit cell. You don't have to deal with the flexibility of a metal particle, so everything becomes simpler. So the reason why we entered in this field of graphene is because we were forced by some collaborators. For many years I said, we are a graphene-free laboratory. For the simple reason that there are so many papers on graphene that I said, what can we discover which is not already known? But then these people, one group of Ivan Lee from South Korea University, and the group of Gianvito Villet at the Politecnico of Milano, basically they asked us to work in this field. So I will not report on these papers. These are basically published. I want to say something different. So we entered in the field of this reaction, hydrogen evolution reaction, on single atoms embedded in graphene or modified graphene. Now, let me mention that if you want to discuss the catalytic activity, there is a very simple model which has been proposed, and everything starts from the reactivity on metal electrodes. On metal electrodes, basically what you have is a semi-reaction. You have protons, they combine with electrons, and you form hydrogen molecule. Very simple reaction. Since both protons and hydrogen are at the free energy equals 0, the delta G of the reaction is also equals 0. And if the intermediates of the reaction have a delta G close to 0, everything is at the same level and there is no thermodynamic barrier. Well, very important, the first step consists in basically combining one proton with an electron, and you form an MH intermediate, which means a single atom sitting on the metal electrode. And then you have only two other possibilities. Either another proton comes to this specific site, it combines with another electron, and as soon as you have this reaction, you form hydrogen, and the hydrogen molecule desorbs. The other possibility is that these two hydrogen atoms diffuse on the surface until they recombine and they form the hydrogen molecule. In any case, on a metal surface, you only have one kind of intermediate, the hydrogen atom, because as soon as you form the hydrogen molecule, this desorbs. Very important point. Now, about 15 years ago, Norskov proposed a very simple model to screen the catalytic activity of these materials. Because since there is only one intermediate, one hydrogen atom adsorbed on the surface, if the absorption energy of this hydrogen atom, the free energy, is close to zero, then you have no barrier in the reaction. So you just have to compute the free energy of absorption of an hydrogen atom, and you are, if you are close to zero, you are on the top of a volcano plot. If, on the contrary, your catalyst is binding hydrogen too strongly or too weakly, you are at the two sides of a volcano plot, and it's not a good catalyst. So, good. This means that computationally, this becomes extremely simple, because you have your model catalyst, you put an hydrogen on top of a model catalyst, you have the protons and electrons reactants, hydrogen molecule, the products, and we have the intermediate. If the intermediate has a binding energy, the hydrogen is binding energy close to zero, platinum is minus 0.2 eV, in this example, excellent catalyst. If it is too strongly bound, molybdenum, or too weakly bound, gold, poor catalyst. Very simple. And of course, just by looking at this delta G, you can screen as many catalysts as you want. And this is what people have done, and people have done huge amount of papers and calculations because this is simple. So you can put in a single paper 200 compounds and you do all possible tricks and all possible predictions. Well, of course, people also try to derive descriptors. What is a descriptor? Is you correlate some properties, some physical properties, to the catalytic activity, which is the final goal of many of these studies in catalysis. So we were attracted by this paper, which was published in 2018 in Nature Catalysis by Xu et al., because they really look at a large number of these potential catalysts, and they found a beautiful, it's a linear, but there is this discontinuity here, but in any case, a huge number of catalysts are along a line, which is a very surprising and interesting result. There is a descriptor, which I don't want to enter into the details, so you compute your potential or your delta G, and you predict the activity of a catalyst very easily. Well, so when you are a newcomer, you enter a new field and you try to basically reproduce previous results. And first of all, you have to care about the method you're using. So we took a subset of results from this Nature Catalysis paper, and we tried to reproduce them. And these are all the numbers. I'm sorry for all the numbers, but we can concentrate on the red line. Is a nickel atom embedded in 4 nitrogen-doped graphene. We were surprised. The results was completely different. So the paper in Nature Catalysis was predicting 0.2 EV for the delta G, so very active catalyst, and we were finding 1.65 is a dead catalyst. It's terrible. And this is a huge difference, not only for this system, but also for other systems. Well, of course, we were using 2 slightly different variants of DFT. And I have to make a comment. Many papers in these days, they say, we have done DFT calculations. Please reject these papers. You have to say which kind of DFT you have used. Otherwise, it is a completely nonsense. Well, these people used PBE plus U, which is a more refined way than our calculation, but still, if you change the method slightly and you get this kind of differences, that is frightening. So the first thing I said, let's see in the literature if somebody has done the same kind of calculations. And we found not one, not two, not three, but 4 different papers where the same subset of catalyst has been studied, and we can just concentrate on the nickel, but also the rest. And we were relieved because all these 4 papers were giving more or less the same result as our calculations. And here I have to make a comment. These 4 papers have been published after the Nature Catalysis paper, but nobody has cared about why my results are so different from the previous ones, which is also something that happens in these days quite often. But at that point, we had to understand what is going on. And here, there is another problem in contemporary science. Well, if you want to reproduce a result, you don't find all the details that you need to reproduce the calculation. So we had to spend a lot of time basically looking at all possible small details in the calculation. I don't want to spend time, but most of the tricks were not really important. These are in millielectron volts, the maximum error you can have. But of course, if you, for instance, if you don't introduce spin polarization, so your catalyst as a magnetic atom and you treat it non-magnetically, well, this is of course wrong. But the exchange correlation functional, which is what often people don't specify, is extremely important. When we looked at manganese in this 4-nitrogen graphene system, if you use a given class of functionals which are not self-interaction corrected, the delta G is 0.3, 0.4 eV. If you use a self-interaction corrected functional, it's 1 eV. 0.4 and 1 is not the same. Well, of course, it's not always like that. If you take nickel, in nickel you have always the same high delta G because nickel is a closed shell in this system, while manganese is an open shell. But in any case, we were now ready to reproduce the whole set of results. And unfortunately, the discrepancies were still there, and very large discrepancies. And with these discrepancies, and if you think nickel still was quite off and completed a different prediction, of course, if you take all our values, which are the blue spot here, you don't have the nice correlation with a descriptor that was claimed in the Nature Catalysis paper. So at that point, we contacted the authors, and after 3 exchanges of mails, we realized that it was not possible to go beyond that, so we contacted the editor. And finally, thanks to the help of the editor, we got the raw data. And the raw data of the group was showing that all the structures used were strained. Instead of being in the minimum, which is what you should use, sometimes the structure was strained by 1%, sometimes by 2%, sometimes by 5%, sometimes in the X direction, sometimes in the Y direction. Finally, the results were not reproducible because that nothing, and also mean nonsense. Well, interesting, some of this data are now used to train machine learning, and this is also quite frightening. Now, the paper is now under investigation. At least this is the only result we got so far. So the first part of the message, we have to be very, very careful, because when we want to predict something which is plus minus 0.2 eV, there is an intrinsic error in the calculation that it is at least 0.1 eV. And then, depending on the functional you're using, the error can be, or the difference can be 0.7 eV. And so one has to be very careful. So there are a lot of aspects that have to be looked more carefully. But that is not the end of the story. Then there is also the importance of the model. Well, this is, I told you that on metal electrodes, and this is what everybody is using, there is only one intermediate. You have hydrogen atoms, and if you form the molecule dissolves. So, but single atom catalysts, as this has been mentioned already, are analogs of coordination compounds. Are the same. You have a metal atom bound to 4 nitrogens. Well, since I've been working in organometallic chemistry a long time ago, I remembered that in transition metal complexes, you can form the so-called dihydrogen complexes, which can either be dihydride, when you have completely broken the hydrogen-hydrogen bond, or you can even have dihydrogen complexes. So it is an activated hydrogen molecule, and playing around with the ligands, you can play around with the HH distances. A beautiful chemistry. Kubas is one of the fathers, 1980s. So when we enter in this field, I said to my coworkers, I cannot believe that nobody has tried to put 2 hydrogens on the single atom catalyst. Indeed, nobody has tried. Hundreds of papers, nobody has tried to put 2 hydrogens. So what we did, we took a subset of 55 different single atom catalysts, either embedded in molybdenum disulfide or in graphene, various, and most of them, they form a stable dihydrogen complex, which can be really a dihydrogen, so with a short hydrogen-hydrogen distance, or dihydride. And when we could compare our computed geometrical parameters with existing structures of known complexes, these were in perfect agreement. But now the question is if you can form these double hydrogen systems. This is another intermediate. So you have another step in the reaction. And the kinetics is completely different. It's not only one intermediate, the hydrogen atom, but you have 2 hydrogen atoms. And if you work out the kinetics, and this was done by my coworker Giovanni Di Liberto, you don't have a 2-dimensional volcano plot, but you have a 3-dimensional volcano plot because you have 2 delta Gs. You have to go through 2 steps. And of course, what we did, we took this set of 55 hypothetical catalysts. You can construct your volcano plot with a classical single hydrogen model. And of course, on top you have palladium, cobalt. These are the best catalysts. Delta G is equals 0. But if you take into consideration the second possible intermediate, the number of good catalysts drops because many of those are not also good for the second step. So the kinetic is different. So the model is very important. And in oxygen evolution reaction is the same. Many people forget, and there are many more different intermediates that you can form, and the kinetics can be completely different. So look at the intermediates. But then there is another thing, I don't have time to go into this, but water splitting occurs in water. And so you have to include the solvent. Because if you don't include the solvent, sometimes this is not relevant or little relevance, but according to our estimates, you can have an error of 0.5 eV if you don't include the solvent. So how can we trust calculations which are done for dry systems? And what about the pH? Also, the pH has a role, and this can also be included. And there are also other small effects, like the fact that this idea of a delta G equals 0 is valid if the overpotential is 0. But if you are at different overpotentials, there is a shift. This has been demonstrated by Exner. It's a small shift, it's 0.2 eV, but it's another correction. So one has to be very careful in these matters. So not only the method, but also the model has to be good. It has to include all possible intermediates, otherwise the predictions have little meaning. Okay, so we wrote one article where many of these concepts are summarized, but I want to only read the last sentence, which is my personal view. And we wrote, time has come to shift the attention from the quantity of data produced to their quality. This could help to better understand the physical and chemical origins of a catalytic activity and be of real help to the experimentalists in designing new efficient catalytic systems. And with that, I would like to thank my co-workers, in particular Giovanni Di Liberto and Luis Antonio Cipriano Marcos. Now he's left the group, and of course my experimental colleagues, but I didn't report about the work now. Thank you very much.
Thank you, Professor Pacchioni, for the interesting talk. Let's now move to the second talk of the second part of the hydrogen production session. And the talk will be delivered by Dr. Alessandro Lavacchi. Dr. Lavacchi is a senior research scientist at Italian National Research Council at Institute at ICOM Institute in in Florence, where he also holds a position of head of electron microscopy facility in Florence research area. His research focuses on electrochemistry and material sciences of surface and coatings. And he has been also involved in nanofabrication of catalytic architecture with special attention to the application of nanostructured catalyst for exploiting biomass in electrochemical system. He has contributed to development of methods for the synthesis of platinum-free electrocatalyst for application in fuel cells, electrolyzers, and raw chemicals electrosynthesis. He has been PI of several research projects, and today he will talk about electrochemical reforming, a high-intensity process for the cogeneration of green hydrogen and sustainable chemicals.
So thank you, Lucia, for the kind introduction. To me, this is a very emotional experience. It's very nice for me talking at CNR, my own institution, in such an important event. And I'm going to discuss today about a process that was pioneered more or less 10 years ago, 12 years ago for the first time by Francesco Vizza and Claudio Banchini, who was a former director of the Institute and the actual director of the Institute, Francesco Vizza. This is a process we believe much, and actually it's a way to explore the nexus between hydrogen and chemical production. I think this is a very relevant point because historically hydrogen and chemicals have been very much connected by the story of oil refinery, for instance, or gas transformation. So today we will we will introduce you to this process that is electrochemical forming, which is, as the name states, an electrochemical way to deliver the reforming, particularly of biomass and waste resources. How does it work? Doesn't change. Okay, shall I use this? Okay, much better. Okay, I think each of you is very familiar with this, you know? I mean, this is electrolysis. This morning you have talked much about this. This is PEM electrolysis, which means electrolysis with acidic membranes. Amazing technology. You can actually buy this system and you can get them installed in 1 year or two, even in size of 10 megawatts or so. Let us discuss a little bit of the energetics of this process. You know, all we know that water is a very stable molecule. I mean, 237 kilojoule per mole, which means that to split water electrochemically, we need at least 1.23 volt to win the thermodynamics contribution. But then we must push the reaction to achieve the high intensity of the process, which means working at least 1 amp on square centimeter, possibly more, and eventually for short time, even more than 5 amp on square centimeter to buffer, I mean, electrical energy peaks. What is the point here? The point is that practically, to run the process at more or less 1 amp on square centimeter, 2 amp on square centimeter, you need an electrical energy input of 1.72 volts, depending on the technologies that you use. Let us split this contribution. So we see here that we have the thermodynamic contribution, and then we have the kinetics contribution. So we have the activation kinetics for the hydrogen evolution reaction, and then we have the kinetics for the oxygen evolution reaction. And then we have others, which means migration, all the other contributions you can have in the system. So it means that for this, I mean, the larger contribution is this one, definitely. So what means this in terms of the energy we use to produce 1 kilogram of hydrogen? Basically, it means that we need more or less 45, 48 kilowatt per kilogram of hydrogen, give or take. And of this, more or less, more than 30 kilowatt hour per kilogram go to win the thermodynamics of the process, and the rest to drive the process at the current density that is possible to achieve with this system, which means more than 1 amp on square centimeter, more than 2 amp on square centimeters. This means that more or less 78% of this energy goes into thermodynamics, which is very much, and more or less 30% goes into the kinetics. So far, most of the research in the process was concentrated on this part of the reaction, making the system less resistive, more active toward hydrogen evolution reaction and oxygen evolution reaction. So is there a way to work on this part here? For sure it is. I mean, there are many, actually. The use of temperature is probably the most popular. All we know that water can be spontaneously split if we raise the temperature. So if we go to 5,000 K, for instance, we can get the splitting of water in its elementary component, hydrogen and oxygen, but not very practical for the extremely high temperature. Or we might use thermochemical cycles happening at 500 degrees C. This is increasingly popular for coupling with nuclear technology, especially the 4th generation that are expected to deliver heat at this temperature. And then all we know also the solid oxide electrolyzers. I mean, they work at higher temperatures, so I mean, the electrochemical window of water shrinks. And this is an advantage. But we can do also something different. We can try to work at room temperature. And the possibility we have is replacing the oxygen evolution reaction with some other reaction that happens at lower potential. So here comes the trick. So this is the core of electrochemical reforming. In this process, what we do basically is instead of evolving oxygen at the anode, we oxidize biomass at the anode. And since oxidizing biomass, the organic compounds, is much easier, at least in terms of thermodynamics, compared than oxidizing water, this leads to a dramatic decrease in the potential of the system. So if we see these two systems, this is an acidic electrolyzer. Alkaline, it's the same because the electrochemical windows of water doesn't shift with the pH. I mean, the width of the window is the same whatever the pH is. It's 1.23. If we place ethanol, for instance, we can get 0.11 volt. So basically, we annihilate the thermodynamics contribution in the system. What we have to do is to drive the reaction very fast. Does this process works? Well, we demonstrated that it does. This work, I mean, the pioneering work I mentioned before, in 2010 demonstrated that it is possible to carry on this process. And what you see here is that you can achieve interesting current densities even at 0.6 volt, 0.7 volt, compared to the 1.72 volt of electrolysis. But at that time, the current density was not high enough. Why this number is so important? Because the key toward the exploitation of hydrogen, toward a real-world hydrogen application, is high intensity. We need processes that work at more than 2 amp, 1 amp on square centimeter, which means keeping the system as small as possible, lowering the footprint, and possibly also delivering separated hydrogen and oxygen to make this convenient. Everything that works with low intensity, I mean, it's actually a problem for the exploitation. That's why electrolysis is so appealing, because it's extremely high intensity process. So we tried to move this, to move away from this figure, going to the same productivities of water electrolysis, at least in terms of current densities. And so we engineered the catalyst. So what you see here is basically a conventional palladium Vulcan catalyst, carbon black with metal nanoparticles on top. And we decided to switch to different kind of supports that are more open and allow a much better mass transport. So the first experiments we did were with titanium nanotube supports. So we prepared high surface area titanium nanotubes by the anodization of titanium, and we got this nice catalyst with the possibility to dope them with particle. With some, the process is also pretty straightforward. It's an anodization process. In principle, it could be deployed in any company that works for aluminum anodization, for instance. So it's still something that is in the, I would say, national industrial culture, because we have a very well-developed galvanic and electrochemical tradition in our companies, especially in Tuscany. We have thousands of companies working in the area of galvanic deposition and also aluminum anodization for fashion and technological purposes. So we can get this, and as I said, we can dope them with palladium nanoparticle, and we can achieve extremely high current density. But there is a problem in this system, and the problem is that originally titanium nanotubes were grown on compact bulk foils, so they don't allow the flow through of reactants and products. So we needed to engineer this to move to real-world devices. And here is the big step we make. So we moved from this anodization of this that is blocked to create something that is more similar to a conventional catalyst architecture for fuel cells and electrolyzers. And the idea in this is very simple. Those who work with electrolysis actually are familiar with these felts. This is a titanium non-woven web. It's an unwoven textile, basically. It's commercial. It comes from Beckert in this case. So what happens if we make the anodization of this material? We can create the nanotubes in this structure here and add the nanoparticle to this structure. And this delivers, a pretty straightforward route to create, I would say, integrated porous transport layers with the catalyst. Well, amazing. Moving from carbon, we were able, in electrochemical reforming, to achieve 2 amp on square centimeter current density with a potential that is more or less 0.9 volt, and which I think is very nice. And pretty much of a cognitive bias here. This is a work we did in 2014, and we didn't give much credit to this curve here. But in 2014, it was actually very good. This is alkaline electrolyte membrane electrolysis, and we were able to get 2 amp on square centimeter with the same cell and with this catalyst architecture in an alkaline electrolyte membrane electrolyzer 8 years ago. But at that time, our interest was much here, so it's our cognitive bias at that time. Okay, you can work with a lot of alcohols, and you actually have the same kind of results. So the energy input is usually very small, and with ethanol, for instance, you can get an electrical energy input of more or less 18 kilowatt-hour per kilogram of produced hydrogen. And then you can also oxidize other compounds like 1,2-propanediol, glycerol, and so on, and you can get amazing products. The oxidation of this compound deliver raw chemicals that can be used for transforming them in basically raw chemical critical for our society, like, for instance, lactate or lactic acid that can be used as a building block for biopolymers. But, of course, as we said, we save a lot of energy compared to electrolysis, but this energy comes at a cost, actually, because it's not for free, no free lunch in nature, actually. So we bring energy to the system by using ethanol. So when this system becomes convenient compared to water electrolysis, I mean, what are the characteristics of the biomass we use that can make this overall energy input to the system convenient to water electrolysis? Actually, this happens because of these numbers for bioethanol, for instance. This is the energy return of the invested energy. And if the energy return of the invested energy of ethanol is larger than 5, the process, at least in the lab scale, for the level of the evaluation we have done with this very small device, can compete with water electrolysis in terms of overall energy input. So sugarcane might meet this requirement, for instance. This is the galaxy of chemicals you can, for instance, get from that. You know, I said at the beginning, this is a nexus between hydrogen and chemicals. So you can get, for instance, acrylic acid, or you can get malonic acid, lactic acid. All these compounds may have added value. So in the whole hydrogen value chain, you can share the cost between these products. It's a kind of life cycle analysis you can make. So it's an additional benefit you can get from the system. No time to do that. This is what we envision as a model for the integration of the electrochemical reforming. So basically, we have the production of the, we have two approaches, small plants, which can be delocalized with renewable energy supply, and we can bring the waste biomass to the electrochemical reformer, and then we get the exhaust reformate, and we process it to create chemicals. And on the other side, we have hydrogen that we can use to power generation, generally. And then we can have big plants, which means a biorefinery, for instance, might have a process like this in its plants. And this could be a low energy process for providing raw chemicals with electrochemical routes. This is pretty much the work we have done at ICOM in the last 10 years. There are no photos, but you can see some of the people that have worked on that at the, at the end of the room over there. And next, there is a lot to do. I mean, for sure, we need to create new catalysts that are more active and use less platinum group metals for this transformation. We need to make more research on the electroorganic synthesis of this biomass. Well, I think one challenge could be, would we be able to make an antiselective synthesis, for instance, for building block of polymers this way? And then we need to deliver a first comprehensive life cycle assessment of the process. But what I want to stress in the end, I mean, I was thinking this morning while coming here, is that this, like electrolysis, is a high-intensity process. Any process that aims at producing hydrogen and bulk chemicals for the society needs, at least for the electrochemical processes, to work at more than 1 amp square centimeter. Guys, this is really a lot. Means that every second, every square centimeter of your device must allow the passage of at least 100 billions of billions of electrons, which means that must allow the transformation of 100 billions of billions of molecules when you create an electroorganic synthesis like this to make it practical. And since the goal is producing hydrogen, producing bulk chemicals, and in the future will be for sure decarbonizing cement, iron, ammonia that work in billion ton scale, intensity must be the mantra I mean, we can't use processes that are too diluted or, I mean, have definitely low intensity. So that's it. Thank you.
Thank Dr. Lavacchi. Let's now move to the last speaker of this first session. That is Dr. Giuliana D'Ippolito. Dr. D'Ippolito is a senior research scientist at the Institute of Biomolecular Chemistry at Italian National Research Council in Pozzuoli, Naples, Italy. Her research activities cover the field of green chemistry and processes for sustainability, and basically deals with chemical studies on microbial metabolism for the biotechnological development of sustainable bioprocesses, production of bioenergy, biohydrogen and biodiesel, and added value molecules through biological processes in hyperthermophilic bacteria and marine microalgae, and capture and valorization of CO2 through microbial platforms. Dr. D'Ippolito has been and is PI of several national and international research projects, and today she will talk about green energy from a biological mechanism for energy conservation.
Good morning. Thanks, Lucia, for the kind presentation, and thanks to Lydia and to all the organizing committee for inviting me. I speak about biological hydrogen production. That is possible in microorganisms that possess a complex enzyme called hydrogenase that use protons as an electron sink to discard excess energy, reducing protons to hydrogen. Electrons comes in the cells from water splitting in photosynthetic microorganisms, or, for example, from glycolysis, a process of sugar oxidation. To improve hydrogen production in microorganisms is essential to know the pathway related to hydrogen production. The comprehension of this mechanism can help to direct more metabolic energies versus hydrogen production. One of the most promising process for biological hydrogen production is dark fermentation, operated by anaerobic bacteria. Glucose in this process is oxidized by glycolysis to pyruvic acid, and when pyruvic acid is oxidized to acetyl coenzyme A, the produced ferredoxin is oxidized together with NADH by hydrogenase, producing hydrogen. In this case, I show the acetic fermentation, and acetic and hydrogen are the only extraction product. and the hydrogen produced in the headspace of the culture is highly pure. And in the process production of lactate, reduce the availability of pyruvate and NADH for hydrogenase. In this context, we started to work in the hydrogen field in 2005 during a FISR project on our model organism, Thermotoga napolitana, which is a hyperthermophilic anaerobic bacteria with an optimal growing temperature of 80 degrees. The bacteria was isolated from the hydrothermal system of the Gulf of Pozzuoli. We optimize some culture parameters such as pH, agitation, headspace, culture ration, and so on. And we demonstrated that it is possible to have with this bacteria hydrogen yield very close to the theoretical value of 4 mole of hydrogen per mole of glucose and an high production rate in terms of hydrogen produced per liter of culture per hour. Okay, generally, during the cultivation of this bacteria, nitrogen sparging was used to arise an anaerobic environment. But what happens when we sparge a culture with CO2? CO2 induced a general acceleration of the fermentation process, inducing an increase of growth and glucose consumption rate. We have a complete glucose consumption in 30 hours. And CO2 did not affect hydrogen production, but decreased the level of acetate that was balanced by an increase of lactate. This was quite surprising because hydrogen and lactate compete for a common pool of reducing equivalence in the cells. But in addition, CO2 is fixed in the carbon 1 of lactic acid as an ambiguously proven by NMR using C13 labeled CO2 generated in situ. And we can see in the C13 NMR the increase of the carbon signal related to carboxy group. This CO2 absorption is possible by reductive carboxylation of acetate, as we proven using labeled CO2 and labeled acetic acid in position 1, supplemented in the medium, or produced by using labeled glucose in the culture. And we obtained the lactic acid labeled in position 1 and 2 as proven in C13 and NMR by doublets flanking the natural resonance of the signal of carboxy group and alcoholic function due to the C13 homocoupling of these carbon atoms. Okay, the enzymatic reductive carboxylation of acetate offers an interesting mechanism from a biotechnological point of view, especially if we think that non-photosynthetic routes for CO2 deconversion into valuable molecules are not so common. Very few microorganisms possess these mechanisms, such as some archaea and chemolithotrophs, and in none of these bacteria it has been reported hydrogen production. Hydrogen is generally a reactant, not a product. And okay, but how widespread is this mechanism among hyperthermophiles? We screened different species belong to Thermotogales and Pseudothermotoga order, and only other two species are able to perform this reaction. And Thermotoga napolitana subspecies capnolactica, that is our proprietary strain, obtained in laboratory under saturated concentration of CO2. And a sister strain called RQ7, that is a naturally competent, and as we have the complete genome sequence, and so it was possible to think two molecular approach in which we try to boost the reaction, the reductive carboxylation of acetate by introducing an heterologous gene of Thermus thermophilus, and that is able to convert exogenous acetate in acetyl coenzyme A to feed the reaction. And the recombinant strains showed an increased production of lactate, and to demonstrate that this lactate derived from external acetate, we use labeling experiments, and we demonstrated that an increase of CO2 derived lactate of 70%. Okay, then we investigated what are the carbon sources that can feed the process. And process can be fed by monosaccharides, disaccharides such as sucrose, lactose, and complex polysaccharides such as starch and cellulose. This is due to the capacity of Thermotoga napolitana to internalize and hydrolyze complex lipid due to the presence of a great variety of hydrolytic enzyme. And this is important in view of a circular economy approach in which we think to use sugar-based waste, such as waste deriving from confectionery industry and so on. Okay, we called the pathway capnophilic lactic fermentation. Capnophilic means CO2 requiring. And in the pathway, it is possible to obtain hydrogen and L-lactic acid at a high rate, starting from sugar-based waste, and CO2. It's interesting to note that in this case we don't need the chemical or enzymatic step of hydrolysis. This is an important point if we think that the saccharification step is one of the major bottleneck in the bioraffinery process. And lactic acid produce is L-lactic acid, an antimerically pure that is important for the industrial purpose. So we have a sustainable bioprocess for production of green hydrogen in Termotoga Napolitana, and CO2 valorization. We actually demonstrated and validated the process on a fermenter of about 50 liters with a high production of hydrogen, but also high production rate. That is an important point, the capacity of the cells to produce hydrogen in a short time, and a good conversion of the carbon in lactic acid. The development of this process was possible to the study of the complex metabolic network of capnophilic lactic fermentation. In the last 10 years, we dedicated to the study of the mutual crosstalk between of the hydrogen-related metabolic pathway from a biochemical and chemical point of view. And we accumulated some clues important to understand the cellular and metabolic reorganization of the cells induced by CO2 and the impact of hydrogen production. In particular, some key points such as the carbon balance, hydrogen balance, and the additional reductants that are necessary in the cells to sustain the concomitant production of hydrogen and lactic acid that are reaction requiring reducing equivalents. Okay, I report some key point about the glycolytic pathway. It's important to know that CO2 induced a downregulation of the classic glycolytic pathway, that is the Embden-Meyerhof pathway, and a shift versus the pentose phosphate pathway, as we proven by using different labeled glucose labeled in different position and analyze the product by NMR and mass analysis. And this is an important point. Why? Because in this way, the cells under CO2 is able to produce more NADH and NDPH per glucose unit to support the reduction dependent by reducing equivalence. And these reducing equivalents are used by hydrogenase, exploiting the energy conservation by electron bifurcation. That is a mechanism to drive an endoergonic reaction, coupling it with an isergonic reaction, splitting two electron donor in two electron for two acceptor, one at low potential and one at high potential. And this is the way in which hydrogenase can produce hydrogen by the isergonic oxidation of ferredoxin and by the coupling it to endoergonic oxidation of NADH. Other important enzymes involved in this process are enzymes abbreviated here as RNF and NFN. Because they create a cyclic process to supply the NADH, the additional surplus of NADH to support the concomitant production of hydrogen and lactic acid. RNF is connected to the gradient of sodium that in turn activate the synthesis of ATP by ATPase. And following a classic energy conservation mechanism of chemiosmosis. NFN is a bifurcating enzymes that exploit the endergonic reduction of NADP ion with NADH with exergonic oxidation of NDPH with ferredoxin. Okay. In synthesis, okay, we have that. In synthesis, we have that termotoga napolitana under CO2 metabolize glucose by the classical glycolytic pathway, and the NADH produced during the oxidation of pyruvate to acetyl coenzyme A is fuel hydrogenase for hydrogen production. NADPH produced by pentose phosphate pathway drive the formation of NADH by the NF complex and formation of reduced ferredoxin that fuel the RNF complex that create a gradient for the ATP synthesis. Okay, I want to acknowledge all the components of the Organic Chemistry unit of Institute of Biomolecular Chemistry of CNR in Naples, in particular Angelo Fontana, all the external collaborators located worldwide, and all the projects that support in the last year this research. And I want to report you that CNR is involved in activity line in the PMRR project. This activity line is dedicated to biological hydrogen production, and these are the components of the team of the DSCTM and DTET. Okay, thank you for the attention.
Thanks, Dr. D'Ippolito, for this biological view on hydrogen production. Now I would like to thank all the speakers of this mornings, but their job is not over, because I then, I would first of all thank all of them. And now invite all the speakers of this first session here on the stage for the discussion that will be led by Dr. Maurizio Peruzzini, that will also come.
So, good morning everyone. I am Maurizio Peruzzini, I am the former director of this activity department, and I'm very proud of the invitation of Lydia and the Helio to be here today.
be here today, just to coordinate together with Lucia this just panel discussion of a discussion session. Yes, please, I ask you the speaker to take their chair. I don't know, ma c'entrano tutti? C'entrano? Okay, seven chairs for 7 speakers. So that have been indeed extremely brilliant today. They have covered different aspects of hydrogen production, moving from electrocatalytic production, the frontiers of electrocatalytic production, to an excursion of different catalysts, single-site catalysts, theoretical analysis of how the systems works, and finally, we have a biological view of the system. 7 speakers is a little complicated just to coordinate all of them, and I would like also to ask the people sitting in the audience to raise questions as much as possible, because this is really the salt of the story. So, please, raise question. Well, I appreciate a lot all of your lectures, very nice, very beautiful, but I have just a general question to you that has been touched by some of you, but that is always pervading my feeling with respect to the production of green hydrogen. How much is the cost of green hydrogen, and how is this technology really competitive with the current one, that is the production of gray hydrogen from fossil fuels? In other words, do you think really that the very minor production of green hydrogen that is today, I guess, I suppose is about 2% at the maximum, will become really prevalent, will become really the driving force for the hydrogen economy? I don't know how to work. Maybe that just sitting on my right side, on my left side, Professor Pacchioni could start the discussion and then move to the other one. This is one point. And the other point is, we didn't talk, and the other session of this beautiful Avogadro Colloquia will talk about that, but I guess that hydrogen, the transition to a real hydrogen economy, has a lot of bottlenecks to be overwhelmed. In particular, the hydrogen storage will represent always a problem. And also, I would like that you consider in just first discussion, how could be the way by which the production of green hydrogen will replace the fossil fuel production of hydrogen in 20 years or 30 years if we match the 2050 limit fixed by the European Commission also. Please, Gianfranco, do you want to start this discussion? Stay very short, because 7 speakers means 35 minutes just for 5 minutes each. Please.
I will be very short because I don't have an answer to your question, but I have also a question myself. Until a couple of years ago, the discussion about the cost of green hydrogen production was entirely focused on the cost of electrolyzers and so on, giving that the cost of methane was considered to be fixed. But now with the cost of methane, which went up by a lot and is also oscillating, what is the reference? So when you say it is convenient, but of course also the cost of the raw material, the methane in these months has changed in a huge way. So I think if the cost remains so high and the production of green hydrogen cost will decrease, for sure it was already foreseen to have basically a crossing point. This will become closer and closer.
That's clear. So we needed at a certain point the big companies, in some way, decided really to invest in green hydrogen production. Please, Professor.
Yeah, okay. So I can just add to my previous speaker. These are, by the way, very important questions. And obviously, it depends a lot also on the scale, because most of the components will become cheaper as the production numbers go up. Not everything. Some noble metals do not follow this economy of scale, like iridium, for example. That's why it's important to minimize this. But things like maybe bipolar plates and certain other components of an electrolyzer should follow, to some extent, the law of the economy of scale. So they should become cheaper as the production ramps up, yeah? And so while we're probably currently somewhere between 5 and 10 euros per kilogram, I'm hopeful that we will see that it will drop below 4 euro per kilogram. And again, as the reference is moving, as our sort of benchmark is becoming more expensive, it becomes more competitive over time. And so in the US, they put out this Earthshot program, $1, 1 kilogram in 1 decade. So by 2032, they believe they can be somewhere around 1 kilogram for $1. We'll see. We'll see about this. And when it comes to the second question, I think you were asking how to use it, where to use it. In Germany, in the National Hydrogen Strategy, they put out sort of the mandate to use, because we don't have enough hydrogen at the beginning, to use it primarily there where there is no alternative. So decarbonize industry. This is a mandate, I mean, a real call to focus on things like ammonia and steel in Germany. There are other applications where we do have some alternatives, like propulsion for mobility. At least for light-duty vehicles, we have the battery. And then things like energy generation, this should come later than when more hydrogen is available. And also heat is something which is probably deferred to a later stage, because that requires a replacement of all the burners. Yeah? You cannot feed directly hydrogen into a methane burner for industrial heat, so this requires an enormous amount of, let's say, investments. Yeah? And so, at least in Germany, I think they decided to start with decarbonizing industry, which also requires modification of the, steel mill and all this. But that's where they start, as long as we have limited amounts.
I was told, there is this one. So nothing to add on the comment from Professor Pacchioni and Professor Strasser. It's clear the targets are very ambitious, actually. The $1 per kilogram in 1 decade is actually truly ambitious. What I would like to mention here is on the second question you raised, is basically, how to make it really green. Because we have, I think, an issue that is the real possibility to decarbonize the energy production. And I think we are already late, at least in Italy, toward the goals we have for 2030, because the installation of renewable energy is late compared to the planned agenda. So I think the problem of decarbonizing, of moving to hydrogen is connected to the decarbonization of energy, of course, and the agenda defined by the European Union is very strict. And we do have many issues, especially, in non-technical elements, like, bureaucracy that we have in our countries to get authorization to install renewable power plants. So
legislation is not...
I think that the point is that the processes are lengthy, So to install, a small renewable energy plant, you need to spend more than 2 years waiting for authorization, and then you get, of course, many trouble because the return of the investment is low, and so on and so on. So I think that, to push hydrogen toward the targets, we not only need technical, points, which are of course very important, but we need to boost the administrative processes for the deployment of renewable energy. That's truly a point to me, and we are already late compared to the agenda, which means that to come to the targets we have for 2030, we need to be faster year after year with the installation of these renewable resources. So what I want to point out is that we as a community, I think we have also the responsibility to stress on this point. So it's not only a technical matter, there are commercial, technologies now, and the learning curves and the massive deployment might lower the costs, but we need really to stress that even the administration is important, and we need to push the system toward the installation of renewable power plants, because so far, it's plenty of problems. If you decided to do it and to invest, and you are an entrepreneur, and you are plenty of unknowns, especially in Italy, how can you afford the investment if you don't know your return time, you know?
That's clear. Angelo? Oh, of course, shake your hands. There
is a Professor Fontana sitting
Angelo Fontana, CNR and University of Naples. I just want to add an issue to your question, Maurizio. So we start from the premise that these processes are better than the usual process, the traditional process for the production of energy, in terms of eco-compatibility and eco-friendly. Okay, but if we limit the discussion about the cost, and we may forget about the importance that we have in the development of eco-friendly processes. So the question is, how much are these processes eco-friendly? And of course they are fine now for decarbonization and for the emergencies we are facing right now. But in terms of the future, in the real future, so in terms of years, how this process can be sustainable in terms of nature and eco-compatible processes, and to keep our life on Earth. So not only the cost, but also the eco-friendly sustainability of this mechanism. Because we know that many processes, currently the hydrogen production is much more aggressive and dangerous than the use of oil, normal oil. So is this changing? Are these processes really changing, or they can in the future really change this issue?
I do agree perfectly with your vision, but you should consider that generally big company, that is the economy of the world,
makes an important role that not always goes in the same direction and with the same velocity expected for an eco-friendly transition. So that is the point for which the cost of the system will be a driving force in all the story, in my opinion. Ippolito, no. Giuliana.
Stefano.
So, just to, I don't have much to add to what Professor Strasser said, but taking the cue from your consideration about the long-term sustainability, I think that one thing that was interesting was also one of this last slide of Alessandro Lavacchi, that was in one of his slides was also mentioning the life cycle assessment, life cycle analysis, because we don't always, we are at the very beginning with these technologies, and so we don't really have still the full idea how much are the indirect costs of these technologies. And also, if you really want to, so the hydrogen economy for sure will be a reality in the near future. I think there's no doubt about that. But competitive technologies, for example, like batteries, are becoming so much more important. I think that a couple of years ago, we thought that, for example, the hydrogen car would be a reality, but right now, with the cost and the performance of batteries, is not anymore certain, something like that. So probably batteries will be competitors and very important as an alternative to, in many contexts, with respect to hydrogen. As a chemist, we always say we want to store energy in chemical bonds, but to store energy electrochemically in batteries is also an alternative that is getting more and more convenient. There was the problem of lithium. There's not lithium enough for everybody, but maybe other materials now are emerging in batteries, and maybe batteries will eat a large part of the market that we thought was devoted mainly to hydrogen. And in this context, it will be also very important, the policy of the countries, because, for example, if you put a carbon tax, it will make very relevant how you make hydrogen, and so you can also shift a bit the applications and the overall way we approach in this hydrogen economy.
Okay, yes, as a chemist, and okay, and about biological hydrogen production, it's clear that it is a very attractive technology from an academic point of view, but also from a biotechnological point of view. The major tendency is to improve yields, to mimic the hydrogenase as artificial catalyst, or to express hydrogenase in other microbial host. It's clear that it's important to respect various concepts, as we told, to overcome the simple question about the economy of the process. It's important to meet the principle of a circular economy approach, and to respect the sustainability of the process, and to try to meet all these principles, and to do a general evaluation together with the costs.
Thank you, Juliana. Here is a question, and then another question there.
Thanks. More than a question, may I? More than a question is a further comment. Is a further comment to the Juliana opinion, is that she didn't mention, I think, about the photosynthetic biological production of hydrogen. We should consider that, for example, some cyanobacteria or microalgae, they produce hydrogens, but not only hydrogen. They might be used for many, many purposes. So hydrogen is only a part of it, but if we exploit all the products that they can have, then maybe hydrogen can become cheaper. Now, biological hydrogen is the most expensive one, very expensive, but if we consider the old products, maybe we find a way to make it convenient or cheaper.
How much is possible to manipulate these bacteria, just to force them to produce whatever you want, in particular hydrogen or other relevant compounds?
Well, it is, of course it is possible. It has already been done. In the States there are many variants, mutants of microalgae that are optimized to produce hydrogen. So this is, of course, is a way that can be pursued. I mean, it's already done. is a reality. So it depends on how much we want to invest in this. Unfortunately, there is not a group here, is in another department. They have, is it just in Florence, the Terra Ambiente department. They are doing already this kind of studies. And then there are many ways to optimize this way. Yeah, thank you.
Let's now move to the vision of industry.
Okay, I will go back to the first question regarding the cost of hydrogen. So, you know, total cost of hydrogen, you have at least two important components. One is the capex and the other is the power. Yeah, so I have a problem with microphone, sorry. Okay, for the capex part, there are, I would say, clear roadmaps how to bring down the cost of electrolyzer, even the present technology, so the alkaline I was referring to in my presentation, for instance. That means we need, somebody mentioned, we need the scale, so hundreds of megawatts, gigawatts of production, so to scale down, to scale up production capacity and bring down the cost. We need a new way of producing electrolyzer, so concept of automation are needed in order to bring down the cost. So we have to also think about a new approach in producing, not only in producing, maybe also already at the design phase, no? To design for manufacturing are really concepts that are needed here. But this is only for the capex. Okay, regarding the capex, I fully endorse the comments that we need high intensity, 1 amp square centimeter, the mantra, correct? Yeah. Then I have a question, where this number comes from? Because you were very precise in saying 1.
I say more
than 1.
I mean, if you look even at the calls from the FCHJU for where's microphone, please? Okay, sorry, I forgot that. But this is coming from the even from the call FGHJU or the targets. It's even more than 1 amp.
Yeah.
1 is actually still pretty low, so it's 2 amp, and with the possibility to go even higher to buffer peaks in the electric energy production. So FGHJU, this was the call, I think, in 2018 or 2019, I don't remember very well, but that was the point. So it was 2 amp constant operations and 6 amp peak, and 2 amp with less than 2 volt, I think. It was something like that.
No, we agree that high current density is needed, but...
Okay.
And if I...
No, finish, please.
Okay.
Don't speak to each other.
Sorry. Okay. Apart from the capex, then there is the power part, and to have competitive green hydrogen, we need renewable, so large availability of low-cost energy. That's clear, because we cannot only focus on hydrogen production technologies if you don't have enough energy, green energy, to power the electrolyzer, and this is the key point. That also, let's say, is important for the question regarding sustainability. Life cycle analysis is important. We started performing life cycle analysis of our products. And again, you have the carbon footprint associated with the production of electrolyzer, for instance, including electrodes. But then on top, you have to include the carbon footprint of the energy that is consumed during the process. And again, this is the big portion. So we need renewable energy.
Okay, thank you. We skipped the question before. Please. Present yourself.
Francesco Basile from University of Bologna. No, okay, you answered already one of my questions that was on the power production. I have 2 comments. First, probably we need to compare with the hydrogen at the same level of carbon emission. So when we compare the cost, we need to consider the cost for sequestration at least, and it's a more fair competition between the green hydrogen and the gray hydrogen with carbon capture and sequestration, for instance, just to answer to the same thing. So maybe it's, in my opinion, while the cost of the green hydrogen will decrease, the other costs will probably need to increase for also take into account this point. Secondly, do you feel, more a question, do you feel that there is a limit in the supply chain for the growing of the hydrogen economy? Because we are discussing about critical materials very often now. So this is for me a crucial point on your perspective.
Somebody will want to answer, please?
Yeah, thank you for these questions, Luca. Regarding the supply chain, this is indeed a limitation at the moment because, of course, we have, let's say, significant challenges, but still, of course, there is a need, as also mentioned by the previous speakers, there is a need to achieve significant automation in this field and also address new technologies, advanced technologies. So the supply chain is really probably a very determining step. Also for the implementation of the recovery fund in Italy, because we have significant goals as mentioned, but still we need to implement the national supply chain for the hydrogen technologies. So that's clear. I would also like to comment on the first question regarding the hydrogen cost and try to give some practical numbers. Some years ago, the cost of green hydrogen in Europe was about 12 euro per kilogram, and now is decreasing to 6 euro per kilogram. The European Commission has indicated as target 2-3 euro per kilogram to compete with natural gas reforming. And now we can analyze the cost of natural gas. When the cost of natural gas was 25 euro per megawatt hour, you know that the cost of grey hydrogen was around 1.5 euro per kilogram. But according to the geopolitical crisis, the recent geopolitical crisis, the cost of natural gas has increased to 200 and 300 euro per megawatt hour. And since we have several, let's say, relationships with the petrochemical companies that are now trying to shift from grey hydrogen to green hydrogen, and they have commented that when the cost of natural gas was increasing so much, the cost of grey hydrogen has reached 5 euro per megawatt hour. So that means we are almost reaching the parity. It depends how much is the cost of natural gas. Of course, in US, where natural gas is much cheaper, you know, the goal is 1-to-1, $1 per 1 kilogram of hydrogen. In Europe, it could be 2-3 euro per kilogram, could be reasonable. However, coming back to the previous comment that was really, I completely agree, from where this cost comes. It mainly comes from the renewable electricity cost. It does, at the moment, it does not come from the capital costs. So we need to implement renewables, as commented by the previous speakers, otherwise we cannot reduce the cost of green hydrogen. And we need to achieve a target for renewables of 40 euro per megawatt hour, so we can be competitive with the actual cost of natural gas. Of hydrogen produced from natural gas. Regarding the comment from Angelo, yeah, that's very clear. We need the sustainable processes. You know that when the European Commission published the hydrogen strategy, the cost of iridium has increased the orders of magnitude. So that this is really amazing. We need to get rid of critical raw materials. Otherwise, will not be independent. We need security of energy supply. We need independence. We need to get rid of critical raw materials. That's, you know, the new challenge. So this is the reason why we are moving from PEM technology to AM technology, because we have a great advantage in that case.
Okay, very clear. There is just a couple of questions and then a few questions more from my colleague here.
Maria Lusurdo, CNR Mate. Actually, if I look at the slide in front of us, I would like to draw the attention from the hydrogen economy to the water economy, which is, we are looking at the process and the products, but we are forgetting about the reactants. And our vision is to look at water as an infinite resource, but we also know that there are EU policies protecting now water. So my question is, considering the future and the needs of the energy, how much energy we need at the global scale, do we have enough sustainable water to use in water plants to produce hydrogen? And that's again about sustainability, but from the water perspective, because water is also a resource now to be protected. Thank you.
Then another question from Nicola Armaroli.
Nicola Armaroli, CNR ISOF. I'd like to make a comment, because we have been talking about the cost of producing hydrogen, but let's not forget what happens afterwards, because so far the cost of us afterwards is zero, because hydrogen is used, most of it on site. So there is no problem about storing it and transporting it. And then you have physical limits that you cannot overtake, and you have to be honest about that. Because if you think about energy density, and you think of using liquid hydrogen, the energy density is 3 times less than liquid natural gas. So when today you use 1 ship of liquid natural gas, in the future you will need 3 ships of liquid hydrogen. And you will never ever change this, because this is nature, this is thermodynamics. So if you want to move it by pipelines, you will need 3 times as much energy to make the same trip with the same amount of energy. And this is another physical limit. So my suggestion, but we will discuss that maybe tomorrow, is to consider also what happens afterwards. And hydrogen has a big problems about that, and we have to be very honest on that.
Okay, thank you for this critical view. And
Elio.
Elio, please.
I do not have comments, but a question, a technical question, a scientific question. 3 of you have mentioned the solid oxide electrolyzer this morning. What is the state of the art of this technology? And my question namely is, the 2 channels, the solid oxide fuel cells and the solid oxide electrolyzer, are going and are advancing the same way or not?
Who wish to answer?
Yeah, this is an important aspect, because of course using solid oxide electrolyzers, especially if this can be combined to waste heat, of course we can save a lot of energy for producing hydrogen, because of course the thermoneutral voltage is constant, but the free energy change is decreasing with temperature. So that means it will increase the heat contribution. So if we can get, let's say, combining with nuclear plants, solid oxide electrolysis, we can really save a lot of energy. And this is one possibility for the future. Regarding the technology, there are several companies involved in this field. Sunfire was mentioned as an example in Europe, but I would like to mention also Solid Power, that is located in Italy, in Trento, that is one of the most important European companies producing solid oxide fuel cells and electrolysis systems. And they have reached now the size of 100 kilowatts at the moment. Of course, is not comparable to the size of alkaline electrolysis or PEM electrolysis, but they are progressing very well. Of course, in that case, there is no need of precious metals, and this is an advantage. The critical disadvantage is that you need to operate the system under steady state conditions. That means thermal cycles, redox cycles will be a critical issue for these systems. But of course we have different technologies for electrolysis, and every technology has specific advantages and disadvantages. So depending on the applications, depending on the process, of course we can select the specific technology for that.
Thank you. There is another question from Professor Angela Agostiano.
Actually, two small questions related to the presentation. The one is for Professor Pacchioni, because I was really surprised and impressed by the fact that passing from qualitative to quantitative evaluation of your calculation, you find models that give different models, different value. So I'm asking an experimenter like me that has to start in this field. What's the best has to do? First, look at the literature from the modelistic point of view, but has the possibility to know what's the best results, or is better to do your experiment and then find the correct model that fits the experiment. It looks crazy, but it's something that we always deal with. And the other question for you is the bioproduced hydrogen has some particular application or can be used for everything?
Okay, let me start to answer the question. Of course, we all would like to reduce the amount of efforts we do in the lab when we have to screen for new catalysts. And of course, theory is a powerful tool that we have in our hands. And I think it has to be used, but it has to be used in the right way. So it has to be done properly, including catalysis. Is a very complicated. Sorry, catalysis is a very complicated process. There are a lot of variables. We have to introduce as many variables as possible. If we try to simplify too much the picture, we may lose very important parts. And so that's why in the literature right now there is a huge amount of screening, which to my mind is not so carefully done, and so the prediction cannot be so good. And this is important when we are talking of artificial intelligence, because machine learning, you have to train the systems and you have to use data to train the systems. If the data are not clean, I don't see, but I may be wrong, but I don't see how you can get, because finally artificial intelligence is a statistical procedure, how you can get something good from out of that. So in my view, that is a general point, not only dealing with theory, but also experiments. We need high quality data and high quality experiments and calculations, and this will advance the field. Otherwise, it may lose only focus and maybe just background noise that is not helping too much.
Okay, thank you. Lucy has some questions more.
Please. Yeah, please.
Okay. Hydrogen produced by biological process is highly pure. It don't contain any type of contaminant, so it can be used in various applications without constraint and limitation.
Any question? Yeah, please.
Yes, this is Luca Lietti from Politecnico Milano. I have a question to Dr. Lavacchi concerning the production of hydrogen associated with chemicals. That seems to be a very nice route for the production of hydrogen. But maybe it's a little bit some provocatory question, but the formation of chemicals associated to hydrogen is an advantage or a disadvantage in some way. I mean, if you are producing, for instance, some acetic acid, but this is diluted and maybe you have to purify in order to use this hydrogen, then the cost, the energetic cost associated to the purification to this chemical could be more important with respect to the energetic cost that you have for the production of hydrogen. So, which is the potentialities of the technology to obtain hydrogen associated with the chemicals, and the drawbacks of this technology. What is your opinion?
Okay, this is actually the question. It's not only a good question, but that's the question. So the point here is that we need to investigate more this point. And indeed we have prepared a proposal, a European proposal in cooperation with the University of Manchester that will study the separation processes and will make the energy and economic analysis of the separation. Because for sure, I mean, there will be a huge production of these chemicals, but in many cases these chemicals will be diluted. And so we need to see how to concentrate them and how to extract the impurities you might find in the input biomass. Because it's not only a problem of what you get out of the electrochemical reformer, but it's also a problem of what you put in. Because, I mean, this kind of bioethanol, for instance, how much pure must it be? Because the purity can condition very much the process and even the stability of the system and the purity of the chemicals you get at the end. But so far, I mean, especially the University of Manchester is very advanced in these purification processes for biomasses, and they work in cooperation with a company that is named Arjan Energy. And they actually are, have delivered right now a process for purifying glycerol from biodiesel production, for instance, and so on. But the point is that there is no clear answer at the moment. So for sure we have a low energy process that can deliver the compound, but the separation of the compound from the exhaust reformate is actually a matter of the investigation, and it will be done. Next. We have done some. We have also contacts with a company associated with the Society for Petroleum Engineering, because this is a kind of refinery, you know. So it's part of that. So I think we need to do engineering investigation and to check how to integrate this process into the real biorefinery, actually. Okay, Lucia, please.
Okay, just one question and then a comment. The question is concerning on what you think can be the impact on hydrogen production coming from the modern advance in material science, so the development of catalyst or catalytic system, both in theory and experimental point of view, keeping into account the warning that Professor Pacchioni gave on the quality of experiment and quality of data.
So the question is about which materials are more promising.
What do you think is the impact that the modern advance in material design and development can have on hydrogen? Well, in this big picture that has been provided today by all the comments and all your presentation, what do you think, what role can play? We have seen that there are many aspects that needs to be taken into account.
Yeah, my view very simply is that one of the major advances in the last years are these single atom catalysts. Because if they work, in principle you really need low amounts of precious metals. Now I was very pleased to talk to Professor Strasser, and they told me that these are relatively stable in the catalytic reaction is looking for. So I would like to know your comment. But of course, this is one of the direction that could be promising exactly in the spirit of having something which is sustainable. So it doesn't need too much raw material to be prepared.
Okay, so maybe I can follow up. So I consider the possible impact of material science enormous, for making these devices a reality. But not only catalysts, you also saw that we need ionomers, we need membranes, we need porous transport layers, which are durable and relatively inexpensive, bipolar plates. So I would say the impact of materials cannot be underestimated. Of course, there's also engineering aspects, yeah, to bring everything together, integrate heat and so on. But materials right now, very important, yeah. And as to stability, it depends a bit, of course, on the potential. So I was talking about these guys in the context of a reduction process, and then a reduction of CO2, which is at -1 volt, where everything is a lot more stable than at +1 volt. So my comment that they were stable referred to this potential range of -1 volts. If you use those carbon ones, of course, for the anode, it's not possible, yeah? They oxidize. So it's all relative, and one has to take into consideration the conditions, obviously. But it is a way to save expensive metals, yeah? And iridium, as we only have a few tons available per year worldwide, so even if it's not a cost factor, there may not be enough for a double-digit gigawatt capacity installations, for example. There's literature and calculations that you can only achieve so and so many gigawatt of electrolyzer installation if you place it, or if you do it 100% with iridium-containing electrolyzers, for example. Yeah? So it's not even the cost that may limit it, it's just the sheer availability, because we have this certain iridium loading of, let's say, 1 milligram right now, or maybe 2 per square centimeter of this active area. So it's not even cost sometimes that limit, that also the real availability can limit.
Okay, thank you. So if there are no more questions, I would like to make a comment on what has been discussed today in this first part of the Avogadro Colloquia. So we have started basically from the question from Maurizio on the cost of hydrogen, but I see that we have touched several aspects concerning the raw materials, the availability of raw materials. We have touched the recyclability, the upcyclability, so what is connected to the circular economy aspects. We have touched the economic and environmental sustainability as an important aspect as well. We have seen how fundamental study needs to be combined to support the technological advance. And I would like to make a comment on that probably will bridge to the session of tomorrow. So for sure, cost is important, but all these aspects that we have been touching are important. And as far as the economic and environmental sustainability, I think that this is not only a balance between cost and environmental friendly process and materials, but there should be also a conscience and awareness behind from the social environment and from a political environment to support this vision. I mean, I was thinking of what also Dr. Errico mentioned about the fluctuation on the cost. But if we mean to really consider all the aspects, we should also consider how much are we as a society ready to pay for having not only some hydrogen, let's say, affordable from economical point of view, but also a cleaner environment. So I think that in all the sum of cost, we should also include the cost for what we are ready to pay for having an environmental friendly systems. So I think, in this point of view, the involvement of society and involvement of also governmental institution at any level and in any state, because as has been mentioned earlier, this is really at the global level, needs to be taken into account. And now I think that we can,
So we have just to thank again all the speakers of this, let's say, very, very nice section. Thank you so much to everybody. And we should convene here in about an hour.
So good afternoon to everybody. Welcome back to this afternoon session. My name is Luca Lietti. I'm honored to chair this first part of the afternoon session. We have 3 speakers. initially, then after the coffee break, after other 4 speakers. So the first speaker of this afternoon session is Professor Andreas Zuttel. Professor Andreas Zuttel got the degree in chemistry in Switzerland in 1985, and then the PhD in physics from the University of Freiburg in 1993. He was postdoc at the AT&T Bell Labs in Murray Hill, New Jersey, US in the 1994, and in 1996 he was head of the metal hydride and energy storage group in the physics department of the University of Freiburg. In 2001, he was vice president of the Swiss Hydrogen Association Hydropol, and he became president in 2004. And since 2006, it is head of the section of hydrogen and energy and the Swiss National Institution for Material Science and Technology. He was guest professor at the University of Tohoku in Japan and visiting professor at the Delft Technical University in the Netherlands. And since 2014 is full professor of physical chemistry at l'École Polytechnique Fédérale of Lausanne. Professor Zuttel major research interests are in the field of hydrides and materials for energy storage, and is a very large scientific production with almost 300 publications, more than 26,000 citations, and what to mention is work or his paper on hydrogen storage material for mobile application that has more than 7,000 citations. So, Andreas, we are very happy to have you, and the floor is yours, please.
I guess I will stand here. So, then I don't look too tall. So thank you very much for this kind introduction, and also thank you very much for inviting me to this event, and great pleasure to be here at this very interesting conference in such a prestigious place with so much history around us. And I would like to start also with a little bit of history, tell you about the history of energy. And then this whole talk is about investigation we did for Switzerland. So it's all focused on Switzerland, but many of these aspects we can also use for other countries, you will see. The idea was to investigate on what it technically and economically means if Switzerland makes this transition from the fossil fuels to renewable energy. And you know, there is always, when we talk about the future, the energy transition, it has a political aspect and a technical, scientific aspect. And in Switzerland, the politics is mainly trying to convince the people, think green and then it's going to happen. And we don't need to do something. And now we have a little conflict. There are the people who want to make the transition, are the same people who don't want to change the environment. And this is unfortunately not possible. Even when we go to renewable energy, it will have an impact on the environment, and that's what I show you today here. So here is one slide, the whole history of energy. You can see it started with the hero of Alexandria about 2,000 years ago. He invented the steam engine. However, the Greeks did not understand that this is a steam engine converting heat into work. They just used it as a toy. And you can imagine the world would look completely different if they would have understood that this machine is converting heat into work. But it took another 1,700 years on renewable energy. So this is not something new, we went already through that for quite a long time. Until Thomas Newcomen then invented the piston steam engine, and people realized in England that this engine is producing work from heat, and this has then was the basis then later for the industrialization, which only started when James Watt increased the efficiency and also made an automatic engine, because the engine from Thomas Newcomen was man-operated, so somebody had to open and close the valves the whole day long. This was not very practical, but James Watt then made it automatic, and it became the basis of the industrialization. Then Stephenson put it on wheels, on a rail, and made the first locomotive, which was called Rocket, because it reached a speed of 30 kilometers an hour, and at that time they thought this is fast like a rocket, and were even concerned whether it will damage the brain to move so fast. Now, I came yesterday with the Frecce Rossa, but almost 10 times that speed, and it's really enjoyable that we can move now today so fast. Then the oil was discovered, the car with the explosion engine, then the motorized flights. And then, very interesting, already in 1957, King Hubbard made a model to describe the depletion of oil. He was working for oil companies, and they were interested in how much oil they can get from an oil field. And he expanded that theory to the whole United States. And then he could predict that 1973, the US will go through a situation where the mining will be less than the demand for oil. And it exactly happened in 1973. He was lucky, because the model is not that precise, but he was lucky to hit exactly the year that made him so famous. Then Jimmy Carter supported a lot this Club of Rome, an organization trying to predict on how we're going to work with the resources, and especially what impact it has on the environment. And their main goal was to predict for the year 2000, and then continued this activity. Then Karl Jochen Winter in 1989 proposed to produce the hydrogen in Northern Africa and then provide hydrogen as an energy carrier to Europe. Unfortunately, it never happened, especially because of the political situation. Nobody wanted to invest so much in Northern Africa, but the idea was a great one, and it's already more than 30 years ago. And I will, at the end of my talk, I will come back to that. Then Campbell, he used Hubbard's model to predict the resources of the whole world, the energy resources, and he came to the conclusion that approximately right now we are going through a peak. That means in future we will have less fossil fuels available. Then Mackay, with his fantastic work, The Sustainable Energy Without the Hot Air, a book you can freely download on the internet, where he investigates what energy is used in England and where it comes from and how it could be replaced with renewable. And Klaus Lackner, he was the first one showing a system to absorb the CO2 from the atmosphere, and also, very important, the first one who calculated how much this is going to cost. And he came up with twice the price of the oil in the US. So in the US, they started to panic. They thought there's not possible to have an economy if the oil price doubles. In Europe, we were all released because we thought we're already paying that amount of money for the oil, so here it would not make it more expensive if the tax is removed. And then finally Hans Rosling with his Gapminder, a tool to present statistics, a fantastical tool where you can see developments over for example, the last 200 years, and also then how it's going to change in future. So, yeah, that's the energy demand, the global energy demand over the last 200 years. You can see steam engine first had no effect, then after 1850 started to mine coal, and after the Second World War there was an over-exponential increase. Here was the oil crisis, and then nuclear power in red here and other renewables in yellow came into the play. But still, the big part of the energy is from fossil fuels today. Well, this has consequences. One of the consequences is the CO2 emission. And here you can see about from what the CO2 is emitted, big part for electricity production, and then almost equal parts for mobility, industry, and residential. And so that's the global picture of the CO2 emission, and we are now around 35 gigatons of CO2 per year. Now, in Switzerland, they often talk about we have to fight the climate change. Well, it doesn't matter what we do in Switzerland. We are so small, we will not change the world. We can reduce our CO2 emission and learn and develop technologies and contribute this way, but it doesn't matter whether we stop to emit or not. And this also we have to keep in mind. I will show you at the end a very interesting economic consideration, and there we will realize that unfortunately we're not going to play the most important role in the future, but that is how the world develops. Now back to the energy. Here is the world energy demand is 19 terawatts. You can see 40% of the fuels are used to produce 17% in energy in form of electricity. So this is a real big part, especially in the coal-fired power plants. China has built in the last 20 years 1,000 coal-fired power plants, same amount as we had before worldwide. So they doubled the amount of coal-fired power plants in the last 20 years. And I'm not blaming China for that, not at all. China is also the country that installs most of the renewable energy converter, but they are a large country and they produce a lot of products, and that's why they also need a lot of energy. And then you can see for mobility, for about 4.2 terawatts, and mainly in that part here, very little for the railway, and then some for the flights and ships. And then in residential, we have another 7.5 terawatts for residential. So this is the global picture. And this is also a global picture. Here you see the temperature increase we are observing as a function of the cumulated CO2 emission. The markers here, they show what is measured until now, and then the extrapolation. And we know that there is, due to the radiative forcing, we have that temperature increase, and there is a physical model for the radiative forcing. Very interesting. The temperature increase is more than what we would calculate based on the CO2 in the atmosphere. Now you can see the pre-factor is 2.85, but physically it should only be 1.65. So we have more temperature increase than we would expect just from CO2. Usually it's explained by additional water in the atmosphere, but nobody really knows why this water is there. Anyway, I will also show you another aspect of it. And then you see here the years. And here is 1850, 1993. Between 1993 and 2020, we doubled the CO2 in the atmosphere. And in the coming 27 years, we will again double the CO2 in the atmosphere. Just to get an idea. So this is a logarithmic, an exponential growth, and if the growth continues with 1.5% per year, we will here, in 27 years, we will have twice as much CO2 in the atmosphere compared to today. And you also see here these two lines, the fossil fuels. This is Campbell's model. According to Campbell, we would run out of fossil fuels here in 2047. This is probably a bit pessimistic. We will probably have more than that. And then here is the proven reserves. And that's what, there's a general agreement that this is about the reserves we have available, and this would last until 2073. So this is probably a bit too optimistic, because proven reserves means 30% probability that they are really there. This is not very high. So that's probably too optimistic, this is too pessimistic. Somewhere in between here, we would run out of fossil fuels if we continue to use every year 1.5% more. And that's another very big incentive to go to renewable energy. I mean, we have to adapt to the temperature increase. But when we run out of energy, then we have a real serious problem. We cannot simply adapt and say, in future we live without energy. So we have this time left, and yeah, we all know the goal now is 2050 to be on renewables, and then we would be on the safe side. This is the global carbon cycle here, or the carbon balance. And you see here how much we emit from fossil fuels, from deforestation. Very interesting is that the natural photosynthesis is absorbing roughly 10 times more than what we emit. So this natural cycle is much, much larger than what we contribute. And this is also a chance, if we could work on the forest fires or on the respiration, we could make a big impact, just as a side remark. More important is that fortunately, naturally, half of the CO2 is removed again from the atmosphere. You can see here that's the emission, and that's where it ends up, and only about half of the CO2 remains in the atmosphere. The other half is absorbed by the plants and by the soil and the ocean. That's very good. That means if we reduce our CO2 emission, the concentration will then start to decrease, and basically all that CO2 that we emitted will be absorbed again, because the higher the concentration, the more naturally is absorbed. And so there is a way back, so we are not in a hopeless situation, but currently we are still increasing the CO2 emission. Now let's talk about the more positive aspects. That's the development of the renewable energy production worldwide. And you see here the produced average power versus the year. And for photovoltaics, for wind, for solar thermal, for hydroelectricity, for biomass, and this is the sum of the renewables. And you see, if it continues like it did the last 20 years, we will reach in 2035 already the world energy demand. This would be fantastic. That means here we will be completely on renewable energy. Now, of course, it will not continue like that, because the closer we get, the lower will be the price for the energy and the less income we can generate with it. But it looks very positive, and we can also see that at the end, in a little bit more than 10 years, PV will make the major contribution to the renewable energy. But the PV depends on the sunlight and fluctuates, and there is no production during the night, so we need storage. You see, these are the different forms of renewable energy, the hydropower, solar thermal, geothermal, and they have all different characteristics. For example, the tidal has a different frequency, different oscillation than photovoltaics or the solar thermal. The geothermal delivers continuously energy. The wind also fluctuates in a different way. So the combination of all them, of course, helps to equilibrate a bit the production. However, they are all, except from biomass and geothermal, they are all fluctuating, and that means we have to somehow adapt our energy storage to these energy converters. Now, this is the big picture of the energy conversion, and we heard this morning already about the power to X. So you see here, yellow is the electric part. And in several places, especially also in Switzerland, the idea is now to electrify as many applications as possible, especially mobility and heating. So we'll have completely electrical system. And then here is an electrolyzer that's making the interface between the chemistry and the electricity. And then we produce hydrogen. And of course, we could convert all our applications to hydrogen. But that means we have to change all the applications. And that also means that's not compatible with that. If we have a hydrogen car, we cannot charge it electrically. If we have an electric car, we cannot put gasoline or hydrogen in it. We have to keep that in mind. This is not something we can just shift from one to the other. But we can also take the hydrogen and CO2 from the atmosphere or from the biomass and produce synthetic gas. And then store the gas, and we have already many applications for gas in mobility, but also in residential. And then finally, we can take the CO2 and the hydrogen, do Fischer-Tropsch synthesis, and produce synthetic aviation fuel, because for aviation there is no real other option. For short distances, which is a large part of aviation, we will be able to do that with batteries in future, but not for intercontinental flights, and therefore we're going to need some synthetic fuel in the future too. The big advantage of synthetic fuel as an energy carrier, of course, is we have already all the applications. And then we wouldn't have to change the infrastructure, and it's very easy to store. Most countries have already a big storage which would be enough to store from summer to winter. So that's the big advantages here. But of course there's a big disadvantage, and I will just come to that, all the losses we have to produce these synthetic fuels. Here in the electrical part you see batteries and the hydroelectric power plant. Sometimes, I think it was also mentioned this morning, we have this idea we could do basically all the storage with batteries in future. This is impossible. This is impossible because of the resources, impossible because of economy. In Switzerland it would cost half of the average salary per person per year. So half of our income would go away just to finance these batteries. Impossible, not even we can afford that. And the other problem is, when you look at the space that would take, it would take the same space as all the buildings we have right now. So we would have to double the buildings just to host the batteries. So we can forget. There is no way to do seasonal storage with batteries. We have to find a different way. One possibility, of course, is to go to hydrogen as an energy carrier, store it underground, because underground storage is about 2 orders of magnitude cheaper than above the ground in steel tanks or in metal hydrides, and then use the hydrogen in combined cycle power plants to produce, again, electricity. Then we can electrify everything and do the seasonal storage like that. So that would be the connection then of hydrogen back to the electricity. And of course here we could also use the heat produced from the power plants to provide heat to the houses in the winter time. Same, of course, for synthetic gas. We heard also this morning the energy density of synthetic gas is 3 times larger than the one of hydrogen, which is a big advantage. It means 3 times less volume. However, here is also a conversion loss. And here I show you now, this is when we start with photovoltaics, for example, battery, then hydroelectric power plant, then go to hydrogen production, hydrogen storage, and then to the hydrocarbons, and finally end up with the fuel. And if we convert it back to electricity, we are here. And so you can see in the worst case, when we do the whole chain to the fuel here and convert it back to electricity, we have about 11% of the energy left. And that's, of course, the big disadvantage of just going here. That's why it makes sense sometimes to stop before. We have here often the argument renewable energy is much cheaper than any other form of electricity which is available right now. And when I say right now, I mean half a year ago, because now many things have changed and we have to also take that into account. But renewable energy, the cost of renewable energy depends very much on when and where we consume the renewable energy. If we consume it directly from the photovoltaics, it's very cheap. But already when we put it through the grid to the neighbor, it becomes more expensive. When we store it in a battery or then through the grid, and then when we do a seasonal storage in a hydroelectric power plant, and then we end up with that cost. And you see there is more than an order of magnitude higher cost. So we cannot simply say it's always cheaper. It's sometimes cheaper, but sometimes also much more expensive. And the economy for energy will have to adapt to that situation. So we have to find a system where we buy sometimes expensive electricity and sometimes very cheap one. Now, Switzerland has made the decision in 1912 to go in the railway from coal to electricity. This was very wise. They also made a report about that, which is also available on the internet, and investigated all the advantages and disadvantages of a coal railway compared with an electrical one, and came to the conclusion they have to electrify. And they did that without having the electricity. So they made this decision before they built all the hydroelectric power plants. And this is a bit the situation we have right now too. We decide we want to emit less CO2, we want to go away from fossil fuels, but we don't have the electricity, the necessary electricity. And then they built all these hydroelectric power plants, and before they stopped the steam engines. That's also important for the development right now, because if we now change too quickly the application and we don't have the electricity from renewable, it will be fossil again. That's what happens in Germany for example, right now. They continue with the coal-fired power plants. And that's, of course, not the goal, because then we have, again, the CO2 emission. So we have to do that change in a wise way. So in Switzerland, we are a bit in a comfortable situation that the part was already changed, and we went already through that. And then, after Fukushima, same in Germany, there was this decision to stop with the nuclear power, and then we have signed the Paris Agreement, which basically means that we, until 2050, we have to become zero CO2 emission. Now, this is the energy map of Switzerland. There are four sectors here. The first one is aviation. That will be synthetic fuel in future. There is no other way. Then the big part here, that's what goes to the individual mobility and the residential. This can be done, of course, with electricity or with hydrogen or with synthetic fuels. Then we have a contribution from biomass that will continue. The nuclear power is electricity. That should also be electricity in future, of course. And then we have already a certain fraction from renewables, mainly hydroelectricity, that will also continue. So we have these two parts here where we have to do the big change. And then finally, we're going to have everything from renewable and mainly applications are electrified for individual as well as for the public transport. But we have seasons, and this is, of course, that's a bit the difficulty in this analysis. That's why we cannot do it globally, because it depends very much where you are. And here in Italy, you are in a completely different situation than the Swedish, for example, or in other places. So you have to look at the location and see what happens there, and then the amount of storage depends very much on how strong the seasons appear. And you can see in Switzerland we have 4 times more solar intensity in summer than in winter, and that means we have to shift a large part of the energy from summer to winter if we want to remain on renewables completely. Now that means in the energy cake here, we have about half of our energy consumption that is fossil, and that has to go to either electricity on this side here, or synthetic fuels or hydrogen, and then the nuclear power also has to come from photovoltaics. If we electrify, and that's the major argument for electrification, then we can save 33% of our energy demand, just because of the increased efficiency. So without changing behavior, just going electric means we can save all that energy here. However, you see it here, we have to store about 20 terawatt hours per year of energy from summer to winter. And that's the big challenge in the whole transition. Much more than building all the renewable energy converters. What does it mean then in technically and economically? This here represents the roof area in Switzerland. So the area of all the roofs which can be equipped with photovoltaics. That's the battery storage we need locally, because if we don't have local battery storage, we would have to increase the grid capacity by a factor of 10. This is also basically impossible. We already have a lot of grid, and so then we need the local batteries to buffer the day-night, and then we could use the hydroelectric power plants to store the energy seasonally. That's what we need for the nuclear power to replace the nuclear power plants, and that means building 4 times the largest hydroelectric power plants, Grandissance, we have in Switzerland, which has 1.5 terawatt hour of capacity. And well, it's difficult because there are not so many valleys available with the necessary height, so that will be a challenge. Now, if we also electrify that part, then we need another 2 times the roof area and another 9 times this largest hydroelectric power plant. And you can already see this is not technically not impossible, but a real big challenge to realize that. Economically, we are currently paying 3,000 Swiss francs per year for energy, so it would be only slightly more expensive economically, no problem, but technically a big challenge. Okay, now we have talked this morning about it. We go to hydrogen and store the hydrogen. And then you see here we need then 6 times the roof area because of the efficiency loss when we produce hydrogen and convert it again to electricity. Then we need a much larger battery, and we need 25 times the Gotthard base tunnel just to store the gas. And this is impossible. You know, it took almost 30 years to build it once. And it was a big investment, a big construction. To build that 25 times, impossible. So we have to find a different way here. And then finally, 12 times the roof area, such a big battery, and then we could produce 94 million barrels of oil and then store the oil from summer to winter. And of course, you can see here the annual cost then will increase almost a factor of 3 from the electrified system. So there is on this side an economic concern and here a technical one. So both solutions are not easy to realize. And this, it's showing you here, we have no reserves. This is just what we need to make it run. The reserves, then we have to build in addition. Now, this looks like a very precise calculation. The calculation is not that precise, of course. You can see here, these are 2 places. Zurich as somehow from the photovoltaics, the worst place in Switzerland because they have a lot of fog during the winter, and Zermatt as one of the best one. And then you see the difference is plus minus 4 terawatt hours on 20 terawatt hours. So we have quite a huge error in this approximation. But it gives us an idea of how large it can approximately be. What can we do? Well, this is something politically, they don't like it at all, the politicians. They always say, yeah, we're going to trade. You know, when we have a lack of electricity in winter, we just import. But they forget that whole Europe has winter at the same time. We're all going to have the same problem at the same time. This is not that somebody will have summer and then plenty of energy available. And so we really have to think on a Europe where each country is self-sufficient. Only then it can, and then we can still trade if it's necessary. But we should at least try to get self-sufficient, because otherwise there will be a big lack of energy in some periods of the year. So what we could do is increase the dams by 26%. They have a V shape in 2 dimensions. So if we increase the dam by 26%, we can double the storage capacity. And then we could store another 9 terawatt hours of water that is available. You know, we cannot increase to any size, because if there is no water, it doesn't matter how big the lake could be. But this water we have available. And then we can also use an additional 12 terawatt hours of biomass. And then we could use a part of the photovoltaics and of the hydroelectricity from the rivers to produce hydrogen in summer, store that hydrogen, and then use it in the combined cycle power plants in winter. And all that is, at the limit, is possible, but again, no reserves here. This would be only in the ideal case, it would just work, under the condition that we can realize all that. Well, this is a problem. We also need 4 times the roof area, so that means once the roof area plus 3 times this area somewhere in the free land for photovoltaics. And then that's the solution with the power plants. That's what I just presented. Or, of course, we could build nuclear power plants again, and then we need much less of renewable, and that's then the other option. Now, I'm personally not a big fan of nuclear power, especially not of the uranium fission reactors, because uranium is also limited, and we can easily show that's maybe for some countries a solution, but not a global one, because globally we would need about 4,000 additional nuclear power plants if we want to replace the fossil fuels. So there's no way to do that. We would run out in a few years of uranium. But there are fourth generation reactors which don't need uranium anymore, which could even burn our nuclear waste we have right now and produce short-living isotopes. And this is all hope. Huh? They are not installed, they're not on the market right now, but that may come. And that's why we should not completely forget this solution, at least to make the transition more easy. And if we have these power plants, either with hydrogen or the nuclear power plants, then we can produce the energy over the whole year with about 3 times the roof area in Switzerland, and we could even produce from the biomass the fuel for the aviation and cover all our energy demands. So there is a solution. It's demanding, technically, but there is a solution. However, there was recently this very interesting paper from Germany. They investigated the last 35 years of sun and wind, and then calculated how much energy was missing as a function of the duration. And this is very interesting. You can see here the maximum is around 60 days. That's 2 months, where there would not have been enough production. So that's why we need these reserves. So we cannot live in future on a system which is just delivering the energy. We need reserves. And currently, for example, in Switzerland, we have 4 months reserves of the fossil fuels. Even they arrive every day. But still, there is by law, we have 4 months stored. And in future, for renewable energy, we need also a storage for several months. And that's why even if we import the energy, it doesn't mean we don't need any storage. We still need to build the storage. Well, the EU has recently, it's about half a year ago, published this idea of producing hydrogen with photovoltaics in Spain, and then providing that hydrogen to the rest of Europe. That's a great idea. In Spain is also a lot of space available. However, you can see it's quite a big area that has to be covered, 42,000 square kilometers with photovoltaic in order to provide hydrogen for whole Europe. And when you look at the annual production of photovoltaics in the year 2020 was 1,000 square kilometers per year. So already that would take 42 years if Spain will get all the photovoltaics produced in the world. But this is increasing, this is all growing, so there may be enough in future. Also many electrolyzers, 100,000 electrolyzers would have to be installed each year until 2050. So it's just to have an idea of the dimensions. It's really a lot, especially because there were only 200 installed in 2020. So you see there is a huge gap. But the most important difficulty here, the most important challenge is this one here. We would have to have a storage of 4,000 terawatt hours from summer to winter, because even in Spain there is a factor of 4 between the solar intensity in summer and in winter. Even we think that Spain is always sunny, but there is the same big difference. And so this is an idea, but very, very difficult to realize, especially that storage basically impossible. There's another option. Australia has summer when we have winter. And Australia has plenty of area where nobody is living. And they have a very high solar intensity, more than twice what we have. So we could also produce hydrogen in Australia, ship it here to Europe, then make the gas, put it in a pipeline, and fuel our power plants. However, when we import, still we need 6 times here the Gotthard-based tunnel as reserve, because we cannot completely rely on that import. So we need this reserve, and there's still a big challenge. And the final cost of the electricity is also challenging. That would be about €1 per kilowatt hour. Well, we are getting used now to these costs, but that has an implication which I will just show you in a second. Here, this is now the end of my talk, and this is energy demand per capita versus GDP per capita for the whole world. we are now 8 billion people, but we should keep in mind 7 billions are living below this 20,000 euro per year per capita. A big part of the world population is here. And there is only 1 billion making the whole rest of the figure. And you can see here where the industry produces the income, then we have a linear dependency with a slope of $0.6 per kilowatt hour, or 0.6 euros per kilowatt hour. That means that's when the industry has 1 kilowatt hour of energy available, they can create an income of 0.6 euros. If the energy costs more than that, the industry turns empty and doesn't create any income anymore. This you can verify in the financial crisis 2008. That's exactly what happened then. The oil price was more than that value, when you take 25% of efficiency, and then we got a financial crisis. Because then you can work as much as you want, but it doesn't create any income anymore. Now, the positive thing is, when you see where Europe is here, and for a long time Switzerland was leading here, and even decreasing the energy demand by increasing the GDP. However, you know, I'm not proud about that. Our government sometimes says, yeah, we know how to do it. No, we just import all the energy-intense products. And we only see primary energy here. So these products are not in the plan. So this is not a recipe for the whole rest of the world. That works for us, but not for everybody else. But there is such a development here. And very interesting is Ireland, in the last 6 years, they bypassed Switzerland here and increased enormously the GDP. So apparently you can increase the GDP without increasing the energy demand. And we should all look at Ireland, what they did right. Obviously they did something very right. When you look at the last 20 years, they almost doubled the GDP. And this is incredible. Then there are other countries like Luxembourg and the United Arab Emirates, they consume a lot of energy and have also a lot of income, I have to say, but you see they are far up here. So what is the consequence of that? We heard this morning, somebody said, are we willing to pay more for energy in order to go to renewable? And that's of course good if we are willing to do that. But again, we have to stay below that, otherwise we have to change the whole economy, the whole industry. There has to be another way of creating much more income per energy. And now when you look at the energy storage, here you have the electricity limit, and then here is this GDP limit. And there are some storage methods in between, like batteries here, the metal hydrides. But for example, the synthetic fuel is above here. So now, even if we are willing to go to synthetic fuel, it will not solve the problem because we could not create any income anymore. Energy would simply be too expensive. And this we have to keep in mind. We should also economically survive this transition. Well, the good thing is that Australia has the plan now to really build up this photovoltaics. You see here, this is what we need for the whole world. This is 1/8 of Australia, which is it's a lot. It's 1 million square kilometers, but possible, technically possible, and the space is available. And then they could produce hydrogen and provide it for the whole rest of the world. And they would make, in a rough estimation, about 10 times the income they make now with coal. So it could also be economically very interesting for Australia. We have published all that, what I told you here in this paper. If you are interested in going into details, have a look there. Again, it's the special case of Switzerland, but can be adapted to other countries, of course. And yeah, I think it's not that bad. Do I have 5 minutes? Just quickly. You know, I showed you before the car from Benz with the explosion motor, which is always taken as the first car with an explosion motor. But the first one was this one here, running with hydrogen, and it was François Derivat, a French officer who came to Switzerland and built a car on the principle of a cannon. So he was shooting up the piston, and then on the way back by gravitation, he moved the car. And he was using that car with hydrogen and air already 1807. That was the first such hydrogen application in mobility. And this car, I read, is in the Technical Museum in Milano. A replica, of course, not the original one, but maybe very interesting to have a look at that. And then we had the build-up of the hydroelectric power plants. For a long time we had the world's largest electrolyzers running in Switzerland. We had the Marcus Fridley, an architect who built the first energy reduced buildings. He converted his house completely to hydrogen. He cooked with hydrogen, he had a washing machine running on hydrogen, the heating, of course, he had also 2 cars running with hydrogen, all that already in 1991. Then we have demonstrated this snowmobile in 2004 with a metal hydride and explosion internal combustion engine. Then my colleagues developed that street sweeper with hydrogen. That was the first car that not only didn't pollute the environment, but even cleaned the environment. So that's the ultimate mobility. Then we have this self-sufficient house here, which also stores hydrogen for the seasonal storage. And it works. There are 6 families living there. It works, but I have to say they are living in a special way. For example, they almost never cook. They live mainly from the pizza service. Because, you know, this works fine. You can look at your energy demand at home, but heating and cooking and hot water, these are the main consumers. And then when you want to run such a house only with the photovoltaics on the house, then that means there's no real cooking anymore, or just fast food. And that's a bit also something we have to keep in mind. Then we are importing these Hyundai hydrogen trucks. This is a bit already going, unfortunately, in the saturation with 48 trucks, but we'll see how this can continue. And we have a company now producing this megawatt-hour storage systems based on hydrogen. And that's there you can see there is really a market for these storages. And then, that's my last slide here. I just want to announce we have a symposium on hydrogen and energy. Will be in last week of January next year. Deadline is today, but if you register tomorrow, we'll still accept your registration. And you're very welcome to come to Switzerland. It's in a beautiful place, as you can see here. And they are using mainly biomass to provide the energy to the hotel, so it's almost renewable energy. Thank you very much for your attention.
So thank you very much, Andreas, for this very nice overview about the energy demand and consumption. So we move to the next presenter. This is Professor Marcello Baricco. Professor Marcello Baricco graduated in chemistry in 1982 and got the PhD in chemistry in 1987. He spent several periods at different universities, including Brunel University, Uxbridge, Slovak Academy of Science, University of Birmingham, and others. He reached the position of associate professor in 1998 and then full professor in 2004 in the University of Turin. And now is full professor in material science and technology at the University of Turin, where it has been also deputy rector at the same university. The research activity of Marcello is mainly based on material science and technology. In this topic has been published more than 350 papers, and the main topics include microstructure and kinetics of phase transformations, thermodynamic properties and phase diagrams, and hydrogen and energy storage. So, the title of the presentation is Challenges for Hydrogen Handling. Please.
Questa.
Okay, thank you very much indeed for the kind invitation and for giving me the opportunity to be here today on presenting our recent activity on hydrogen. Let me just start with some logos, just to present what we are doing and what is the organization we are linked with. Of course, ENSTM, that is very much engaged on hydrogen. I would like to show this logo that is IH2IT, that is the Italian Association for Hydrogen, that is merging industry and academia on hydrogen. This is a logo for the EIA activities in the frame of hydrogen. Together with Andreas, we are together in this organization. This, I think, is one of the main logo we have right now. That is the partnership we have in Europe that is dealing with the money related to hydrogen for the projects. In the frame of this organization, that is the Hydrogen Europe Research, so any university or let's say research center is welcome to come and to join that. ERA is another big organization related to renewable energies, and there is a specific joint program on hydrogen and fuel cell, so everybody is welcome to that. And then I will be back on this logo that is linked to a project that we are dealing with in this time. Okay, so the hydrogen cycle basically is what we discussed, looking to the green hydrogen. The idea you have renewables, then you have the electrolyzer we already discussed this morning, but the people this morning was asking what to do with this hydrogen that we are producing. And this is what I call handling. In other ways, what we can do with this hydrogen that later on have to be used in fuel cell or in other application in order to close the cycle. Now, the point is, before some years ago, let's say, before what I call the Hydrogen Day, middle 2020, when Europe say, oh, we want hydrogen in the future, actually this was an handling of few amount of hydrogen. But now people is looking for tons of hydrogen. So how to manage such a huge amount of hydrogen that we have to manage? So the first idea was to go back and then to ask to a colleague of mine, asking, oh, what to do with this hydrogen? So I went to the main building of my university, and I was basically asking to Amedeo what to do with such a huge amount of hydrogen. He said, oh, I apologize, but I already say that if you increase the amount of hydrogen, you increase the volume. So there is no way. So the idea is how to manage in order to reduce the volume and then to have an efficient way to handle hydrogen. So basically what we are dealing with is how to, let me say, reduce the volume of the hydrogen. What I'm used to say is 1 kilo of hydrogen is about 11 cubic meters. And to make the fill of your Toyota Mirai, you need 3 kilos of hydrogen. Means that you definitely need the way to manage properly such an amount of hydrogen. So what is the possible let's say, approach? The first one, of course, is to compress it. That is obvious. The second possibility is to reduce the temperature and then to transform into liquid. Then you have to try to set up some reversible reaction that is linking in some way hydrogen with some other elements like carbon and nitrogen. And finally, of course, you can find a solid that is able to, in some sense, to, let's say, reduce a bit the repulsion that is in the gas phase. So I quickly like to run on these different options and then to show up what are the challenges that we have nowadays when we have to talk with tons and not just on few grams. But what are the main requests? Of course, the first time is to have a high gravimetric and volumetric density. That is the main issue. The second one is to play close to the room, let's say, conditions, let's say, ambient temperature and pressure. Then, of course, we need a solution that is able to put hydrogen in and out quite easily, quite often, without any trouble in the number of cycles, and everything has to be done fast. And, of course, what the people is asking is has to be safe and cheap. So, at the end of the day, this is the challenge that we have to deal with in order to manage in the real life such a huge amount of hydrogen that we are hoping to have in the future. Pipelines, of course, this is the first approach. This is very much pushed in Italy, at least from a very big company. This is just an idea of what is the net we have of already existing pipelines in Europe. The big issue is, of course, the idea is to put hydrogen into the methane and then to run around, but at the end, when we are somewhere, we have to get it out. So there is a huge issue on how to separate hydrogen from methane. Another big issue is related to the role of hydrogen into the pipelines. There is a risk of hydrogen embrittlement, and this, in some sense, is what is very much limiting the actual normatives. The bad news is that in 2022, the fire brigade in Italy say that no more than 1% of hydrogen into the pipelines. That number is a bit higher in other countries, but that is what we have to deal with at the moment. But it does exist a pipeline only for hydrogen. Well, actually, it does already exist in the north of Europe, that is in Netherlands and in Belgium. And is the news of a few days ago where actually Ursula was going to Spain and to say, oh, we are basically building up a big way from Africa to Europe to deal with hydrogen. There are some projects that are hoping to manage such a huge net of pipelines of hydrogen in Europe, but definitely this is the big, the main way to transfer a very huge amount of hydrogen. But one key point is pipeline will be crucial if the model in the future will be to produce huge amount of hydrogen somewhere and then to distribute around. But in this way, we will need probably very high power electrolyzer, megawatts, I don't know if we could call it gigawatts, but in any way, very big power. If the model will be a very distributed production, probably the pipeline will be not so crucial in the real future. So we have to store it somewhere, and as Andreas already said this before, underground, that is a solution. Very cheap, huge amount. You basically have to find a place to put there. It does exist. Such a kind of places that do exist. That can be already existing, let's say caverns or something that can be built. You could also think to put some container underground, and there is a lot of experience already running. The good point is that, of course, you could store at the tons level. You have a very low compression cost because you can put hydrogen at very low pressure there. But nowadays there is still a need of normatives. In Italy, basically, this is fully forbidden. No way to have any experiment in this direction in Italy because that basically is not allowed. Of course, there is some challenges. You have to have low construction costs. You need no leakage around, no contamination. Some projects are running in Europe. Of course, then you could increase the pressure and then you put hydrogen into a tank. This is what is already available from the commercial point of view. The story basically says there are 4 types of storage tank for hydrogen, and nowadays basically in the cars we are playing with the type 4. That is basically a sort of composite material with some liner around, and that they can reach up to 700 bar. This is basically what is available right now. What are the challenges? Well, the first point, of course, the storage capacity of the system strongly depends on the pressure that you want to use, because if you increase the pressure, of course, you have to increase the thickness and the kind of material. And then the other point that, of course, to go up to 700 bar, you need to compress, and compressing it costs from the energetic point of view. There is, of course, some safety issue, even if they are in some sense managed. And of course, you have a pressure dropping when you are filling the tank at this pressure. Okay, that's basically the challenge. The material, we still need a research in the materials to do that. They have to be recyclable in some way. And one point that quite often companies are asking is to have tanks with the sides different from cylinder. So, of course, you need material that is able to take 700 bar with a size that's not a cylinder, but can be accommodated in the train or whatever. So that's, in some sense, is a challenge. Liquids, of course, this is a solution that is already available in the market, very well known. What is the good point of liquid hydrogen? That's strongly the gravimetric density strongly depends on the size of your container. If you increase the size, if you are able to do a huge amount, in some sense you could go towards the, let's say, theoretical density of the liquid hydrogen itself. That is a number quite interesting. So definitely this is one of the main options that we are right now, mainly for transporting hydrogen between different continents. But of course we have needs to liquefy, that is costly. We have the risk of boiling off, so we have to manage the boiling off in some way in order to avoid to lose hydrogen around. And of course, in order to reach such a huge value, you need big sized tanks. And that, of course, is a challenge. Carriers, that is the last option. So to stick hydrogen to somewhere. I borrowed this plot from Andrea. Thank you, Andrea. That is basically showing the volumetric density as a function of the gravimetric density. So what is the situation? If you deal with the compressed gas, you are in this area, you can reach, let's say, interesting gravimetric density, but from the point of view of volumetric density, you are in a very low level. This is the theoretical liquid hydrogen. This is, some sense, is the trend of liquid hydrogen if you increase the amount, and we know that if you have a huge amount, then you can reach the theoretical direction. But in the top, we have carriers, let's say something that can be linked with hydrogen to produce, let's say, new compounds that can be used to be transformed. Basically, on the right, we have molecules or system that can be linked with hydrogen with a covalent bond. On the other side, we basically have hydrides, but on this side we have very low gravimetric density and this very high gravimetric density. So the idea is to play in this range for the stationary application, in this range for the mobile applications. So how to translate this in the real life? One of the big pushing is towards what we call chemical hydride. This is very simple molecules, we know. Ammonia, methanol, formic acid. Ammonia is nowadays seen as one of the main energy carrier. Of course, we are quite used to play with ammonia, but all these tons of ammonia nowadays are produced with the gray hydrogen. So what to do with the production of ammonia with a green hydrogen in order to synthesize and then to use that to move around. But for instance, the world of the ships, they are definitely looking to ammonia. All molecules that have some carbon around, not very liked by Europe, this is my experience, so in some way, all the time that you use a molecule where there is some carbon around, of course you have to deal with all the possible CO2 emission. In any case, that is basically what we have right now, that are liquid, and liquid is very much worried by Europe, or at least from the industries. So this basically are a very good option for carrying on hydrogen around. Quite often we need catalysts, and there is plenty of people very expert on this point, but they are commercially available. Of course, all the time that you put hydrogen to some other compounds, you lose a bit in the energy density. This is what we know. Even if this morning somebody was mentioning about the difference in transporting hydrogen or methane in terms of energy. Nowadays became very popular what we call liquid organic hydrogen carriers. The idea is simply to have a molecules that can have, let's say, double bonds and then single bonds. In this way, you could move hydrogen quite easily. Well, there is a very, let's say, a company in Europe that is promoting such a kind of approach with this molecule that is very well accepted. There is again a liquid phase. The liquid phase, this is very welcome. Quite often you need different temperatures to manage absorption and desorption of hydrogen inside. You can have quite high gravimetric density, up to 6%, but quite often you need a huge amount of catalyst, and quite often you need a different catalyst to go in one side on the other side. But they are commercially available. My personal opinion is that organic chemistry is so wide that probably there are more than this single molecule. So my message is try to find new molecules because there is plenty of room for going in this direction. Absorption is another way. People was working a bit on this. The idea is, of course, to stick hydrogen with a physisorption. MOF is very well known, zeolites, carbon nanotubes. There has been a lot of work on this direction. what are the main challenge? Of course, you quite often need low temperatures, you quite often obtain very small volumetric density, and to my understanding, there is no commercial availability of such a kind of approach. So there is a lot of hopes on this direction, but no results up to now from the real point of view. Absorption, of course, that is in metal hydride, that is probably one of the most explored approach. The idea is simply to put hydrogen in the solid solution in a metal hydride, then to start to form an hydride, and then to have a new phase. Of course, you have a thermodynamics, that pressure as a function of the amount. You have a solid solution, then you have a sort of range where you have two phases, and then you go to the pure hydride. And this plateau, that strongly depends on the temperature, of course. And thanks to the Van 't Hoff plots, you basically have the key parameters, thermodynamic parameter for such a kind of reactions. I would like just to stress that entropy usually is going close to 120, that is typical entropy change from a gas that is becoming a solid. But enthalpy is placed in a key role. In order to play close to the room temperature and room pressure, you need an enthalpy that is close to 30 to 40 kilojoules per mole of hydrogen. And that is the challenge, to find material that is light, that is stable, that is good, and have an enthalpy close to that. The second message is, because you have an enthalpy change, you need a thermal management when you play with hydrogen in hydride, and that is quite crucial. That, in some sense, was an attempt to answer with a project that we are coordinating that is called HyCare. And the idea is basically to play with about 50 kilos of hydrogen to be stored in a metal hydride. And it means that basically we need about 4 tons of powder to produce such a kind of storage. But the key point is to manage the hydrogen storage together with the heat storage. So the matter is, when you go from, let's say, from the metal to the metal hydride, you usually go to the low temperature, high pressure, and then you have the hydride, low pressure, high temperature, you have the metal. And then you move one side to the other. The challenge is to stay in the same temperature and then to go up and down in pressure, taking into account that you have an hysteresis effect. So absorption and desorption quite often have a different level. So the idea is, okay, when you go up and down on this direction, you have a thermal exchange. When you produce heat, when you charge your tank, where this heat is going. The idea is taken by a phase change material that is taking the heat, is maintaining the heat. When you need hydrogen back, you ask to phase change material to provide you the heat, and then hydrogen is coming out. In this sense, you have an efficiency of the whole system. So the concept is very simple. You have the charging, then the heat is going to the PCM. When you want to have hydrogen back, the PCM is going heat to the system. That is basically the idea. In order to do that, of course, we need to produce tons of powder metal hydride. We selected such a kind of composition that has been produced in tons level with an industrial approach, and that has been taken in sort of pellets. And these pellets from tons, they have been inserted inside of the tank. I don't have the time here to go into the detail, but one of the key points is that when you produce tons of such a kind of metal hydrides in an industrial scale, you have a lot of effect of oxides around. You have possible different second phases. We studied carefully such a kind of matter that is very much linked to the what we call activation process. Let's say that the material at the beginning need to be activated in some way to start to go up and down with the hydrogen. So there is a challenge related to the moving from the lab up to the industrial scale. And this is demonstrated with this typical PCT plot, where you have the amount of the pressure of hydrogen in equilibrium together with the amount of hydrogen inside the tank. What I like to stress, this is the behavior that you have in the lab, and the behavior you have in the tons level that is a bit different because of the oxide, because of the different possible contamination. But the main message is, if you get hydrogen from an electrolyzer about 30 bar, and you have to deliver hydrogen at about 1 bar to a fuel cell, actually you have to stay in this pressure range, and then the amount of hydrogen that you can put in the alloy is a bit limited. In our case, such an amount is around 1%. That for a metal hydride is not so bad, but in an absolute way, of course, is very small amount. That is the tank that is basically ready. We organized already in April the event to showing that the system is working, so everybody's working in Paris to see the tank working in a proper way. This is the place where we have metal hydride, this is the place where we have PCM, and the total amount there is about 50 kilos of hydrogen. As already mentioned by Andreas before, the metal hydride can be also used to compress. The idea is very simple. You put hydrogen in at low temperature, and then you increase the temperature of the system, and that is delivering hydrogen at high pressure. And this is a typical approach for what we call a metal hydride compressor. The idea is very simple, that you play it back up and down with the Van 't Hoff plots. If you have, you play with two different temperatures. So you put hydrogen inside, you have a thermal fluids that is basically managing the system, then you heat up, and then you take out the hydrogen at a much higher pressure. This has been already demonstrated. That is a way, if you select properly the alloys, that is a way to have a compressor at a very cheap cost, let's say, without any moving parts, but of course you need heat going up and down. In any case, we set up a sort of metal hydride-based refueling station. The idea with this project was basically to set up a system that is filling up at about 200 bar, 300 bar suitable tanks. And these small tanks have been used to put in a drone that is a sort of hydrogen drone that is, again, a request that is around because the hydrogen drone are able to increase the flying time. In our case, that was 70 minutes. And, well, this is a picture just to say that the drone was able to go up and down in a proper way. Okay, but before going to the decision if this option are good or not, of course, as mentioned this morning, you have to take care on what is the impact. So for this reason, we did basically a couple of approach in using life cycle assessment of the system in order to check if there is a strong environmental impact of the different approach. What I like to mention here is that all the time that you deal with some new technologies, quite often in the database that you have available, there is no data. So in some sense, you have to build up numbers, and that is actually an effort that you have to do that. Well, basically the approach was very typical of LCA. This is the results we have on compression. So the idea is that the blue line, you have a comparison of the metal hydride compressor with the air booster and the generic hydrogen compressor that you can find at the market. Well, actually there is an increase in the impacts, in this case, if the CO2 production as an indicator. But the big issue is related to the heat that you need to go up and down in the system. So if, in any case, with a metal hydride compressor, you are able to get heat somewhere, maybe lost heat, of course, this impact can be going close to what you have in the standard approach. But if you do the same exercise, comparing a solid-state hydrogen tank with the commercial ones, the big issue is that in the commercial one, you have to compress up to 700 bar. But in a metal hydride hydrogen tank, you don't have to go such a high pressure. So in some sense, if you compare the solid-state hydrogen tank with the type 3 or type 4, of course you have a higher effects from the point of view of the materials on the, let's say, of the components, but you have a lower impact related to the energy that you have to deliver for the compressor. And then at the end, the impact is comparable. So the message is, from the point of view of the impact, the technology is actually affordable. Let me conclude just to say that these are the options that we have nowadays for handling hydrogen. Let me summarize: low pressure gas, underground, high pressure gas in hydrogen tanks, liquid hydrogen, linked to the chemicals, liquid organic hydrogen carriers, adsorption, and hydride with absorption. But there is a huge of parameters to be taken into account. I already mentioned some of them. Of course, how to manage huge quantity tons, how to have high gravimetric and volumetric density, how to have a sort of shape conformability, how to have a huge efficiency, avoid to lose energy around, what are the charging time up and down all the time, how much is reversible, if the system is sensitive or not to the quality, how to manage from the thermal point of view, what is the life cycle that we already discussed, what are the materials around, how it is stable over time, how much is available, how much is safe, how much it costs, and let me just conclude how much it is accepted by the people around when you have different options to put on the table. Okay, in order to go towards this challenge in our university, we set up a group of people coming from different departments that is, we call H2 et Unito, and that is a group of people that is dealing with hydrogen in our university, and we are very welcome to collaborate to anybody that's maybe interested on this point. I think I can stop here, and I thank you very much.
Thank you very much, Professor Baricco. We can go now to the next speaker, who is Alessandra Samson. Alessandra took the master degree in industrial chemistry in 2000 at the University of Padova, and then in 2003 got the PhD at the School of Industrial and Manufacturing Science at the University of Cranfield in the UK. And since 2008 is responsible of the group of materials and processes for energy at the ISTEC, Institute of Science and Technology of Ceramic Materials. Her scientific interests are in the design and engineering of ceramic materials, with particular focus on the preparation and characterization of ceramic materials, and on this topic she published more than 100 publications on international journals. So please, Alessandra. The title of the contribution is Perovskites are cornerstone for the development of sustainable hydrogen technologies. Please.
Thank you very much for the kind introduction, and thank you very much for the scientific committee to give me the opportunity to be here today. We are back into the material science and speaking about perovskites. Perovskites, as a dear friend of mine said to me this morning, is very ancient materials actually, but I'm stealing the motto of the 100 birthday of the CNR, saying that we are back to future. So perovskites are very interesting material. They are basically coming from titanium, calcium titanate, and it's basically a body center structure where of AB X3 composition, basically, where the B side is in the center of octahedra. And these octahedra are basically the main actor on the perovskite. Perovskites are originally inorganic oxide one, and they are very well known for different applications for electric generation and conversion, and more recently the allied perovskite, where the X anion is actually an halogen material. This is well known now because they are the base of the new perovskite for photovoltaic application. It's a very interesting structure because it's very flexible. So you can play around with the structure, either with the A, the B side, or the X side, and you can change the cations and the anions, and with that you can tune the different properties that this material can exhibit, especially conductivity. That is a very important property for energy application. But it has another very interesting property, is that if there is an S-site underbonding, this is causing a rotation of the octahedra. And this rotation of the octahedra is changing again the structure and it's changing again the properties. On top of that is prone to layering. So this perovskite layer can be layered among themselves and with other kind of materials, like rock salt layer or bismuth oxide layer, giving origin of different family of parenting structure that are well known for energetic application like Radisson and Popper that are well known, for example, for superconductor, the Diode-Jacobson family, double perovskite, or Aurelius-based perovskite. Perovskite are well known as electrodes for solid oxide cells, a technology that were mentioned this morning and is very interesting for the production and use of hydrogen. And why they are using there? Because they are very interesting property of conduction. So they can be, they can exhibit mixed ion or electronic conduction, or then there is the common basic perovskite, or they can even exhibit ionic, so anionic, protonic, and electronic conduction. So very different kind of conduction mechanism and species that can be going around the structure. This latter conduction type is generally linked to simple perovskite, like barium serrate-based one, or double perovskite, or Radisson and Popper. All these compounds are very interesting and very important for all the application, especially for hydrogen use and production. Especially when you are considering proton-conducting perovskite. As was mentioned before, the problem of solid oxide fuel cell is commonly the high temperature of operation that is commonly, intermediate side is among 700 degrees C. If you use a proton-conducting electrolyte material, you can lower the temperature, so the material is becoming, and also the balance of Planck is becoming more and more convenient. But it's also used in another kind of application, that is the membrane sector, when you can use protoconductor to separate at high temperature hydrogen from other species. And this is a very important application where therefore you don't need to, for example, lower the temperature of the flue gas in order to have a separation of hydrogen and CO2, for example. These materials are exhibiting proton conductivity actually as a consequence of an oxygen vacancies that seem a little bit odd, but actually the proton conductivity is given because you doping the B side of the structure with a trivalent ion, and this is for the Kroger-Wingen notation. As you can see, you can generate an oxygen vacancy that reacts at high temperature with the water, forming an hydroxide, and then free a proton that can then hop from one side to the other of the oxygen through all the materials. And as you can see here in the, maybe I can try to do this. No, it's not working, okay, but in the sketch before. So today I will speak not on solid oxide fuel cell or electrolyzer, but on membrane, high temperature membrane. The flux of hydrogen through the membranes is linked to the Wagner equation that you can see here in the sketch. And it's generally due to the material properties, so the material has to exhibit photonic and electronic conductivity, and generally this is properties of the barium serrate-based material that have high proton conductivity and good stability in CO2 atmosphere. But actually it has a low electron conductivity. So in order to overcome this problem, we generally mix the protonic conductor with an electronic-based conductor, steel ceramic one, that is commonly gadolinium dopsyria. So we obtain a cell-cell composite where we have still the protonic conduction, but we gain the electronic conduction. On the other hand, the flux is given by the pressure, so more on the process parameters, the pressure between the two sides of the membrane, that is the one that pushing the hydrogen from one side to the other side, and to the typical geometrical issue, geometrical parameters, basically the thickness. As all the materials thinner is the layer, higher is the conductivity. So in order to do so, you have to reduce the membrane thickness. But if you do reduce the membrane thickness, you need to support it in another way because it losing mechanical stability. And this, for a ceramic-based material, is quite challenging because actually you have to create a bilayer that is dense in one part and very porous in the other one. And if you are a little bit familiar with the ceramic processing, this is very challenging because they are going in a completely different direction one from the others. What we managed to do here is to build a symmetric ceramic membrane. We commonly use the so-called tape casting process that basically it requires to produce, you can see like a tape that is I would say a polymeric loaded sheet of materials, basically, that is very flexible. Then we laminate it together, and then we burn it out, everything, in order to have the pure ceramic phase. It's not very easy as it can sound, because you have to optimize all the processes parameter, considering the support that, remember, it has to still be porous because the gas has to reach the active materials, and then you need to optimize a lot of different parameters inside. You have to optimize the lamination procedure, so the two different layer that you see has to be very adherent and has to go through the very nice and smooth process of elimination of the organics. And you still have to have a very dense ceramic membranes, that is the active part, and should be dense as much as possible, because it's the material, is an electrochemical flux, is not going through porosity. So you need to have a very dense material because you have to have as much material as possible. But in this material, there is another challenge, that is the high temperature. In order to obtain a full membrane, you have to sinter the whole system at 1400 degrees C. This is a very high temperature. At this temperature, these materials that are commonly very stable, they are losing barium oxide. So you are losing basically the stoichiometry of the system. So in order to overcome this problem, what is commonly we are doing, you can see here the effect on a full dense membranes. You can see that there is a lack of barium on the first, I would say 12 microns of the membrane. So in order to do so, in a ceramic process, what you are doing, you're using a sacrificial powder. So basically, you put a powder inside in order that this counterbalance the evaporation of the barium with the one that is coming from the sacrificial powder, the one that is going away from the membranes. And this seems very easy, because you can say simply, okay, you can put just barium oxide, but it's not working like that, because if you're putting just barium oxide, there is a very low melting temperature compound, so you are not reaching what you are needed, but you're just covering with the kind of layer of barium oxide on the surface. You generally use the compound itself, so you make a sacrificial powder or barium stearate, zirconate in this case, and you use it as a source of barium oxide. But actually, what happened in a bilayer compound like that is that there is a solid reaction between the sacrificial powder and the electronic conduction part, so the gadolinium doped ceria, that actually is very similar to the cerium compound. And so what you attain is a couple of microns at the surface of the membranes that is not anymore a cell composite of cerium, gadolinium doped ceria and barium stearate zirconate, but actually it's a single phase of barium zirconate stearate doped with deuterium. So what we managed to do is to change the sacrificial powder and use the same composite in order to counterbalance the evaporation of barium oxide. And doing like that, we obtain a very nice microstructure, as you can see here, of the cell-cell composite of an electronic and protonic conductor phase. And it may seem trivial, just 2 microns of a single phase on the top, but actually it's not at all like that, because if you are going to see the permeation, the hydrogen permeation measurement, you can see that if you have just 2 microns of single phase on the top, you have basically not the ambipolar conductivity that you are expecting, but just the ambipolar conduction of the single phase. So basically, you don't have any more the need of a composite. On the other side, if you manage to retain the double, the cell-cell composite throughout all the membrane, you manage to have a very high hydrogen flux. Very high for this kind of compound, obviously. Yeah, also always to look at in relation of the other. If you then change the geometry, so from a pure compound and a dense, high thickness membrane to a supported one, you will see that you will obtain a 1 order of magnitude more of conductivity in this kind of compound. And on top of that, if you use even a catalytic phase on both sides, you manage to increase even more the conductivity, reaching values that are quite interesting. But more interesting if you manage to change the way in which you make the support and have a directional porosity. This is something that you generally don't obtain with the ceramic process. So in the way in which you don't have any more problem of flowing of gases toward the membranes, and then you reach what is considering the highest flux among the ceramic base membranes that you obtain today, that is 1.1 milliliter per minute per square centimeter. Obviously at high temperature, because this material to work has to need very high temperatures actually. And this is one of the highest flux that you can see in literature up to now. But actually, perovskite are also used in a different application that was not mentioned to this morning, but is what is called the artificial photosynthesis. So the way in which we can convert the solar energy directly into hydrogen or different chemicals. We will hear surely more information afterwards. And there is basically 3 different technologies that try to exploit this approach. One is pure photocatalysis, the other one is photoelectrocatalysis, where there is a voltage applied, and the one is an electrochemical cell where you use the renewables to give the additional external voltage. If we consider the first 2 technologies are basically based on materials that absorb lights, and with these lights is used to photogenerate electrons and holes on the other side, so the couple, and this couple is used to the redox reaction that are commonly considered for example, CO2 reduction. In order for having a good and an efficient process, you have to avoid recombination. So you have to avoid that holes and electrons are coming together, reaching neutrality, because if you have a recombination, obviously you don't have any more the electrons for the redox reduction. So you have to increase the electron lifetime of this system. And the way in which you can do that, the most simple one actually, is when you separate the reduction to the oxidation reaction. And this is what we commonly do in a photoelectrochemical cell. So you separate the two redox reaction, you apply an external voltage, and then you enhance, obviously, the charge separation. You have higher efficiency because you have an higher changes lifetime, actually. But another way in which you can add another external way of improving the lifetime is actually to exploit the structure of the materials in order to have an additional external load to the system. And this is what we commonly do with the so-called piezo-phototronics materials. Piezo-phototronic materials are very nice and exploit the multifunctionality of perovskite by itself because they are actually materials that have at the same time exhibit piezoelectricity, semiconductor behavior, and can act as photoactive materials. So they are very nice material that can be very useful in this kind of application. For the one of you that you are not familiar with the effect, piezoelectric effect, the piezoelectric effect is actually quite old as well, and is the one due to the particular structure of the materials that actually allows you to have to develop a voltage if you applied a mechanical stress in what is called the direct effect, or in the indirect effect, you apply a voltage and you have a mechanical strain. This is the base of actually the actuator, for example, the indirect piezoelectric effect. In the photocatalysis, this is always, the piezoelectricity is exploited through mechanical steering and ultrasonic vibration. So you exploit the direct effect to develop this internal voltage. Actually, this is not useful when you have a compound in a substrate, so in a photoelectrochemical cell, obviously, because otherwise you have, you remove all the material from the electrode, so it's not very useful. In this case, what you can do, you can use a subclass of material, piezoelectric material, that are called ferroelectric material, that have a very unique properties because they can develop an internal polarization if you, before applying an external voltage. So what you are doing, basically, you are applying a voltage and you create an internal dipole and therefore an internal polarization that remains after you remove the external load. And on top of that, this polarization can be reversed. So you can decide which side of the application, which side of the voltage you want to apply. What is the link between phototronic materials and perovskite is because one of the family of materials that are exhibiting this effect is actually a perovskite-related family, the Arrhenius one. This is a very nice family of material, layer material, when the perovskite block are intercalated with the bismuth oxide one. And in order to check the possibility to apply this material also for the reduction of CO2, because they never been tested for that actually, we try to produce two different compounds. The one that is the so-called the parent compound, the most common one, that is bismuth titanate, when you have 3 perovskite block between BO2 layers. You can see it is the third from the left, and is very common and very used also for photocatalytic application. And the other is bismuth molybdate. In this case, you have just one perovskite layer each bismuth oxide layer, but it's a very nice compound because you can tune the microstructure of the compound. And if we if we are talking about moving electrons around, if you manage also to have a directional material, this is helping much more this application. So starting from bismuth titanium oxide, the first nice thing of this material is that it has actually a structural special separation of the charges by itself, because the photogenerated electrons are going through the perovskite block, while the holes are going through the bismuth oxide. So you have already a separation of charges due by the structure. On top of that, it has an high Raman polarization, very high for thin film, the highest that you can find actually. And in order, therefore, it's very useful for this kind of application. So we managed to optimize all the different parameters to obtain this film by spin coating from the processing to the thermal treatment. And what we obtain is a very nice homogeneous 150 nanometer film, crack-free, with the right composition. This is not so easy to do because all the allyl compounds are very refractive, so they need a very high temperature to be developing the right composition. As you can see, the film is very transparent, and this is very useful when you are talking about photoelectrochemical cells. The band gap is a little bit high, higher than what you expected in powder form, but this is commonly in this kind of situation. And when you are talking about, so I'm going faster then, and what we try to manage, so we look at all the different properties that I'm skipping at this point, just to show you, if I manage to go back, okay. If you, just to show you this graph, that is what is looking at is what is happening if we apply a Pauling voltage to this system. What happens is we manage to enhance the current density and to reduce the resistance between the electron and the electrolyte, as you can see in the graph on the right side. And this is basically due to the changing of the Pauling system to the band, the energy band diagram of the materials. This is the one that you can see for the material without Pauling. And this is what happens when you apply a Pauling. So you develop a piezo photoelectric or ferroelectric internal dipole. So you have basically a bend, a downward bending of the electronic band, and therefore this is helping in separating the charges as you can expect it. Actually, when you apply the Pauling on the other side, you increase you decrease the charges, because you basically have an internal voltage that is going in the opposite side of the external one. So I'm just leaving you with this. That is the work that we have done on bismuth molybdite, actually, showing how we manage to change the microstructure of the film from nanosheets to nanorods. I don't have time to show any other results, and I'm just finishing apologizing if I'm too long, and thanking all the funding agency and you for your kind attention.
Okay, thank you very much. I think that now we have the coffee break. I would ask you to come back in 15 minutes in order to be not too late. Okay, see you then.
bisogna andare vicino al microfono, se no anche
non sapevo come stava lì.
Vediamo se ci colleghiamo anche noi.
Anche tu sei quasi facendo. Abbiamo fatto la prova, prima si sente benissimo.
Gabriele?
Ciao Gabriele, sono Elio
Ma
Giannelli.
adesso dovrebbe entrarci.
Sono qui con alcuni amici che ti stanno guardando, vogliamo sapere intanto come vanno le cose, come sta Linda. Cosa vuole?
No, però perché non si sente?
È bene che non si sente in questo
momento. No, lo so, ma mi preoccupo per dopo.
Mi spiace. Comunque, senti, tu hai fatto bene a non venire a stare lì, poi ti si sente e ti si vede benissimo, quindi stai tranquillo. Adesso, stamattina c'erano dei problemi sul collegamento, invece adesso è perfetto.
Senti, chiedigli se vuole diminuire, se ha bisogno di meno, perché altro siamo un po' in ritardo.
Cristiano che sta chiedendo una cosa, aspetta, parla di tu che non ho capito bene cosa vuoi.
Gabriele? Ciao, senti, dato che possiamo andare un po' lunghi, no, se tu hai delle esigenze insomma io posso anche farla, la possiamo fare anche un po' più breve, invece di 20 minuti, perché capisco che tu hai fretta di andare, insomma, purtroppo sono andati un po' lunghi, quindi però se tu vuoi la possiamo accorciare senza problemi. Per te, se vuoi, dipende da te. Va bene? Ok. Però noi ci dobbiamo collegare con lui.
No, è interessante, non mi uscita. Adesso io non riuscivo a di bilanciare un attimo tra me che sono veramente radicale, no? Però cosa ti dai?
Gabriele, ci senti? Ci senti? Gabriele, tu ci senti? Gabriele, tu ci senti? Ma io non ti sento però. Forse dobbiamo chiedere. Ciao bella. Si sente? No, non lo sto sentendo. Hanno provato prima e si sentiva bene. Riattiva l'audio. Vediamo. No.
Il mio amico Miracca, quando direttamente con lui, non è ingegnere, non è rimasto insensibile.
Scusa Gabriele, ma tu ci senti? Non sentiamo la tua voce, un attimo solo. Com'è che non si sente più?
Non vorrei che in questo momento non sia la regia solo prima si sentivano.
Parla adesso, si sente? No, non si sente, stiamo aspettando il tecnico, un attimo. Aspettiamo il tecnico.
Le presentazioni dove stanno?
No, adesso io poi esco da Teams e stanno sul desktop.
E si capisce quali sono?
Sì, vediamo. Sì. Ecco. Bordiga, eccola qua. Vediamo. Siamo. È tutto a posto, quindi questo è a posto. Tranquillo. Adesso rientriamo in Teams.
Pronto? Gabriele, ci senti?
Io vi sento perfettamente, voi mi sentite?
Noi ci sentiamo perfettamente, tutto a posto.
Ok, ottimo.
Okay, good afternoon. Please sit down. We want to start the final session of today. This is related to the conversion to chemicals from hydrogen. And I would like to announce that there will be a change of program. We will shift the first two presentations, and our first speaker will be Professor Gabriele Centi, that is connected by remote for personal problem. And a few words about Professor Centi, that is, I think, well known to everybody. He's full professor of industrial chemistry at the University of Messina, and is the king of the catalysis in Europe. His research interests are, among the others, in the applied heterogeneous catalysis, sustainable energy, and chemical processes. We have too short time to make a list of all the honor and the project. He has been a coordinator of more than 20 European projects, received several awards. Between them, I would like to mention the Humboldt Research Award, and is involved in various editorial activity, chaired, for instance, the editorial board of ChemSusChem. He's author of more than 500 scientific publications, 12 books, a number impressive of citation and NH index that is impressive too, it's around 100. Today, he will talk with us about from first to second generation technologies to make chemicals via green hydrogen. Please, Gabriele.
Many thanks, Angela, and good afternoon to all. And let me apologize that I'm not able to be present in person. So essentially, in the title, you see the content that I like to stress, that we need to pass from the first to second generation. Essentially today, we have seen also in the discussion today, we are focusing essentially to electrolysis as a way to produce hydrogen, and then of course to transform using this hydrogen eventually to make via multi-steps process some chemicals. My suggestion is that on the contrary, we need to put emphasis at least to the fact that we need to pass and to accelerate the pass to second generation of system where you have the direct conversion, and I will try to stress you why. And of course this should be made in collaboration, at least a large way at the European level, like the Sun Energy Initiative. But just two words before, just to put some salt for the discussion, how green is the green hydrogen produced by electrolysis. And here is an interesting result, is an LCA analysis which include also the carbon footprint related to distribution in the grid. And what you see, this is a study made from people from ThyssenKrupp inside the carbon 2 chemicals. What you see here is that actually the carbon footprint respect to what is the carbon footprint by hydrogen by steam reforming is still very high, because essentially electrolysis is a very energy intensive technology, and also there is a lot of energy that we need for all the value chain in the system. So with the actual system, and even for the future in 2030 system, still the production of hydrogen has a carbon impact which is higher than if we produce hydrogen by conventional way. And the second data is this one, which is very related, which is an estimation of, this is a study of the Max Planck, is what is the efficiency of the hydrogen process chain. And again, if you consider, for example, a production of electrical energy and then transformation of by electrolyzer and then storage and so on and final use, you see that essentially from 90 gigawatt you obtain 24 gigabyte. This is of course based on the idea to have a full day necessary to produce in this way. So essentially you have 26% of efficiency in the overall system. So these are the two bases. You can discuss if it's true or not, but anyway, to give a very clear indication of the problem that we have when we speak about the green energy. So what we need is to really reduce the effective total carbon footprint and cost of producing green hydrogen, and of course also we need to develop a better hydrogen vector. We have seen also some aspects related to storage and also some of the energy vector, but my thesis is that with the actual system we are not able to address effectively the need that we have, and so we need to accelerate the development of new solutions. This is the reason why I will very briefly speak about some of the possibility to produce in alternative way hydrogen, and of course with lower energy intensity, and also how we can use, for example, produce in an integrated way some hydrogen vector, and how we can integrate the energy storage beyond the classical power to X system. And finally, a few words about the possibility to use solar energy in a continuous mode to produce, for example, hydrogen. So let me start very briefly. There is a lot of interest, and also in Rome now is starting a very large project on producing hydrogen from waste. There are some plants in construction also in Porto Marghera and other. However, if you just make some estimation, here you see all the flow sheet and some of the carbon balance, what you see is that the emission of carbon dioxide by this system is still very large. Can be a cost competitive way to produce here some estimation. However, the carbon footprint is high. It is a bit better if you consider also the non-biogenic carbon dioxide, because you have part which is deriving from biogenic waste, but still the impact is very large. So this is not a solution to reduce the carbon footprint. What you can make is, for example, try to simply just electrify a classical steam reforming, and if you see that in terms of energy, if you try to develop a system in which you have steam reforming, but in which the heat of the reaction is provided by electrical energy, you decrease to 1/3 at least the energy intensity, and for this reason, at the end, you have a better carbon footprint. Of course, if you have fully renewable energy, electrolysis is better, but with the actual mix, the electrolysis have a higher impact than this would. So this is, for example, part of a European project which is just started to try to develop, because you need also to develop the technical solution to achieve this. The other possibility that you have is to even produce hydrogen, green hydrogen, with an even carbon negative footprint, and of course this is the solution in which essentially you have a splitting of the biomethane. Of course you need to start from biomethane, and because the negative carbon footprint derived from one side, because you are sequestrating carbon dioxide, or better, you can transform this to carbon material that you can use as polymer additive, and this of course is creating added values. However, the problem is that you need to find a new technology, because the actual one is working at very high temperature. If you have a system like this one, which is outlined here, this is an Italian project which is will start now. You can make the reaction at much lower temperature, something like 600 degrees, use a kind of combined active carbon and a plasma, non-thermal plasma activation of the biomethane, and in this way essentially you can use directly renewable energy to run the process. And by this combination and the fact that you produce a carbon material that you can use for plastic additive, for example, then you can have an even carbon negative footprint for the hydrogen. And finally, just let me remember that we have, even if of course has in some way the size is lower, you have the possibility also to produce something that, a material that was some way similar to what described before. You have some solid proton conductive membrane and a catalyst on the two sides. You can apply a potential which drives the transport of the proton, and then you can realize dehydrogenation from one side and production of hydrogen on the other side. Of course, the advantage of this is that you have a co-production of ethylene from one side, so you reduce the carbon footprint of producing ethylene from one side, and you can produce hydrogen as a byproduct. So again, this is formally a carbon negative footprint if you include also the reduction in the system that you can have in producing the olefin. But of course you can also have, we have seen before also the problem of transporting and storage hydrogen, and this is the technology that was commented before, which is actually you need to make renewable electricity, and then of course you need to have hydrogen compressing, and then catalytic hydrogenation, dehydrogenation. You can integrate this element, for example, inside an electrocatalytic system, in which again you can have valorization of the anodic part. In this case, this is an European project which is just started. You have transformation, some linear derivatives, so you have another valves on the anodic part, and on the cathodic part directly you have the, let me say, hydrogenation of the lipid organic hydrocarbon, which is then can be transported, generate on-site hydrogen. So in this way you have a link between bio-waste valorization and hydrogen economy, and of course you reduce the steps, so you have a process simplification, and you have also some advantage in terms of lower energy intensity of the process of producing hydrogen and hydrogenation. And you can apply something similar to the concept of, we have seen also that ammonia has, is some way in an ideal hydrogen vector because has a hydrogen storage capacity which is double that of liquid hydrocarbon or any of the other storage system. And of course they have the additional advantage that essentially the nitrogen which is formed by redecomposition you can emit it, so you need not to transport back. And of course here you have a multi-steps process actually, but today you can realize or is under development the possibility to have a direct system in which eventually you can also integrate a membrane in order to operate directly with air rather to have separation of nitrogen, and you can produce in a distributed way ammonia which can be transported. Of course we need still to improve the performance, but again is a question that you need to intensify the research in this direction. And this is the question because we have seen that power to X is the actual solution. There are many plants, demo plants which are running, but of course the main limit is the cost and the carbon footprint which is related to production of hydrogens. So we can reduce this if we can integrate, we have a process intensification, we have a reduction of the carbon, of the energy intensity, and so we can have a series of advantages in order to integrate the system to produce what I call second generation of solar fuel in contrast to e-fuels, which is the first generation. And of course, what are the advantages? First is that you are producing and using the hydrogen equivalent, which are proton and electron, rather than to form the hydrogen molecule. So you avoid to have all the energy expenses which are related to forming the hydrogen molecules and using the hydrogen molecule. And there are many, we have not time to discuss, but there are many problems related to this. And also you avoid all the thermodynamic limitation. For example, that takes the possibility to produce, to have to hydrogenate, for example, CO2 to methane, which is one of the possible also way to chemical storage of hydrogen and energy. And of course, you have, this is strongly limited by thermodynamic, and if you are making directly in an electrochemical cell, you avoid the thermodynamic limitation. And you have also other advantages that you can even integrate some membrane. For example, you can work with dilute stream and others. So in general, all this system translate in a reduction of the capex and OPEX cost and operation in mild conditions. So these are systems which are ideal, especially for a distributed production, and so you avoid all the problems related to transport. So you can realize local storage and reuse. And this is one of the concepts, for example, in which you can try to integrate. So today, the approach is essentially, besides to have, for example, batteries or flow redox batteries. This is an Italian project which is also starting now. You can have storage as conventional power to gas, but you can have an advantage if you are passing to a next generation of system in which essentially you can directly convert CO2 to methane in an electrochemical cell. And here also one of the other possibilities that you can create is to have a spatio-temporal decoupling of the two reactions. So in order to have a system in which essentially you are substituting the oxygen evolution with another reaction which is less demanding and also occur in solid state, so allow also to extend the time of operation and then to remake the regeneration during the night. And this can reduce potentially at least by 20-25% the energy intensity of the process. So in general, this is an interesting possibility because if you are extending the concept, essentially you can try to arrive to a system which can operate in a continuous mode, essentially including some redox mediator which accumulate in the system and which act as a buffer to implement really this continuous operation. So, because the main problem that we have with all the systems which are in some way from photovoltaic to photoelectrochemical cell is that, of course, we are limited from the time when is available solar energy. In this system, we can extend and virtually to arrive to continuous mode, and we will see also another alternative of this concept. And essentially, this is the concept because rather than to use this, we can also implement the reaction, for example, of transforming CO2 to formic acid, which is an excellent hydrogen chemical storage. But in this case, the difference is that we integrate this in a scheme, in a photoelectrochemical scheme, in which we have the co-production of formic acid from CO2 and hydrogen, and during night, so when is not operating, essentially the formic acid which is accumulated is decomposed, reforming CO2 which is recirculated and forming hydrogen. In this way, essentially, we can have a continuous 24-hour, not 2 hours, sorry for error, hydrogen production. Is low, but I think that you can extend this concept because you can realize a kind of compact device, a kind of artificial leaves device where you can operate this. And this is essentially illustrating this picture. Essentially, you can realize a kind of artificial trees where you can produce essentially at home the hydrogen that you can use for, well, during night or when it's not the sunshine. So in order to provide the energy that you need at home. There are something which is similar, which is essentially a combination of the photovoltaic panel with an electrolyzer. So you see here an image. But in this way, if you can integrate with a storage, you can have some advantage in terms of allowing a continuous production. And of course, you have many possibilities also, not only to convert these to hydrogen, but you can essentially produce directly a series of chemicals. This is some data for converting electrocatalytic CO2 to ethylene. You see that this is a way, state of the art, let me say. You see that already there are many interesting performance in terms of current density and Faraday efficiency. So this is definitely one of the direction which is increasing, and definitely we will see the possibility to produce not only ethylene, but we have a large variety of other systems, acetic acid, methanol, higher alcohol, hydrocarbon. I will skip the production of carbon monoxide because in my opinion this is not the right way to go. We need to form more complex molecules even if this is more challenging. And of course, based on this, you can realize a kind of new chemistry, essentially using direct electrocatalytic process in which you can combine it a traditional way to also to use of the active intermediate in a combination between them in order to try to synthesize all the kind of molecules which are, of course, you need some also to have some biomass for these, but essentially you can largely produce mostly of the chemical which are produced now from fossil fuels. So this is the challenges that we have. It's possible. We need to work to go in this direction, and we can achieve at least 70% of the fossil fuel substitution within 2050 if clearly if we investigate and if we have enough research effort to go in this direction. This corresponds just only in Europe to something like 800 million tons per year of carbon dioxide reduction, equivalent reduction. So something which is quite relevant and is feasible. We need only to invest more in the research in this direction. And so this is the last word. I think that is self-explaining. We have a lot to work, but sun is our resource, and you see also here a view of the group of people which are, of course, who is making this kind of testing and development. Thank you for attention.
Thank you very much, Gabriele, for being with us. And of course, he will not stay for the final discussion, but if anybody has some question for him, he can send him by mail, he will answer. Then we close the connection with the teams, and we go ahead with the section. Okay. Now it's time to call Dr. Mario Marchionna. Is here? Oh, yes. Mario is a perfect connection between the company and industrial world and the research and education world for the role that is always had in dissemination, in education, and also in promoting industrial research. He is the corporate head of technology innovation of SAIPEM, president of the division of industrial chemistry of Italian Society of Chemistry, and we thank you very much for this. He's vice director of La Chimica e l'Industria, that is the journal that is really the voice between the society and the industry and the public. That is a really important role. And his mission is to transfer the value of the economical, environmental, and social value created by technology innovation. Today, he will talk with us about hydrogen production and conversion to chemicals, a zero carbon puzzle question. Please.
Thanks a lot, Angela. It's really a pleasure for me to be here. Thank you a lot to organizing committee, all of you. I'm really honored to be in this conference. So I'll talk about the production of chemicals through hydrogen. That is actually the real industry of hydrogen at the moment, because as we've seen, the main purpose of hydrogen, at least on a bulk scale, is to operate in the chemical industry and in the refining industry. So I'll give a look just to how is the situation today, which are possible schemes for producing hydrogen with a lower carbon intensity and ammonia, that is the most important derivative, some initiative on our side, and we'll have some takeaways and we'll try to answer to this puzzle, because at a certain stage it's a puzzle, it's not so easy to decarbonize on a very large scale these big chemicals. The situation is that hydrogen is used as an intermediate product now. Is mostly produced from natural gas in very large scale plants using either methane steam reforming or autothermal reforming, very mature technologies, very optimized, very consolidated. Hydrogen has a very high carbon footprint because for 1 ton of hydrogen you produce from 6 to 9 tons of CO2, if you move from natural gas, that is the most decarbonized among the decarbonized sources, is even worse from oil or from coal. And the production of hydrogen is responsible for a significant amount of CO2 emissions worldwide. The number seems low, but in absolute terms is absolutely relevant. And it's clear that in perspective, it's mandatory to decarbonize this sector. If we give a look how is the situation now of how hydrogen is produced and which are the main uses, I start from the uses. Ammonia is the most important one, then use of hydrogen in the refining, then methanol, then other uses. It's mostly produced from fossil fuels. Natural gas is the most important, but for example in China, coal is still very important. In the countries of Middle East, oil is still important. There is also a very small portion of hydrogen from electrolysis in the very traditional electrolysis of sodium chloride to produce chlorine and soda, but is very niche. If we see the main uses, ammonia and methanol are two among the top 10 chemicals. So the amount of ammonia produced worldwide every year is very, very high, at million. And ammonia is an intermediate for fertilizer, principally. Mostly urea, nitrates, and so on. Is a very bad chemical, is the number 5. Methanol is the number 10, and is used as an intermediate to make formaldehyde, industrial solvents, but it's also an intermediate for olefin and also polymer from olefins, for example, in China. Methanol is an intermediate to produce olefin and then polyolefins. This kind of process is peculiar. This production are very huge. The plant does never stop because you need to have continuity of production for practically for all the year. This is typical of this large production. This is clearly something that has to be taken into consideration when you think to decarbonization of these intermediates. And as also pointed out before by Armaroli, hydrogen, as soon as produced, is consumed. So it's an intermediate with a very short life. This will be the same also in the future production of hydrogen. It does not change in this respect. You will not need any storage or transportation. You will have to produce and then to convert, such as now. We as Saipem have a considerable experience in hydrogen production. First of all, maybe some of you does not know what is Saipem. Saipem is a service company. We are an engineering and construction company. We make engineering in the sense that we make very complex engineering studies from conceptual to very detailed studies that led to the final investor decision to realize or not to realize a plant or not. And then we realize also this kind of plants. For example, this is one of the largest, maybe the largest one plant of ammonia in the world in Qatar. We have a considerable experience. We work both offshore and onshore, but it's clear that regarding the production of this chemical is mostly onshore. And we have experience in hydrogen production, ammonia, methanol, gasification of oil residues to hydrogen, and also Fischer-Tropsch reaction, both in the engineering side and also in the realizing side. So we have really an experience that is fundamental to move the technology from the flow sheet to the final plant that has to work for a life. So which are the opportunities to decarbonize this industry? The most well recognized are the so-called blue hydrogen, green hydrogen. I do not explain too much, you know very well. And blue hydrogen is conventionally the capture of CO2 from the current production schemes, and then you have in some way to storage elsewhere. Green hydrogen, I don't say anything. In principle, there could be a lot of other hydrogen with other colors. I put here turquoise because I love a lot turquoise, but it's not the most important one. Maybe it's more interesting, hydrogen from waste and so on. But I confine the discussion to blue and green hydrogen. Blue hydrogen, you have to couple the conventional steam reforming or autothermal reforming plants with capture of CO2 and transportation of CO2 and moving to a storage site. You can also utilize the CO2 in other ways, but the main scheme is with storage of CO2. You need a minimum level of carbon capture. It's clear that the highest the level, the better is for reducing the carbon footprint. You have to follow three main criteria to allow this option. The first is to have cheap gas available and affordable. And actually the production of these chemicals are in very precise countries. You need an existing pipeline infrastructure to move CO2, and you need a CO2 sequestration potential. This is clear that is not always easy to match these criteria, but these are the criteria. In principle, a few geographical areas are better suited, for sure the US, Canada, North Sea, the Middle East, also Russia, potentially, Australia, and maybe also China. It's clear that this option has some advantage in terms of simplicity. You have your plants, you can retrofit by adding capture units and storing, and you do not change anything. There is also another aspect to consider, that sometimes you need also CO2, because if you produce urea, that is one of the most important derivatives of ammonia, you need CO2 and ammonia to produce urea. So you have to catch CO2 somewhere, and this is true also for methanol, because you need a source of carbon. By the way, we are one of the most important technology licensors in the urea field, and about 40% of urea worldwide is produced according to our technology. So we have a definite experience also in this field. Green hydrogen is for sure the best option to really decarbonize. It's clear that the technology has to move in order to comply with the scale, the huge scale of these bulk chemicals. And also some improvements should be done also not only in respect of the scale of your electrolyzers or your electrolyzer plants, but also regarding the efficiency, because the efficiency for the moment is not so high. So let's give a look to understand a bit more which are the main schemes. So in blue you can see a typical steam reforming plant to produce ammonia. What you have to do, you have to add a post-combustion CO2 capture and optimize the CO2 cycle in the steam reforming. On one side, these technologies are well referenced, and you have to achieve a proper integration of all the process units, also to increase the overall efficiency and to maximize the carbon capture rate. It's clear that this is not free. It's clear that capture CO2 in any case is a significant investment that you add to this unit. In some cases, for example, in the case of autothermal reforming, that is a mix of reforming using water and oxygen, you can achieve even higher carbon capture rates. There are examples. For example, in Canada, there is a huge plant of blue hydrogen produced in the Scottsford refinery of Shell in Canada, and CO2 is moved to a sequestration site in nearby. As regards green hydrogen, the plant in principle is very simple. As regards you have to clean water if necessary, then with renewable power you have the electrolysis, green hydrogen. On the other side you have to take nitrogen from air through separation, ammonia and so on. Only a particular aspect, you produce also a lot of oxygen. If you see in mass, the main product of all this cycle is just oxygen. This does mean that in a certain way I think that we have to valorize this oxygen. When we talk about green hydrogen, we talk only about hydrogen, but oxygen is produced at a rate that is, at least in mass, 8 times the hydrogen you produce. So it's not a byproduct, it's a product that we have to valorize. For sure, in perspective, we can improve a lot in this respect, because renewable power will cost lower and lower, and also electrolyzer will increase their efficiency, their experience curve and so on. I think that also, for example, solid oxide electrolyzer have in perspective the advantage to afford a better efficiency than conventional electrolyzers. So we could improve on a lot of different respects as regards green hydrogen. It's clear that it's important, the power infrastructure, because you need to have the electric energy available at stable conditions and in huge amounts. So we have made some exercise also because our clients ask us this kind of exercise. They want to understand how their plants could be hybridized, convert in some way to produce green ammonia and maybe also urea. So we have made different elaborations, both on blue hydrogen, but it's more specifically on green hydrogen. We have studied different examples. This is one that is maybe least likely, because it's clear that on one side, if you have renewable electricity available at your side, it's very simple, but it's very unlikely that you'll have an excess of renewable energy at your size. So it's much more likely the situation that you have to generate the renewable electric hydrogen, and then you optimize your electrolysis plants to produce. In this case, it's not a big production of ammonia, but it's a significant production that is at least 1/10 of an industrial plant. This for sure is possible. You have to optimize the scale of the power production, because you need some power in excess with respect to what needed from your electrolyzers, both because of reason of efficiency, and because it's clear that the variable character of the renewable source needs to be in some way complied by the electrolysis. Specifically for the photovoltaic plant, you need a lot of surface available. Sometimes you have, sometimes you don't have. A possibility to avoid this constraint is to move electricity production offshore. This is an option that we are investigating. We are not the only one, also because there are a lot of different projects that are at a feasibility stage. So this is a bit the feature. We have also made some practical exercise. We report here only a few of them. One representative for blue hydrogen. This is a plant very close to the Barents Sea, very Arctic conditions, and it's one of the largest ammonia plants worldwide. We have studied carbon capture is possible and practically at total level, and we are optimizing the plant. Of course, we are very far still from the real decision to change this plant, but it's a study that is very instructive. Such as it's instructive this other case. This is purely green hydrogen in Morocco. In Morocco, most of the electric power is produced by wind, and but there is also some photovoltaic. This is a really attractive area in the sense that you have available all the best conditions for a power plant of this kind, and so this reflects also positively in the case of ammonia production. We are also studying some case of generation of power renewables offshore. This is a project that is offshore Ravenna. It's called Agnes, and we have made feasibility studies. This is mostly a project for the production of renewable power, but there is also some hydrogen that can be produced offshore and onshore. So this is a summary of which are the most peculiar features of which are the issues in decarbonizing hydrogen and so ammonia and derivatives, which could be the takeaways. It's clear that both the hydrogens have the potential for gradually replacing the so-called green hydrogen. It's also clear that, I have to be very careful here because it's dangerous, but I survived well. And it's also clear that the use of non-dedicated renewable energy sources will be very limited to very contingent situations. In the midterm, I think that green hydrogen could be more competitive. It's difficult to talk about costs because based also on our experience, we realize that, for example, blue hydrogen could be much more convenient 2 years ago. Now the situation is completely different. So it depends. What we want to achieve is to have a clear comprehension of the fundamentals that are behind this kind of conversion. Electricity is better to produce from dedicated renewable parks, better located in geographical areas that allow you a low production cost. There is also some aspect that is strange, because steam reforming is a technology that is very optimized but is very rigid. For example, if you move to a biorefinery where you have variability of the feedstock, it could be interesting to have a green hydrogen that give you more flexibility. So in some respect, it's not said that it's always an advantage to have a technology so consolidated. Green hydrogen can give some option. It's clear that carbon tax is useful. By me, it's very clear that the better you achieve good valorization for oxygen will give a big advance also to the deployment of green hydrogen and also to lowering the cost. Finally, it's clear that there is not only this kind of industry for hydrogen, because for sure this part of the oil and gas side of the so-called hard-to-abate industry is one part, is an important one part. You have also industries such as steel, aluminum, cement, paper mills and so on that are very intensive. All these ones are responsible for 1/4 of the overall CO2 emissions, and this kind of concept could be advantageously extended also to this kind of industry. This is an option that in perspective could be very important. Finally, what to say about the question mark of the zero carbon puzzle? It's a puzzle because it's not so trivial to find the right situation. Most of the situation will be, in any case, site-specific, but I think that the progress is evolving, technology is evolving, and I believe that step by step, with, for sure gradually, not on one pot, but will achieve significant improvement on this side. And finally, thank you very much.
Thank you very much for this really interesting presentation. It's time now to call Professor Visconti Carlo Giorgio, Associate Professor Politecnico di Milano. His work is related on the preparation, characterization, and testing of catalyst heterogeneous. His work is now focused on reactor, catalytic reactor, advanced, and their development and their modeling. Today he will present a work on decarbonizing with hydrogen, technological challenges and opportunities. Please.
Thank you very much for the kind introduction, and good evening, everyone. It's a great pleasure for me to be here today and to have the chance to share with you some thoughts on the technological and engineering challenges and opportunities behind the decarbonization with hydrogen. And I would like to acknowledge the organizing committee for inviting me today in this beautiful event. So, why we should decarbonize our economy is pretty obvious today, but what should we decarbonize first is not that trivial. And so I would like to start my presentation showing you some plots helping us to address this issue. And this plot shows where the greenhouse gas emission at the world scale come from. And as you can see, more than 70% of the global greenhouse gas emission comes from energy conversion processes. 1/4 from the energy used in the industry, 1/4 from the energy used in the transportation sector, 1/4 from the energy used in buildings, and 1/4 for the rest. So it's thus clear that we should start decarbonizing the way we make the energy. Now, this is a quite complex Sankey diagram showing us the global energy flow, again at the world scale. And two comments can be made looking at this plot. First of all, the amount of energy we produce today, starting from renewable energy, is really limited. And second, what we can observe is that the energy we use to make the energy for transportation comes mostly from very carbon-intensive source and raw materials. So we should decarbonize the way we make energy first, and in particular the way in which we make transportation fuels. And that's why the first case I would like to share with you today will be focused on how to make decarbonized transportation fuels. But let's have a look also to the chemical industry. And here again, on the left, what you can see is that in addition to the CO2 emissions related to the energy conversion within the chemical industry, another 2.2% of the global greenhouse gas emission in the chemical industry are associated with the production of what we call the process CO2, the CO2 we produce as a byproduct in the production of chemicals. In particular, again, looking at this Sankey diagram, what we can realize is that the two major contributors to greenhouse gas emission in the chemical industry is the hydrogen production to make ammonia, to make nitrogen-based fertilizer. But this, as we learned today, is pretty simple to be changed by replacing fossil hydrogen with green hydrogen. And a bit more complicated is to address the challenge of CO2 emissions for the production of monomers, basically through the steam cracking, we use them to make polymers. And the second case study I would like to share with you today is how to decarbonize the production of monomers to use to make polymers. Now, the question is how to decarbonize the transportation fuels and the commodity chemicals. And in addition to the direct use of hydrogen we have discussed in the morning, I think that one of the only options we have, at least for the energy transition, is to produce e-fuels and e-chemicals. In particular, as we already discussed today, by reacting low carbon or green hydrogen together with CO2, we can make methane, we can make long chain paraffins, and we can make methanol or DME. So a lot of molecules that have a direct use as fuels. But also by combining CO2 with green hydrogen or low carbon hydrogen, we can make lower olefins, so ethylene, propylene, and butenes. We can make, again, methanol as a platform chemical, and by combining hydrogen with nitrogen, we can make ammonia. So we have access also to chemistry through the production of e-chemicals. Now, the problem that I would like to discuss with you today are the challenges, the technological challenges, the engineering challenges we have to face in order to produce those e-fuels and those e-chemicals. And I'm not going to focus on the catalyst development for those processes. I would like to discuss with you today more the problem of developing dedicated compact scale and flexible reactors for carrying out those reactions that, as you can see from this table, are all strongly exothermic, and all of them occurs with a strong contraction in the number of moles. And also I would like to discuss with you the challenges of the catalytic processes behind the industrial deployment of those processes that have to address strong thermodynamic and kinetic constraints. So let me start with the first case study, which is the production of transportation fuels out of CO2 and hydrogen. And there are many ways in which we can make transportation fuels out of these molecules. For example, we can exploit the renewable energy to make the water electrolysis, and then we can combine the hydrogen we make and the CO2 to make a two-step process, exploiting at first the reverse water gas shift reaction and then the conventional Fischer-Tropsch synthesis, followed by a product upgrading for the production of naphtha, normal paraffins, kerosene, gasol and diesel, base oils, and other fuels and chemicals. As alternative, we can directly react hydrogen and CO2 in a reactor where we run the so-called modified Fischer-Tropsch synthesis, where we make liquid hydrocarbons directly reacting CO2 and hydrogen. But also we have a third alternative, which is that of exploiting the co-electrolysis of CO2 and water, so to make syngas, which we can then exploit, we can then be converted in a conventional Fischer-Tropsch reactors. Now, what all these routes have in common is the fact that they are based on strongly exothermic processes. And all of them exploit the Fischer-Tropsch process. Now, if we have a look to the reactors we traditionally used to carry out the Fischer-Tropsch synthesis, what we can see is that conventional reactors are huge. In the first line, you can see the Fischer-Tropsch reactors used by Shell in the Pearl GTL plant to convert natural gas or battery syngas from natural gas into liquid hydrocarbons. And what you can see is that those are unit 20 meter long, 7 meter in diameter, 29,000 tubes in these multitubular reactors. Below you can see the Sasol gas-to-liquid reactors used to exploit syngas, again, to make liquid fuels, and those are reactors 60 meter tall by 10 meter in diameter. So the question is, are those reactors applicable to carry out the Fischer-Tropsch synthesis when exploiting syngas coming from CO2 and hydrogen? And the answer is no. No, because those reactors are too big. So the technological problem we have to face is how to scale down those conventional technologies. And even if I focus on the more simple technology to be scaled down, which is that of multitubular packed bed reactors, when you have to significantly scale down the process to be able to exploit the small amount of green hydrogen you have available with the small amount of CO2 you have available locally, then you have a problem, because clearly you can decrease the number of tubes, but when you try to shorten the tubes, then you enter in a trouble, because as you know, the heat transfer in multitubular packed bed reactor is controlled by convection. And convection is a heat transfer mechanism strongly relying on a velocity of the reactants flowing in the reactor, which means that if you shorten the reactor tube, you basically lose efficiency in the heat transfer. You basically, as this plot shows, have both a radial heat transfer coefficient and the wall heat transfer coefficient linearly decreasing by decreasing the Reynolds number, so decreasing the flow rate in the reactor. Which means that making multitubular fixed bed reactors short, you basically are not able anymore to manage the strong exothermicity of the Fischer-Tropsch synthesis. So how to deal with this technological problem? What we have done in our group in the last few years was that of proposing alternative ways to operate multitubular fixed bed reactors, in particular by replacing the randomly packed bed of pellets with highly conductive structure substrate to be used as reactor internals. In this sketch you see, for example, an aluminum-made honeycomb monolith packed with catalyst micropellets. The idea is that of keeping the conventional reactor design, but is that of replacing the convection, which is a dominant heat transfer mechanism in packed beds, with conduction. Conduction within the thermally connected solid structure of the honeycomb monolith. In such a way, we can exploit a heat transfer mechanism which is scaling sensitive. And as you can see in this case, both the radial heat transfer coefficient and the wall heat transfer coefficient are insensitive on the size of the reactor. And so this is appropriate to develop compact scale reactors. And to give you a practical idea on how the performances can be different by adding in the reactor a highly conductive structure internal, I want to show you some data we collected at Politecnico di Milano in a semi-pilot plant reactor, where we studied single tubes with a very short catalyst bed, only 20 centimeters long, 1 inch in diameter, representative of a very short tube of a commercial unit. And I want to show you the difference in the thermal management by using a packed bed of pellets and a structured substrates. And we have tested many different structured substrates with different geometries. We started with highly conductive honeycomb monoliths, we tested open cell foams, and then we tested the 3D printed periodic open cellular structures. Well, in this slide what you can see are the temperature profile we measured inside the reactor by running the Fischer-Tropsch synthesis with a conventional packed bed reactors at different levels of conversion. And what you notice, these are the values of conversion, is that even with CO conversion below 10%, the temperature gradients in such a short reactor are dramatically high. with the CO conversion of 7%, we measure an axial temperature profile of almost 30 degrees C. When we replaced the packed bed with a highly conductive structure internal packed with the catalyst, we were able to run the same reactor, so with the same size, same amount of catalyst inside, same process conditions, which strongly decreased the temperature profile. And here on the right-hand side, you can see that even at conversion as high as 70%, the temperature gradient in the reactor is below 10 degrees C. So you can see a complete difference. So my first take-home message from this experience is that highly conductive packed reactors represent a solution to design compact and flexible unit to be used for the Fischer-Tropsch synthesis when applied to the exploitation of CO2, and in general to be applied for all the highly exothermic processes to hydrogenate the CO2 into fuels and chemicals. And what this plot on the right shows you is that by playing with the structure of the internal substrate you use, you can basically tune the heat capacity of the reactor, always looking for the best compromise between the catalyst inventory in the reactor and the heat transfer performances of the reactor. Well, the second case study I would like to share with you deals with the synthesis of lower olefins out of CO2 and hydrogen. And this process can be carried out according to two routes. One is the modified Fischer-Tropsch route, according to which you exploit an iron-based Fischer-Tropsch catalyst, and you make lower olefins out of CO2 going through the production of CO. The second route, and this is the route that I want to present you today, is a two-step process going through methanol. So you make methanol first, and then you convert methanol through MTO process. I would like to focus on this second process because it is reported in the literature that this process is more selective than the first one, and that's very important when you want to make a chemical such as the lower olefins. So let's start analyzing what happens if you carry out the process in a single reactor with the two catalysts, the CO2 to methanol catalyst first and the methanol to olefin catalyst then. So these are the performances you can measure for the CO2 to methanol, exploiting a state-of-the-art low-temperature methanol synthesis catalyst based on indium and a state-of-the-art high-temperature methanol synthesis catalyst based on zinc-chromium. What you can see on those pictures is that, and in particular from the plot on the left, is that the reaction is kinetically inhibited at the low temperatures, so the CO2 conversion is quite low, while when you increase the temperature, the CO2 conversion can be increased, but basically you lose selectivity. Instead of making methanol as you want, you make essentially CO. So from these plots, what you can conclude is that if you want to make significant amount of methanol, you should operate possibly in an intermediate range of temperature to find a good compromise between kinetics and thermodynamics. But then if you analyze what happens in the second part of the bed, where the methanol to olefin reaction takes place, what you found is that the methanol to olefin reaction occurs only if the temperature of the reactor is over 350 degrees C. However, those conditions, as the plot on the left shows you, the most abundant reaction products are paraffins and not olefins, because all the olefins in the presence of the excess hydrogen you have in the reactor for the production of methanol are hydrogenated to the corresponding paraffin. Also, what you can observe, and this plot on the left that is a function of the time on stream clearly shows you that, is that the catalyst quickly deactivates in these conditions. And after a few hours, instead of making hydrocarbons, you have methanol leaving the reactor, indicating that the catalyst you're using to make the MTO is completely deactivated. So how to fix this problem? How to make the desired products, the olefins, out of CO2? The idea we were studying was that of putting the two catalyst functionality in the reactor in a different arrangement. Instead of making the methanol catalyst first and the M2O catalyst then, we studied the possibility to make a mixture of the two catalysts, so to be able to progressively make the methanol, keep the methanol concentration low, and progressively making olefins and reducing the contact time of the olefins in the reactor, so to prevent their further hydrogenation into the paraffins. And this is what we obtained. By running a combined bed with the methanol synthesis catalyst mixed with the MTO catalyst, what we found was that, in fact, we were able to measure significant values of CO conversion, of CO2 conversion, about 40%, and among the products we found a significant amount of olefin, with an olefin to paraffin ratio 1:1. Obviously, the system is not optimized, and what we found is that the way in which you arrange the two active phases, the one for the methanol synthesis and the one for the MTO, is very important. And I want to show you, in fact, that if you increase the contact between the two active phases by intimately mixing the two catalysts, what you obtain is that you completely lose the selectivity of the process. You basically make CO, but you don't make any more olefins. While on the contrary, if you take the two active phases and you put them too distant, you also lose performances and you make more paraffins than olefins. So there is an optimal conditions, an optimal degree of interaction between the two active phases, which allow you to maximize the performances. And the take-home message that I would like to give you from this experience is that every time you have to convert CO2 into e-fuels and e-chemicals, and you have to catalyze together two reactions with different requirements, by playing with the interaction between the two active phases, you can improve the performances of the reactor. And this concept, of course, applies to the CO2 to olefin process, but in general to all the processes where this requirement is true. And with this, I hope that I've convinced you that the decarbonization requires the production of e-chemicals and e-fuels, in particular in the context of the energy transition, so for the years to come. However, the industrial deployment of the technologies for the CO2 hydrogenation to e-fuels and e-chemicals poses many technological challenges at different scales. So this is a multi-scale problem. We have problems at the catalyst scale, we have problems at the reactor scale, we have problems at the process scale. But this poses new opportunities, this offers new opportunities in terms of new catalyst development, new reactor development, and new process development. And I would like to conclude by thanking all the PhD students that worked on these projects through the years, my colleagues and co-workers, and then the European Research Council, ENI, and Technimon for the financial support, and you for the kind attention.
It's now a great pleasure to call Silvia Bordiga for the last presentation. Silvia is full professor of physical chemistry at the Department of Chemistry of the University of Turin and is professor in the Department of Chemistry from the University of Oslo. Is associate editor of ACS Catalysis and is part of the editorial advisory board of Journal of Catalysis. It's a long list also to mention all the honor and the prize of Silvia. I just want to remind some of them, the Francois Gold lectureship, and lastly, in 2021, the Feltrinelli Prize for Physics, Chemistry and Application awarded by the Accademia Nazionale of Lincei. The impact of the research of Silvia on the communities is witnessed by more than 450 publications and a fabulous H index of 107. She is also the owner of several projects, between them one important synergy project, and actually is working also in communication, also theatrical communication of chemistry, that is always a nice thing. So we can ask Silvia to come here and talk with us of synthesis of commonly used molecules through new processes, methanol as key intermediate. Please.
Thank you for the kind introduction, and thank you to be here till very late today. And the previous talk was an introduction for what I'm saying, because my focus will be methanol. And methanol has been described as a molecule that can be useful in a sort of artificial photosynthesis, as was described by Professor Hola many years ago. And in this very interesting paper, he suggested to use methanol as a carrier for energy and the development of different processes. And the artificial photosynthesis can help the standard carbon cycle, which is reported on the right of my slide. And thinking about this, the importance has been mentioned already before. We need to develop catalysts based on non-critical elements. We need sustainable hydrogen, and then we need atomic and energetic economies. So trying to have processes at low pressure and low temperature. And we have seen many applications of methanols, has been already presented many times today. At the moment, methanol is produced from fossil sources, and then we can use methanol in so many applications. So really, methanol can be considered as a key molecule for a sustainable development. But how to make methanol from carbon dioxide? This was introduced from the lecture before. We have seen that we have limits in the conversion, and per pass we have a possibility of conversion lower than 20%. And so the production of methanol through carbon dioxide requires some implementation. And so the idea that we developed in this process is, as already introduced by the previous talk, to combine the synthesis of methanol with another reaction, and so the conversion to methanol into hydrocarbons. And this has been the topic of this project that is approaching the last phases, and sponsored by the European Commission. And we started with the idea of combining the synthesis of methanol using alloys, so palladium zinc alloy, but then we moved to mixed oxide in order to be more sustainable in the process. And in particular, we had to face the different process that we have to combine the problem of having a reaction which is favorable at lower temperature, at high pressure, with a reaction instead that needs higher temperature and is run at standard pressure. And to do this, at the moment when we started, we had a lack in the condition, and so we decided really to try to develop catalysts on both sides. So starting from the catalyst for the synthesis of methanol, we moved from alloys to mixed oxide, and being able to find a mixture that was compatible with the second reaction, so the conversion of methanol into hydrocarbon. And in particular, we focus on mixed oxide based on zirconia doped with zinc, gallium, and cerium. And this was done in collaboration with other labs. And if we compare the benchmark, which is the copper on zinc oxide on alumina, which is the benchmark catalyst for the production of methanol from carbon dioxide, with the other mixture, and we look not only at the conversion but also at the selectivity towards methanol, we see a big difference in the different mixed oxide. For instance, the zinc cerium zirconia system is showing a very high conversion of carbon dioxide, but a very low selectivity towards methanol. And so now I will show you some results on the series of zirconia zinc materials. And in this we have studied different compositions, so with a pure zirconia in combination instead with zinc zirconia with a different doping, so 5%, 15% and 30%. And first of all, the presence of zinc is changing the structure of zirconia, so we don't have anymore the monoclinic zirconia, but we have more cubic tetragonal zirconia. And if we look more in detail at the XRD pattern, we see that in some peaks we observe a shift on the peak in the diffractogram, and this is due by the presence of zinc inside the lattice. And so the fact that we don't see an extra phase, so only when we load a very high amount of zinc, we observe also the fingerprint of zinc oxide, while for the other two compositions, we don't see any evidence of the formation of extra phases. And so we have the indication that zinc with medium content is able really to make a solid solution or very small cluster inside the zirconia particles. And the study was combined with many approaches characterizing the material and also combined with some molecular modeling that try to describe the mechanism of the effect of zinc inside the zirconia. And so here is the sketch of the process. So we start from carbon dioxide and hydrogen, then we make methanol, and then methanol is converted inside the zeolite, producing propylene and propane. This was the target molecule for our project. And when we look at the performance of the catalyst, in the condition that was the target, so 350 degrees and 30 bar, we don't see a very promising result when we look at the selectivity for methanol. So you see here the selectivity is very low, while the conversion is not too bad, but the selectivity is very low. In fact, we produce mostly carbon monoxide. Likely when we combine the mixed oxide together with the zeolite, instead what we observe is an improvement in the performances. In fact, in this case, in the same condition, we have a better performance with a conversion which is sufficiently good and the selectivity which is not too bad. However, in this case, we have used a commercial ZSM5, and ZSM5 is not very good for the selectivity towards propylene, which was the target of our reaction. And so, in the second step of the project, we have trying to develop also the catalytics part related to development of the zeolites. In order to be able to be more selective towards the propylene, so the small olefin, we know that we need to work with smaller cages. And so we moved from the SAPO34, which is the commercial and standard catalyst, to other materials. In particular, we worked on MAPO18. MAPO18 was made containing not only the silicon, which is introducing the strong acidic sites, but also with other hetero elements. In particular, we worked with magnesium and cobalt. And with magnesium and cobalt, we see that we have a better performance in case of all the conditions that were tested. And so also adding some extra molecules, such as also an extra amount of carbon monoxide in the feed system. And the reason why these catalysts are better than the simple SAPO18 is that magnesium and cobalt are providing more acidic sites inside the lattice. And this is seen here when we compare the infrared spectra of the SAPO with the material with magnesium and cobalt. The fact that this component is shifted at lower frequency means that we have the presence of stronger sites, and this is important because this allows to have a higher polarity in the bonds, and providing higher acidity improve the catalytic behavior. At the moment we have some work in progress trying to make these heteroatoms more stable inside the lattice in order to be able to make the final catalyst that then we have to put inside the reactor, because this process requires to reach the demonstrator level, and so we have to speed up the research in order to be able to make the catalyst that will be used in the demonstrator. So with this, I conclude the first part related to methanol synthesis coming from carbon dioxide, but I want also to describe a different path that exploits also a totally different chemistry. So we are discussing about the impact of carbon dioxide as greenhouse gases, but we know that also methane, natural gas, has a big effect. And so the possibility to convert natural gas methane into methanol directly is also a big relevance. And we have enzymes which are able to do this, methane monocygenase. We have two families of enzymes, the soluble one based on iron, and the particulate based on copper species. And the particulate enzyme has been studied a lot, but with many difficulties, because when the core of the enzyme is extracted, then very easily it loses the reactivity. And so for many years, people that were studying this enzyme were studying something that was actually something that was not able anymore to perform the reaction. And so sometimes also the results were not very, very meaningful, and I will show you some very new results. In the same kind, so we have tried in many labs to develop catalysts containing both copper and iron that were trying to simulate what the natural enzymes are doing. And in particular, many years ago, already in 2005, there was this nice publication suggesting the capability of zeolites. So here we are in the inorganic sphere, where copper, isolated copper, was able to convert methane into methanol. And combining with this, we have many other examples based on homogeneous molecules, such as this, or systems based on the formation of hybrid systems, or organic, inorganic inside lattice, like metal-organic framework. And this is a very recent result published by Amy Roswing, which is one of the most known scientists studying the methane monocygenase, that now is proposing a totally new center for the catalytic reaction, which is a monomeric copper center. And this very new result was possible exploiting the combination of cryo-electron microscopy and also the possibility to stabilize the enzyme inside a lipid environment that allow to maintain the catalytic behavior. And so now we have a different picture of the local site of the possible copper catalytic site, where we have not only the presence of some nitrogen, but also the presence of an oxygen very close to the copper. And this opens a totally new landscape in the development also of our catalyst. In this respect, so starting from 2020, we started this project involving 4 labs, my lab in Turin, then the lab of Uni Osby in Oslo, the lab of Vincent Elsky in NMBU, and the lab in MPI with Serena De Beer. And our target is to be able to develop catalysts, metalloenzyme based not on the methane monocygenase, but a simpler enzyme, which is the MPMO, which is now able to make hydrolysis of cellulose, so it's an enzyme which is not able to make exactly this reaction, but is simpler than the methane monoxygenase. And so now we are trying to modify this enzyme, making able to do this reaction. In the meantime, we are working on zeolites, and also we are working on molecular units that then we plan to put inside the metal-organic framework in order to be able to make this reaction. And in respect to this, I'm happy to share the first series of results that we have obtained studying these complexes, which are quite simple and are not new complexes, but were not used in this context. And the possibility of changing the substitutional group on the ring make the copper sites with a special hindrance, and in this way the copper that is introduced as copper 1 can easily, or at least more easily, change the oxidation state from copper 1 to copper 2, being able to react with oxygen and then make the oxidation of methane or a substrate, an hydrocarbon substrate. And in order to try to understand better the chemistry of these complexes, we have developed a series of measurements trying to follow the different effect of substituent on the ring in order to select the best complex and then introduce the complex inside the organometallic framework. So here we have the different complex where we have a different substituent. So in this case we have the methyl group on the position of the two pyridine, and in this we have followed the chemistry followed by voltammetric cyclic, and in this case on the right instead the change in the optical spectrum. In particular we have the starting point where we don't see any DD transition, so we don't have any copper 2, here is flat, and when we contact the complex with the oxidant, the alkyl hydroperoxide, we have the formation of this component here, which is the indication of the presence of copper 2. And then what we see is the possibility also to follow the full cycle, and so the reactivity of this complex together with a substrate. And this can be followed with a combination of technique. And in particular, what we have done is a multi-laser Raman study, in particular exploiting the possibility to excite the molecules with different lasers. We have been able to follow all the steps of the reaction. So here I compare the spectrum of the molecule, which is the gray curve, with the molecule inside the solvent reported at the bottom of the figure here. And when we react the molecule with the terbutyl hydroperoxide, we observe a dramatic change in some specific fingerprint. In the meantime, we observe a change in color of the system. So the formation of this oxo species has been investigated in many ways, and is not only the matter that we observe the oxidation of the copper, because when we react the complex with another oxidant, so for instance this oxidant here, we observe the formation of copper 2, but we don't have any further effect in the optical transition associated to the oxo species formed on the copper. Instead, this species is associated with a fingerprint reported in this part. So we have followed this with Raman, doing really an in situ experiment where we combine Raman collected at electra beam time, so at electra synchrotron source, and in combination we also collected the UV visible spectra at the same time. And so we had a reactor where part of the solution was measured at the synchrotron, and in the same time we collected the Raman spectra. And then after a while, what we did was to combine this step. So the first we have the oxidation part, and then we reacted this with a substrate. At the moment we are working with cyclohexene, so a molecule which is easier to oxidize than an hydrocarbon. What we observe is that we observe a change again, so the spectra comes back. But with the use of this laser, we don't see any fingerprint of the product. And so in order to be able to see the fingerprint of the product, we changed the laser. So we moved from 266 to 2026 laser. And in this case, we were able to see this fingerprint here, which is associated to the cyclohexanol and cyclohexene. And this has been already followed with the UV visible, where we can say the change in the fingerprint associated to the copper 1. First, we observe the decrease of this of the fingerprint here when we contact with the oxidant, and then when we introduce the substrate, we observe the restore of the fingerprint associated to the copper 1. And so in this way, we have been able really to complete the overall reaction. So now we know that we have a molecular unit which is able to do the chemistry, and what we are developing at the moment in combination with the colleague in Oslo is the introduction of this species inside the framework of a metal organic framework in order really to make the catalysis an heterogeneous catalysis. And in this work is in progress. And with this I want to end this short talk saying that I think that we have a new pathway for methanol synthesis, and but to do this we need really to develop a new catalyst, and we need also the combination of different approaches in order to find more reliable and robust information. And it is important to be able to have the possibility to study more than one molecules or system in order to be able to follow a trend in order to make a stronger conclusion. And with this, I want to acknowledge all the people involved in this sort of work. So also some companies that are also providing some big questions that they require answer from us. And of course, the support from the European Commission and all the synchrotron facilities that help us with the study. Thank you.
Vediamo se proviamo a fare una piccola discussione. Sì. Diciamo, chiamiamo i nostri colleghi.
Okay, there is still some time to open the discussion. Then I would like to ask all the speakers to stay at the table.
Okay, so I think that we have heard a lot of very interesting contributions. For sure, the complexity of the argument is very high, and this is demonstrated by the different topics and the different technologies that have been proposed, ranging from modification to the old technologies in order to decrease the carbon footprint to very new catalytic materials and new technologies for to solve this problem. This, of course, is good, meaning that we have a lot of work to be done, and so this is, of course, a great opportunity for us. But also we have a responsibility to try to solve the problem as much as possible. So since we are a little bit, well, we are late actually, instead of challenging the speakers with some general question, I would like to leave to the floor time for questions that I'm sure that should be a lot, because we really heard this afternoon a lot of different topics and different questions. So, okay. Please introduce yourself and make the question.
I'm Gianluca Farinola from University of Bari and Società Chimica Italiana. It's been a very interesting sessions and many points to discuss. I would like to, in particular, focus on something which is relevant to the storage and transportation. Many aspects have been considered for evaluating different techniques, including cost, carbon footprint, and sustainability. I was wondering if also the safety of different processes have to be taken into consideration. We are handling hydrogen, and so I'm sure it poses some issues relevant to safety. And the second question, I've been pretty, I mean, it's pretty interesting, the possibility of storing hydrogen in form of liquid organic compounds, because hydrogenating and dehydrogenating organic compounds has usually very high kinetic barriers. So I was wondering how convenient is this process, and how does it compare with the others, which apparently are kinetically much easier?
Okay, thank you very much for the question. It seems that I have to answer. From the point of view of safety, in some sense, this is definitely a point that is taken into account. I was shortly mentioning this matter related to the comparison between 700 bar under your seat or having something closer to 30 bar. For sure, there is the needs of normatives still, just to understand a bit better how to, to implement that in the market. For sure, for the car industry, this has been quite well tested, and it seems that even in the real application, when you have a brake or something like that, hydrogen is going up quite soon. So in some sense, car industry says that is even 700 bar quite safe. But you are fully right in saying that is a point to be taken into account. I'd just like to mention that Europe is very much worried about that. They have the GRC that is specifically playing a role in that. There is a lot of meetings related to the safety. Concerning the liquid organic hydrogen carriers, I simply say that that is very much pushed by Europe right now. Liquid is something that companies like to have, because the concept to have something liquid is much more familiar, mainly for transportations. My message was there is plenty of molecules around, and probably the markets could be open with respect to what we have already in the market. The company that is selling that molecules that Professor Centi was also showing in his presentation, actually they found solutions. The weight percent is quite reasonable. They are in the condition to charge and discharge in reasonable condition, but there is plenty of room, from my point of view, of improving. Organic chemistry is very, very complicated. There is a lot of room for that.
Okay.
I have some questions. You mentioned that in Switzerland a relevant role is to be played by hydroelectricity. What is the impact of climate change on the availability of water and snow in Switzerland for the foreseeable future? So is there any impact on this option? And then I have another question for Professor Barrico about the hydrogen storage underground. What about the reactivity in terms of geochemical reactivity and bacterial reactivity? Because there are some evidence that in some cases the hydrogen is consumed to a pretty high level. And finally, a question for Dr. Marchionna. How many blue hydrogen plants are active in the world now? Thank you.
Maybe then I start with the hydroelectric power plants. There is certainly an impact, but I'm not a specialist for that. From what I read is that the climate change will have an effect on the water input, and especially when the glaciers become smaller, there will be less water melting from the glacier during the summertime. So there will be an impact, and I think, Switzerland is nothing special. Italy in Piedmont, you have exactly the same problem. I think there where the glaciers are going to disappear, we have to put a dam in order to keep the water in the mountains and not have a flooding in the late spring and then a certain period without water. This is also a measure to protect the environment and to keep the rivers flowing throughout the year and not only in a certain period. But this is very much debated topic in Switzerland. Environmentalists are very much against any technical constructions in the mountains. And so we'll see. Will be decided from politics and not from technology.
Well, from my point of view, I apologize, I'm not very expert in underground storage. For sure, our colleague in geological department, they are dealing with this subject. Of course, it strongly depends on where you are planning to put hydrogen. I think the possible reaction with the rocks, it seems a bit more severe than the reaction related to the microorganisms or whatever. So to my feeling, that is a bit less serious. But you're fully right, that have to be taken into account. Start a running project, actually they make some preliminary tests, and it seems there is plenty of place where you could put quite safely hydrogen, so it seems something affordable at least.
As regards blue hydrogen, there is the plant that I mentioned in Canada. Maybe there is another small plant, I don't remember exactly where, but in the last year there are a lot of announcements, especially in the US, of possible new plants. Of course, moving from the press release to the final plant realized that it works, it runs a lot. So I'd like to wait for real facts instead of press release. It's also clear that in principle there is no particular obstacle if you have the infrastructure for managing CO2. It's clear that in the US there is no particular issue because they have a network of CO2 pipelines that is so huge, and also they have a lot of reservoir for storing CO2. So I believe that this will be a solution at least for some regions. Of course, it's not a solution that you can have everywhere, but I'd prefer to wait for real facts. What I'm seeing is that there is a definite increase of proposals.
Thank you again for all of your presentations. They were very nice. I have a quick question for Professor Züttl, and that is, we agree that there are applications in which we will continue to use liquid hydrocarbons, aviation, and these kind of things. But as long as we use a combustion engine, there will be a NOx formation. So regardless of how renewable these liquid fuels are, there's constantly NOx generated in these combustion engines. Is this a concern, or should this be a concern for us in the long run? Can we deal with this, or can we ignore this constant NOx emission that will remain, right?
You are absolutely right, especially for turbines a problem. I think the internal combustion engines, they have a catalytic system in the exhaust gas pipes to deal with the NOx, but in the turbines it's not possible, and that's a concern, yes. I have no easy solution to that. Maybe some additive to the fuel in future could help to reduce the NOx. But in turbines, you don't want to lower the temperature, otherwise efficiency goes down. So that's an issue.
Models which predict how much NOx this will be until the end of the century.
Even after switching to completely CO2 neutral fuels, are there any techno models or?
This I don't know. I guess it's known how much NOx the airplanes emit, and you are absolutely right, that will not change. If we have synthetic fuel, we still have exactly that same problem.
May I add a few words about, so for sure there is a big also market for the development for the NOx catalyst. So for airplane at the moment there are no planes, while for ship instead, so the maritime transport, instead there are activities ongoing. And so the producer of the NOx catalysts are still confident that for many years they will have something to sell.
Okay, there is another question.
Mario Surdo, Siena Mate. My question is for Professor Baricco, related to the hydrogen storage. And the question is, considering the large variety of materials we have been listening to today, what is your opinion about the competitivity still of the hydrides, considering the limit of the temperature to dissolve the hydrogen and the cyclability of those materials? So do you think that it is still worth it to invest in hydrides from the technological and research point of view? Thank you.
Yes, well, I was very much pushing in the direction of hydride, that it was very clear. So in some sense, the answer is definitely that is an option. To my understanding, that's probably will be not the solution. Probably in the transportation that will be limited maybe for ships or something like that. There is room in some application where you need weight, and in the market there is already something in the handling machine just transporting stuff. Well, actually, one of the last logos that I put in my screen is a small company that we built up, started to sell. For sure, there is interest in the market. At the moment, there are some companies that are already selling, and there is a section on the market. But for sure, other options related to the gas phase and the liquid hydrogen will be definitely an option in the future. My opinion that there is not a competition, but rather a collaboration among the different options.
Okay. I have two or three questions for all of you, more general and linked between. I heard from the first speaker that there are so many solutions in so many different countries. My question is, this depends from politics, from development of different industries, or from population, education of population. It's for all this. That was not the Italian situation.
I think everything is important, but I don't think that it's a problem of better understanding. It's finally the economics that defines what the market accepts. I mean, Marcello has nicely underlined all the advantages of metal hydrides, but you can show the metal hydrides storage is much more expensive than, for example, filling an empty volume with pressure. And if you have an application where you don't want to have a high pressure, let's say in the house, in the basement of the house, for example, then the metal hydrides have a huge advantage, and if you cycle them 4,000 times, then they become economically interesting. But if you put a tank in a car where you only fill it 250 times in the life of the car, then of course you don't, and you don't want to have a high weight, then you rather take a pressurized system. But I think, as Marcello also said, there will be space for many different solutions in future, and it will also depend on what's going to happen, because of course these 700 bar tanks, they seem to be quite safe, but we know sooner or later such a tank will blow up, and then I guess the people will be shocked about what happens. And that will have a big impact then on the future, but we will see. You know, I'm not hoping that it happens, but this is like an airplane crash. Sooner or later that happens, you can do whatever you want. And with 700 bars, that will make a big impact. And such things will also have an influence on how the storage will develop in future. But no matter what we think, we're going to need storage, and we're going to need a storage that contains a lot of energy, and a lot of energy always has a potential risk. But we have also learned in the past to deal with these risks and to accept it. It's not that natural gas or kerosene or petrol would be completely without any risk. There is still many more accidents with fire of petrol than with hydrogen. But still, the people think hydrogen is more dangerous than petrol, surprisingly. Do you want to add something?
Somebody was... It's okay. Okay, the other question was related to distribution. We talked about pipelines and lines and so on. I was wondering how the actual situation, you know, with what is happening in Europe and world, can influence the distribution, the quality and the distribution of gas, the pipelines, and how can be in contracts from the point of view of conversion, the local conversion, what it means to have some local production that is also used by a small company for conversion, or how is more inexpensive have a big company with a big plant and the conversion made over there and then distributed.
Maybe I can answer again. So of course we connect renewable energy oft with a decentralized energy system, and also because currently it's mainly based on installations that people do on their own homes instead of having huge power plants. But in China, for example, they are building power plants with photovoltaics, or also in Germany with wind parks. There are power plants. And I think on a long term, again, for economic reasons, these huge installations, they are much more economic than doing it at home, especially if you have to do all these conversions. On the other side, you know, this is also true for mineral water. But now recently a market has developed where people suddenly pay for 50 grams of CO2, 20 euros to make the mineral water at home. So against all economic, suddenly that happens, and same could also happen for energy. If it becomes interesting to produce it at home, maybe small systems will be installed. But I'm personally convinced that we also in future we need large storages and large power plants, centralized systems. I cannot imagine that the whole energy system is just based on very small producers, first of all because it's very expensive, and secondly it's not going to be reliable.
I can simply add that my feeling is that probably what Andreas says is very Correct, but it might be that both very centralized and delocalized solution will survive in some way. There is a lot of social aspect behind that. For instance, there is the issue of energy communities that in some sense is pushing with the idea to have locally some production and then small way to store and then to share again. So my feeling is that the two options probably will survive, but for sure pipelines, of course, will be very much related to the very centralized and big production. If you ask what is running right now, I was mentioning this normative that we have, at least in Italy, that is 1%, that is incredible. And we have a project in the Torino airport, and actually there is a trailer moving up and down with the trucks because there is no way to move in a different way. So at the moment, we are still in the same situation we were years ago, but the pushing is very much, it's very strong at the moment.
Yeah, I would like just to make the comment on what has been just discussed about the local versus the distributed, because I think local sometimes has might have some different impact if we think to heavy industries, also all the hard to abate sector. In that case, local doesn't mean really small scale, means something local because the hard industry is local, is not distributed. So definitely I agree with Professor Baricco on the fact that both options need to be fully evaluated to really best, to exploit at the best the option.
Can I add something? I sure agree that there is a push toward decentralization of technology, but there is still, there will be a combination of the two, but depends also on technologies. And there are, especially what Lucia said, there is some situation in which the decentralized system is more sensible than a centralized one. So it depends on the sector and it depends on the technologies. I mean, it's like the big photovoltaic fields instead of the photovoltaics on single home. It depends on the use of the technology and on the specific area that you are considering. So there is not, in my opinion, a specific technology. There are several kinds of technologies that will cover different aspects of the energy sector, even with hydrogen.
Okay. Any question? Please.
Regarding backup power, as an example, probably is micro-distributed. Regarding backup power, in my opinion, micro-distributed storage would be more feasible than centralized, because of course there are so many small companies, industries that have a photovoltaic plant on the roof, and of course they don't want to inject this power into the grid. They want to store and use this power for their internal applications. And as you know, in Italy at the moment, you need to inject into the grid and after get back, and of course you need to pay tax for that. That is amazing. So there is a lot of interest in micro-distributed energy storage and hydrogen storage, replacing batteries in this case. What is your, I don't know, who would like to answer? Okay.
Yeah, I just short comments. I mean, you're fully right. But what we have all the time to remind that is in the hydrogen cycle, we have an efficiency of the electrolyzer, we have an efficiency of the fuel cell, sometimes we have an efficiency of the handling system. Efficiency has to be multiplied. At the battery in the middle, actually there is nothing at all. So for sure, this, let's say, comparison between hydrogen and batteries is on the table. It's a discussion of day by day. My feeling is, again, is not a matter of competition. What I call is an alliance, because there are some situations where definitely hydrogen there is no room at all, other situations where at the moment there is no room for batteries. What you mentioned, the backup power, I think is strongly dependent on the size, on the specific situation, but nowadays there is batteries that actually can play quite a key role with a much higher efficiency. So once again, it's a matter to define case by case what is the better. This is my personal opinion. I don't know if.
I have a question from my side. I don't know, probably for Professor Zuttel, but maybe other speaker may answer. When you show that, for instance, the production of e-fuel is rather expensive as compared to other source of energy, due to the fact that you lose in efficiency in the transformation or the various transformation that you have. I wonder if in this calculation it has been taken into account the fact that in case of the e-fuel you have already the infrastructure that are available. If you want to switch from e-fuel to hydrogen, for instance, you have to build completely the infrastructure. That is a significant problem in my view. So that may make changes in the economy and also in the carbon footprint, because of course to build a new infrastructure is expensive also in terms of CO2 emissions. So may have you some comments on that?
Yeah, you're completely right. I tried to mention that a bit, and that's the fundamental difference. If we electrify everything, we have to change all the applications in order to run them electrically. Same with hydrogen, we have to adapt the applications, and that's also a cost. But this cost goes to the consumer, not to the company or to the government installing the plant. And there is, of course, a push to bring as much as possible of the cost to the consumer. I mean, that's what you mentioned before with the electricity from the PV on the roof. Most people, they are producing electricity and inject it into the grid. And then in the evening, when they come home, they buy the electricity 4 times more expensive from the electricity company again. And that's also why it's so distributed right now, because it's very interesting for the electricity company. They just earning money by moving it forward and backward. And we should not forget, currently we have only small partial applications. We have over 50 square meters of photovoltaics on the roof, but there are 6 people living in that house. And if you want to produce the energy these 6 people consume, then you would need something like 600 square meters. But most people don't have such a roof. So, it will also change as soon as we're going to have a larger contribution of the renewable energy. The whole system will change because of that. We are still in these niche applications where we do something because it's nice to have, not because it will bring us completely away from the fossil fuels. And still, we will see this winter. This will be a very interesting experience, I guess, for whole Europe. What happens if we do not get the electricity when we need it from outside? At least in Switzerland, we have now big discussion because the government first told all those who have photovoltaics on the roof that they are on the safe side. And now it turned out that, of course, none of this system is going to work if there is no grid, because these inverters, they all rely on a grid. And if the grid is not there, no matter how much battery you have in the basement, you will also not have electricity. And so I guess we will go through a learning phase and then become somehow smarter for next year, and then move in a more intelligent way in the future.
I think we're ready to close because it's time to go.
So we thank all the speakers again.
Thank you very much. Okay, it has been another very interesting afternoon, but we will meet tomorrow precisely at 9 o'clock. Don't forget.